In the spring of 1905, a storm broke out in the mind of Albert Einstein. At least that is how Einstein himself described it later in life. And the result of that storm of thinking is the special theory of relativity, a theory that completely transforms our understanding of space and time and matter and energy. I mean, Einstein found, completely counter to experience, that clocks in motion tick off time at a slower rate. He found that objects in motion are contracted along their direction of motion. He found that clocks, that one set of individuals say are in sync relative to each other, he found that if someone's moving relative to those clocks, they would say they're not synchronized. And of course, he also found the most famous equation in all of physics, E equals mc squared, establishing this deep, hidden connection between mass and energy. Now, you should say to yourself, if there is such an unexpected nature to reality that we have missed through our everyday experience, why have we missed it? I mean, why aren't we aware of special relativity right in our bones? And the answer to that is, when we look out at the universe, we recognize that there are a huge range of scales that constitute reality. And we humans only have access to a very small part of that totality. So to give you a feel for that, let's look at one axis, a length axis. And if you look at the scales that are out there in length, atoms, 10 to the minus 10 meter, viruses, 10 to the minus 8 meters, red blood cells, 10 to the minus 6, single-celled organisms, there we humans are, 2 meters, the Earth, 10 to the 5 meters, solar system, 10 to the 13, galaxy, and on to the observable universe itself. A huge range of scales when it comes to length, and we humans really only have direct access through experience to a small part of that. And that's only the axis of length. Imagine we look at the axis of mass. There, too, we will find a huge range of scales, right? So if we go back and look at atoms, they weigh in 10 to the minus 26 kilograms, go down to red blood cells, 10 to the minus 15. Humans, well, depends who you're talking to, but about, 100 kilograms or so. Solar system on to the entire universe, the observable part, 10 to the 52 kilograms. A huge range of scales in mass. We humans only have direct access to a small piece of it. One more axis to look at is the axis of speed. So we humans, we walk around the world at certain ordinary everyday speeds. Sometimes we go into airplanes, but there's a huge range of speeds out there. The growth of human hair, that's pretty small. Human speed, typically, space shuttle, 10 to the 3 meters per second. Speed of light, that's a number that's going to come up a lot in our discussion, 10 to the 8 or so meters per second. The point is, in this spectrum of all possibilities, in length, in mass, and also in speed, we humans occupy a tiny, tiny part. So our experience, the experience that has given us our intuition, is built up from a very limited sense of what is actually out there. So our intuition, which really has come in some sense from evolution, right? So we evolved out there in the jungle, and our intuition got built up in order that we can survive. The survival value of understanding your environment is what matters. We humans only have access to a small piece of the totality of what's out there, and therefore it would be surprising if what we have experienced really does tell us about the physics at all possible scales, in length, in speed, and in mass. And it turns out that indeed it is the case that when you look at extremes of mass or length or speed, the world operates, the universe operates in ways that we are not accustomed to. If you are looking at extreme, say, a very small size, the new physics that comes into play is called quantum mechanics. If you are looking at extremes of huge mass, the new physics that comes into play is the general theory of relativity. If you are looking at extremes of speed, how the universe behaves at very, very high speeds, then it is the special theory of relativity that comes into play. That is what we are going to be discussing. So in a nutshell, all of the discussion we are going to be having here is focused upon how the universe behaves at very high speeds. That is the special theory of relativity. Since speed is the fundamental core of what drives the special theory of relativity, let's start at the beginning and ask the most basic question of all, which is, what is speed? Well, we all know the answer to that, but let's get all on the same page. So if that car, say, has a speed of 100 kilometers per hour, we all know what that means. If we look at how far it's gone divided by how long it takes it to get there, so let's say this is 1 hour journey. If it's going 100 kilometers an hour, we know that it will have traveled 100 kilometers in that hour. That's what speed is. So in essence, speed is nothing but distance that an object travels divided by duration. Now, expressed in that language, speed might seem like, I don't know, a kind of boring concept, a pedestrian concept. Why concern yourself with speed? The answer to that is clear if we recognize that distance is a measure that has to do with space. Duration is a measure that has to do with time. So if we find, as we are going to find going forward, that speed has unusual features when the speeds involved get very big, near the speed of light, what we really will therefore be learning is that space and time have weird, strange features. That is what we are after. Okay, good. That's where we're headed. Let's start by first thinking about the non-strange features of speed, the features that we all hold in our intuition. So what are the basic features of speed? Well, first off, speed is a concept that even before Einstein was known is a concept that is relative. What do I mean by that? Well, imagine we look at this car, say it's going 100 kilometers per hour. What we need to say is 100 kilometers per hour relative to the road. Why? If that road is itself moving, let's say it's on a boat, the boat is moving, then the car's speed relative to the water is not 100 kilometers per hour. And if we zoom out and look at that car on the surface of the Earth, and we realize that the Earth itself is spinning around, the Earth itself is going in orbit around the Sun, with respect to the frame of reference, our perspective right now, that car is executing a pretty complicated motion, not just 100 kilometers per hour. So it's always vital when you're talking about speed to recognize that you can only ever frame the idea of speed for ordinary objects that we encounter as the object has this and that speed relative to this or that object. You need to specify the reference in order that the speed that you are specifying has any meaning at all. Okay, so that's a very basic feature of speed, that it is relative. Another basic feature of speed is that it is additive and subtractive. So what do I mean by that? Well, let's imagine that we have two characters who are playing a game of catch with, say, a football. George and Gracie, two characters that we are going to encounter often in our discussions. And imagine that they're throwing that football back and forth at, say, 5 meters per second. Now, that's all well and good, completely understood. But let's imagine that they go out to play a game of catch on another day, and Gracie is surprised to see that George has a hand grenade. Now, she doesn't like hand grenades, and so she runs away when he throws it because she knows that by running away from the hand grenade, she can change the speed at which it approaches her. She can subtract her own speed from the speed of the oncoming grenade, and in that way have it approach her not, say, at the initial speed at which it was tossed, which, for instance, might be just like the football, 5 meters per second. Instead, if she runs away at 3 meters per second, she knows that now the grenade will approach her more slowly at 2 meters per second. And that is a good thing when it comes to hand grenades. Similarly, it's the case that if an observer like Gracie is to not run away, but say run toward an object that is being thrown at her, the speed with which she approaches the object will be added to the rate at which it approaches her. So if it was thrown at 5 and she's running toward it at 3, well, we all know that that means it will approach her at 8 meters per second. Speed is additive and subtractive. You can change the speed with which an object is coming toward you by either running toward it or away from it. Now let me quickly mention, just as a small footnote, these basic calculations that we've done here, we surprisingly are going to find that they are only approximate when you take into account some of the strange features of relativity, but that's something that we will encounter later, especially if you're doing the math version of this course. But in terms of the basic idea that comes from our intuition, you certainly would anticipate that if you run toward an object, its speed will approach you more quickly. If you run away from an object, it'll approach you more slowly. Third basic feature of speed that, again, we are all familiar with is this. When you are executing a very special kind of motion, what we call constant velocity motion, motion that has a fixed speed, fixed magnitude, and a fixed direction, then you can't feel that motion, right? You can't feel that motion for a very good reason. If you are executing constant velocity motion, you are completely justified in claiming to be at rest and the rest of the world moving by you. In that sense, constant velocity motion is very special because it is motion that is completely subjective. There is no absolute notion of being in motion when the velocity is constant. So let me give you a quick example of that. So let's imagine that we have one and the same physical situation described from two different perspectives. So what I'm going to imagine is having George and Gracie floating in space, okay? Floating in space. Now here's George's view of the events. He looks out and he sees a character, Gracie, coming toward him, and she waves as she passes, as does he. His perspective is that he is stationary and she is rushing by him. Good. Now, I'm going to show you exactly the same situation, but from Gracie's perspective. So what does Gracie say? From her perspective, she says that she is stationary out there in space. She looks out into the distance, and she sees George rushing by. He waves, she does too, and he goes on his merry way. Is one perspective right and the other wrong? Absolutely not. You are completely justified if you're not accelerating, if you aren't changing your speed or changing the direction of motion, to say that you are stationary. Now, the reason why I'm emphasizing constant velocity motion is something that you have all experienced, right? If you are in a car and you take a sharp turn, you feel your body being pushed this direction, you know that you are moving. If you are in an airplane and it's taking off, as it accelerates, as it speeds up, you feel yourself pushed back into the seat. You know that you are in motion. But if you're not accelerating, you don't feel the motion, and in fact, there is no way for you to detect the motion at all. So for instance, if you imagine that George and Gracie were in two floating laboratories out there in space, and they do experiments to work out the laws of physics, they will work out exactly the same laws because there will be absolutely no remnant, no experimental implication of their relative motion if that motion is at constant speed in a fixed direction. No way to determine your state of motion because you are justified in saying that you are at rest. Now that idea that you can claim to be at rest, that there's no implication of constant velocity motion, does not start with special relativity. It does not start with Albert Einstein. This is an idea actually that goes way, way back. It goes all the way back to Galileo. And Galileo wrote a wonderfully poetic description of this idea. Let me show you a little visual representation of what he said, and I'll just read his words to you while this plays. So he said, "Shut yourself up on a large ship, and there procure gnats, flies, and other small winged creatures. He said, let a bottle be hung up, which drop by drop lets forth its water into another narrow-necked bottle placed underneath. Then, with the ship lying still, observe how the winged animals fly with like velocity toward all parts of the room, how the distilling drops all fall into the bottle placed underneath. Then, he says, having observed all these particulars, make the ship move with whatever velocity you please." So here it is, the ship is going into motion, and he says that so long as the motion is uniform, by which he means constant velocity, you shall not be able to discern the least alteration in all the forenamed effects, nor can you gather by any of them whether the ship is moving or standing still. That is the very same idea, that constant velocity motion cannot be detected. It has no impact on your observations. Old idea, back with Galileo. So where then does Einstein come into this story? Einstein's new contribution is to say that among the four named effects that Galileo was talking about, he was just talking about the gnats and flies and the water dropping into the bottle placed underneath, that those things would not change if you go into motion so long as it's uniform. Einstein added something to the list. Einstein added to the list of things that would not change, he added the speed of light. This is the surprising new insight of Einstein. Let's see what it means. The speed of light is constant, right? That is one of the most famous sentences in all of science. The speed of light is constant. Now, what does it mean, and why should you care? Well, to get there, let's think about how it is that Einstein came to this idea that the speed of light is constant. It's an interesting history where, over the course of many centuries, many people struggle to understand light. And perhaps a good place to pick it up is in the 1600s to the 1800s, when a whole group of physicists spent a lot of time, put a lot of effort into trying to measure the speed of light, and they did a pretty good job. Romer, Huygens, Bradley, Fizeau, Foucault, these guys, some of whom had very long hair, made increasingly precise measurements of the speed of light. With modern updatings, we now know that the speed of light is 671 million miles per hour. If you like those units, it's 300 million meters per second, or a little bit more precisely, it's 299,792,458 meters per second. But we will round that off to 300 million meters per second for the most part. So that was good. People understood the speed of light. But even so, physicists lacked an understanding of what light actually was. And that's when two physicists, Michael Faraday and James Clerk Maxwell, who through experiments, mostly Faraday, through theorizing, mostly Maxwell, they realized something quite amazing. Because they studied electromagnetic waves. They studied ripples in an electromagnetic field and came to a stunning conclusion. So Maxwell did this mathematically based upon the experimental results of Faraday, and roughly speaking, what Maxwell ultimately concluded from the equations, from the math, was that an electromagnetic disturbance always travels at a particular speed, regardless of the wavelength, which is the distance between one crest and another. And remarkably, the speed that he found for electromagnetic waves, again, independent of whether they have a very long wavelength or if, for instance, they have a much shorter wavelength, like this fella coming in here, he found in the equations that the speed of those electromagnetic disturbances would always be equal to a particular number, and that number turned out to be 671 million miles per hour, or 300 million meters per second. So this was a stunning insight. And again, if you haven't studied electromagnetism, it doesn't matter. All that matters here is that Maxwell had these equations, and from the equations out came, from a calculation, a speed that was equal to the speed of light. What was Maxwell to conclude? Well, naturally, he said, if the speed of the electromagnetic disturbances is equal to the speed of light, then light itself must be an electromagnetic disturbance. It must be an electromagnetic wave. That was a great step forward. Now we had an understanding of what light actually is. But even with the progress that that represented, it still raised a profound mystery. And that mystery is this. As we described before, whenever you talk about speed, you need to say an object has this speed relative to that object. You need to state things in that manner for speed to even have any meaning, right? But when it comes to the equations that Maxwell was studying, they didn't specify what speed 671 million miles per hour was relative to, right? So if you have sound waves, the speed of sound is relative to the still air. If you've got water waves, the speed of the water wave is relative to the still water. What was the thing relative to the speed of light was being calculated? Nothing seemed apparent, so physicists dealt with this mystery by making up an answer. They said maybe there is something called the ether filling space, and when you talk about the speed of light, you're talking about the speed of this electromagnetic wave relative to the ether. Experiments were done to try to find the ether, and to make a long story short, no evidence for the ether whatsoever. So the puzzle remained. This is where the genius of Einstein comes into the story. Because Einstein had this uncanny ability to look at something that everybody else had been staring at and see it in a new way. And Einstein said, look, if the equations are saying that the speed of light is 671 million miles per hour, but the equations are not specifying what that speed is relative to, maybe that's because you don't need to specify anything. Einstein said the speed of light is 671 million miles per hour relative to anything, so long as it is traveling through empty space. Now, this is a strange idea. It is a maverick idea. You might say it's a crazy idea because we are unused to any speed that isn't relative. We are unused to any speed that, for instance, can't be changed by running toward it or away from it. But that is what Einstein was saying. So let me give you just a little visual example of what this constant speed of light, this fact that Einstein was saying that you don't need to specify the reference for the speed of light. It is just a number, a law of physics. Here is what that would imply. So imagine we have George and Gracie out there again. Gracie has a meter that can measure the speed of light. When she's standing still, George fires his laser beam, and she gets 300 million meters per second. But now let's change things just a little bit and imagine that Gracie runs away. You would think the speed should be less because she's running away, but no. Einstein would say it's still 300 million meters per second. It is a constant. It is a law of nature that the speed of light is that number relative to anything. Similarly, if Gracie were to run toward George, you'd think the speed would go up because she's running toward the oncoming laser beam. No, 300 million meters per second again. And the same thing would hold true if it's not Gracie that's running, but George. So the source, if the source is running, you'd think the speed should be a little bit bigger, 300 million meters per second, not 1 iota bigger. And similarly, if George were to be running away, you would think that the speed she should measure should be smaller than 300 million meters per second, but it remains, according to Einstein, the same fixed number, a constant, 300 million meters per second. Now, if this is true, right? This is Einstein's idea. If it's true, it's telling us, as we mentioned before, that speed has some very unusual properties when you're talking about speeds that are very fast, near the speed of light. 300 million meters per second or 671 million miles per hour is very fast, fast enough to go around the Earth 7 times in a single second. And what Einstein is saying, at those speeds, you begin to reveal a feature of nature that you would not anticipate based upon footballs or hand grenades or any of the ordinary objects of everyday experience. So if it's true, if speed has these weird features when you're talking about speeds near the speed of light, then that would mean that space and time, because speed, distance over duration, space over time, it would mean that space and time have weird features. That's why this is such a critical idea. But of course, the essential question is it right? Is the speed of light actually constant? In this section, we're going to take on a subject briefly that is not the most scintillating of subjects, but it's an important one, which is the question of units. What units should we use when we're doing actual mathematical calculations in special relativity? And that actually slightly shortchanges the subject, because one way into this little discussion is to think about for a moment a question that I have been asked many times over the years, which is, what is so special about the particular numerical value of the speed of light, right? We talk about 671 million miles per hour, 300 million meters per second, but why those numbers and not like, 400 million or 800 million? What selected of all possible numbers those particular values for the speed of light? And the answer to that question is there is nothing at all special about those particular numbers, because those numbers are completely dependent on the units that you choose. And we know that, right? Because if we look in units of, say, miles per hour, we've spoken about the speed being 671 million, but we've also noted, and perhaps you know yourself already, that if you use different units, like units where we take the time unit to be seconds, and we use, say, miles still for space, the speed of light is a different number, 186,000 miles per second. And if we use different units still, meters per second, we've noted that it's 300 million meters per second. The numbers in the right-hand column are all different. And as you can imagine, by choosing any particular units that you like to work in, you can make that number in the right-hand column anything that you want. So the key thing is, the only thing special about the speed of light is it's not zero and it's not infinity. It's a finite number. And once it's a finite number, then by changing the units, you can make it any value that you want. Now, there's something particularly useful about this idea, which is that from a practical standpoint, right, we're going to be doing a lot of calculations in special relativity, and we're going to find that the speed of light, c, crops up all over the place. And if you are using units in which the speed of light is a big number, that means you have to constantly, over and over again, do calculations with a big number. And there's a trick that allows us to alleviate that kind of headache of having to write and calculate with a big number over and over again. And that trick is this. We can carefully choose our units so that they're tailor-made, so that the value of the speed of light in those units is a very simple number. Now, what are the simple numbers? Well, the simplest number, the one that we love to work with, is the number 1, right? Can we make the speed of light 1 in particular units? And the answer is absolutely yes, right? So if we choose our time units to, say, be the year, and we choose our space units to be the light year, how far light travels in 1 year, then by definition, the speed of light in those units is 1 light year per year. The speed of light is numerically equal to 1 in those units. If you choose your time units to be seconds, you can play exactly the same game. Choose your space unit to be the light second. Now, the light second is the distance that light travels in 1 second. In familiar units, it's the numbers we were talking about before. But if you make use of those as your base units, then in them, the speed of light is 1 light second per second, by definition. Now, let me give you one other example where the speed of light becomes 1. This is just really an accident, historical accident, but it's a useful one, and it's one that we're going to make use of from time to time, which is this. If you choose your time units to be the nanosecond, 1/1000th of a second, then it turns out, you're going to do a little calculation to verify this, it turns out that light travels very nearly 1 foot in 1 nanosecond. It's not exactly right, but it's a pretty good approximation. We're going to use that approximation often. So if you choose your space units to be feet, this archaic unit that only us in America and a few other backward countries when it comes to units actually use, but in relativity, that actually turns out to be useful because in them, as I just mentioned, the speed of light is very nearly 1 foot per nanosecond. And what this means is if we use those units, it'll make for very easy arithmetic in our calculation. Either if we use light year per year, unit for the speed of light within which the value of the speed of light is 1, light second per second, again, numerical value of the speed of light in those units is 1, or 1 foot per nanosecond. And that is the way we're going to do our calculations. On occasion, we'll make use of 671 million miles per hour, those sorts of units, but it will make life much simpler if we choose our units so that the speed of light is 1, and that is what we'll often do. The constant speed of light certainly violates our intuition about how speeds behave, how speeds combine. But it also seems to violate basic mathematics of how you combine quantities, right? I mean, we're used to the fact that if, for instance, you are throwing an object, then if someone's running away, the way you get the speed is by subtracting. So we would expect that if the speed of light is c and you're running away from it, the mathematical way of combining your speed v with the speed of light would be to get c minus v. The basic mathematics, if you're running toward the light, we expect it to be c plus v. But these formulae can't be correct because the speed of light is constant. So a good question to ask is, how does special relativity modify this very basic mathematical way in which speeds should combine based upon any normal way of thinking about how quantities of that sort would be put together? And I'm going to now describe the answer to that question in special relativity. I'm not going to derive the new formula that's going to replace that formula on the board. I'm going to derive it later. But right now, I want to show you the formula because it helps alleviate a kind of misunderstanding, a little bit of a pitfall that sometimes people encounter in the subject, which is the thought that the new ideas of relativity only kick in when light is involved, only kick in when the speed of light is part of the problem. That is not true. The new ideas of relativity kick in at all speeds, but as we'll see, their effect at small speeds is small, so we don't notice them. And we can see that mathematically by looking at a couple of situations. So let's consider an example where, say, we have Gracie throwing a baseball. And let's say she throws it at velocity v, right? So we're used to the fact that if George now runs away at speed w, that it will approach him at v minus w. And of course, we're also used to the fact that if he runs toward the ball at speed w, it would approach him now at the higher speed of v plus w. So what is the new mathematical formula that special relativity gives us to replace the velocity combination formula that we are used to? So of course, we are used to saying that the speed of approach will be v minus w if George is running away. It'll be v plus w if he's running toward the ball. And special relativity replaces both of those in the following way. So the new equation looks like this. V minus w divided by 1 minus vw over c squared. New correction factor from special relativity that we will derive, but now I just want to show you what the result is. And this one is v plus w with a similar correction factor, 1 plus vw over c squared. So I want to say a few things about these formula, as they are a vital part of understanding how it is that special relativity modifies the basic equations that we are familiar with from Newtonian physics. So point number one that I want to make is that when v and w are much smaller than the speed of light, that's what that symbol means, much smaller than the speed of light, notice that this piece that we have in the denominator, 1 minus or 1 plus vw over c squared, if v and w are each very small compared to c, that's a small number, and that's a small number too, which means that these formula reduce to v minus w and v plus w when speeds are small. That is how we are assured that special relativity recovers Newtonian ideas at low velocities. But this correction factor is always there, even if it's small, nonetheless. OK, point number two surrounds what happens when, say, one of either v or w is the speed of light. So now no longer a baseball. Let's say a laser is involved. So let's look at what happens to c minus w. That turns into c minus w divided by 1 minus cw over c squared. And of course, that's very nice, because that is equal to c times 1 minus w over c divided by 1 minus, one of the c's cancels over here, w over c. These guys cancel, and we're left with c. In other words, when you run away from a beam of light, instead of its speed of approach going down to c minus w, its speed of approach goes to this value, which evaluates to the speed of light. Doesn't change it at all. Exactly what we need to have happen for the speed of light to be constant. And of course, the same thing happens for c plus w. That now goes over to c plus w divided by 1 plus cw over c squared. And indeed, everything cancels out, and you are left with the speed of light again. So here is a very nice example where we see directly how the new mathematics of special relativity ensures this strange fact of the speed of light being constant. Now, one other point worthy of emphasis here, I've written down these two formula as if they are somehow different formula. They're actually, of course, the same formula, because the only difference between running away and running toward is the sign of the speed. Our convention is positive speed is going that way, and so negative speed is going this way. And indeed, if you change the sign of w from running away, this is where it's a positive number. Make that a negative number. Minus a minus is a positive. Similarly, downstairs, this formula becomes that formula. So they really are the same equation. The other thing to bear in mind is that equation holds true regardless of whether it is the observer who's running toward or away or the source. So, for instance, were we to look at an example now where Gracie does the running, you would have thought that would yield a speed of approach of v plus w. No, it yields v plus w over 1 plus vw over c squared. And similarly, if Gracie is running away and throws that ball towards George, pay attention, oh, he wasn't looking, you would have thought that would have been v minus w, and that would have been better for George if it was, but it's v minus w over 1 minus vw over c squared. So that is the new way in which speeds combine in special relativity. That's the new formula. Again, we will derive this a little later in our discussions, but before we get to that point, it's a good idea to get a feel for these equations by playing around with them. So there are a couple of demos that we have to do that. So in this demonstration here, you say pick the speed of a rocket or a projectile. So let's say you choose the speed of a rocket that's firing a projectile. That's like Gracie throwing the baseball. And then notice as you vary the speed with which the projectile is launched from the rocket, the combined speed never gets bigger than the speed of light. And perhaps it's worth emphasizing in this equation here as well, you will never get a number that's bigger than the speed of light because the numerator will never be more than c times the denominator. And that you see directly happening here. So you should play around this to get a feel for the way the equations work. Another nice thing in this demonstration is if you click Show Newtonian, you can see in that dotted white line, if you focus in on this closely, here's what Newton would have said for the speed of a projectile being launched from a rocket. If the rocket's going fast and the projectile is going fast relative to the rocket, their combined speed, according to Newton, can be quite large, bigger than the speed of light. But this new formula turns the curve over, and it never does become bigger than the speed of light. And the other demo that is good to play with is just the reverse situation where you are varying the speed of the other object. So let me show you that over here. So in this demo, say you can pick the speed of the projectile, and then say vary the speed of the rocket. And again, the faster the rocket goes, the faster the combined speed of it and the projectile become. The rocket's going forward, it's firing that projectile, so you're going to watch the projectile go faster, but how much faster? If you were Newton, you would imagine situations where the combined speed again would become larger than the speed of light, but because of this new relativistic velocity combination law of special relativity, the combined speed never does become bigger than the speed of light. So that is the essential lesson of the velocity combination law according to special relativity. It ensures that the speed of light is always constant. It ensures that the combined speed of two objects never gets bigger than the speed of light. And it also is always present, but at low speeds, the impact of the correction from special relativity just hardly matters. That's why we don't notice it, but it's always there. We care about the speed of light being constant because speed, again, is a measure of space per time. So if speed does something weird, then that must mean, as we've emphasized already, that space and time must be doing something weird too. And in this section, we're going to describe one of the most startling implications of the constant nature of light speed, which is that there is no universal agreement on what things happen at the same time. That's where we're going. Now, to get there, let's start with the basic intuitive understanding of time, right? So over the course of many centuries, we humans have gotten pretty good at learning how to measure time. We have developed all sorts of clocks that through the ages have gotten better and better and better at measuring the time interval between one event and another with absolutely astounding accuracy. Now, having said that, we have still struggled for ages to really understand what time itself actually is. We don't yet have an answer to that question, but we do have certain basic understanding of the properties of time. For instance, we all agree that clocks that are properly functioning and properly set, all of those clocks will tick off time at the same rate, so they will all be in sync with one another. They will all agree with one another. We also generally agree that individuals that are measuring the duration of an event with properly functioning clocks will get the same answer. We all agree on how long it takes for something to happen, and we all agree, generally speaking, on what things happen at the same moment, right? Those are the basic features of time as we experience time in everyday life. Here is the thing. The constant nature of light speed says that all of that is wrong. It tells us that properly functioning, properly set clocks do not generally agree with one another. It tells us that we generally do not all agree on what happens at the same moment in time, and we generally will not all agree on how long it takes for something to happen. Now, those are some pretty striking claims. I'm not going to describe all of them right now, but we're going to take on one of them. Want to describe how it is that the constant nature of light speed ensures that different perspectives of individuals that are moving relative to each other will not agree on what events happen at the same time. And to do that, I'm going to frame it in the context of a little story. The story goes like this. Imagine that there are two warring nations, forward land and backward land, and they've just come to an agreement. They're ready to sign a treaty, except each president stipulates that he does not want to sign the treaty before the other. So the Secretary General of the United Nations needs to come up with a plan that convinces them that in the procedure that they are going to use, each president will sign at the same moment. Here's the procedure that the Secretary General comes up with. He says, look, we're going to have you both sit at opposite ends of a table. We're going to put a light bulb in the middle. We'll turn on the light bulb. When the light reaches your eye, you sign the treaty. You're equidistant from the bulb, and therefore it should take the same amount of time for the light to reach you. You should sign simultaneously. So here is the setup. The light goes off. The flash goes toward each of the two presidents, hits them, and they sign the treaty, and they are all very, very happy. Good. Now, they are all very happy that this agreement has been reached, and a few months later, they come to another agreement that they want to sign at the same moment, except this time both presidents want to do it a little differently. Even though they have many, many differences, each of the presidents of forward land and backward land, they both have a deep love of trains. So they want to do the treaty signing ceremony on a train that is going right across the border between forward land and backward land. So they set up the same scenario, and here they are on the train. Train is going along. There is a table again in one of the cars. The presidents are equidistant on the train from the bulb. The bulb will be turned on, just as in the previous case, and when each president sees the light, he will sign the treaty. Okay, so here we go. The bulb goes off, the light flashes, goes toward each of the presidents, and they sign the treaty, and everybody on the train is again very, very happy with the result. But here's the thing. Just after they sign the treaty, word comes that the people on the platform are fighting. They're fighting because those folks from Forwardland claim that they have been duped. They claim that their president from Forwardland signed the treaty first. How could they come to that conclusion? Well, here's how it goes. So the people from Forwardland, they are on the platform watching this happen. And from their perspective, look what happens. When the flash goes off, the president of Backwardland is moving away from the flash from their perspective, so it takes longer to reach him than the president of Forwardland, who's moving toward the flash. So let me show you that again. Watch what happens when the flash goes off. The president of Forwardland moves toward the flash. President of Backwardland moves away from the flash. The light has to travel further to reach the president of Backwardland than the president of Forwardland. It has the same speed. The speed of light is constant. So if it has to travel further, it's going to take longer to get there from the perspective of those people watching on the platform. And therefore, they claim that the two presidents did not sign at the same moment. They claim that the president of Forwardland signed the treaty first. Let me show you one more variation on that so you can really see the detail of what's going on. This time I'm going to draw a line where the flash takes place. There's where the flash took place. Look how far the light has to travel to reach the president of Forwardland versus Backwardland. It only has to travel this distance to reach Forwardland. It has to travel this distance to reach the president of Backwardland. Light travels at the same speed. If it has to travel further, it's going to take longer to get there. So we now have an interesting situation. Those people on the train are absolutely convinced that the two presidents signed at the same moment. Those people on the platform are just as convinced that they did not sign at the same moment. So the big question is, who is right and who is wrong? And the answer is, they are both right. The reasoning of each group of individuals is absolutely impeccable. For those on the train, the presidents are equidistant from the bulb. Bulb lights up. The light travels the same distance to each, so they sign at the same moment. Perfect reasoning. Those on the platform, they say the flash goes off, and it doesn't have to travel as far to president of Forwardland as it does to the president of Backwardland. Speed of light is constant, and therefore they do not get the flash at the same moment. That reasoning is absolutely impeccable. So what this is telling us is that the constant nature of the speed of light means that events which take place at the same time from the perspective of one group of individuals will not take place at the same time from the perspective of another group of individuals moving with respect to them. Now, this relies, of course, on the constant speed of light, because what Newton would have said is he would say the projectile, say the light, will get an additional kick from the train moving in this direction, and that additional speed will allow it to cover this distance in the same amount of time. The light going this way would have its speed diminished, and therefore it's traveling a shorter distance. And when you take those two effects into account, Newton would say both of the presidents get hit at the same time, regardless of your vantage point. But because of the constancy of the speed of light, we come to a very different conclusion. This is what's known as the relativity of simultaneity, and is one of the most startling implications of the constant nature of light speed. I want to now briefly focus on a pitfall that I've seen many people encounter when they are first studying relativity, which has to do with the relationship between what you observe, what you see, and what actually happened to be responsible for what you see. You see, those two things are generally not the same. There is a difference between what you see and experience and what actually happens. Let me give you a real quick example of that. Imagine you head off to a baseball game, and you know, baseball tickets are a little expensive, so you decide to sit in the cheap seats, right? So you're out there in the bleachers, and you're watching the game, and there's a common experience that anybody who sits in the bleachers always has, which is this. You watch the pitcher's ultimately going to throw the ball to the batter, but I want you to compare when you see the batter hit the ball versus when you hear it, right? Let's watch this. See the difference, right? So you saw the ball being hit by the bat before you heard it being hit, and the reason for that is straightforward. It takes longer for the sound to travel to your ear than it takes for the light to travel to your eye. And therefore, if you're naive, if you're not thinking things through, you might come to the conclusion that the process that produced the light that you're seeing happened at a different moment from the sound that you're hearing, because after all, you are experiencing them at different moments. But of course, that's not right. We all know what's going on here. What's going on here is you need to distinguish between what you perceive and what actually happened. Of course, the ball, sound, and the light from the ball were produced at the same moment. They're all produced by the bat hitting the ball. It's just your perception is leading you to a perhaps erroneous conclusion unless you're smart about it, unless you recognize that you must use what you see and experience to figure out what happened. You can't just go by your raw perception, right? Let me give you another example. This one not with sound and light, but this one with light and light, right? So imagine that we have a situation where our fearless friend George is looking at two firecrackers. They go off at the same moment, travels, and hits his eye at the same moment. So he sees them explode at the same moment and therefore concludes that they explode at the same moment. Good, but now let's compare this with the following situation where, again, from our stationary perspective, from his perspective, the firecrackers go off at the same moment, but since he's closer to one, he sees the light from that one first, he sees the light from the other explosion second. So if he weren't thinking things through, right, George might conclude that the firecrackers went off at different moments because he sees the flash of light at different moments. But of course, he needs to post-process his observations to take into account the light travel time to reach his eyes. And when he does that, if he does the calculation correctly, he will correctly conclude that the firecrackers actually went off at the same moment. Let me give you one other example. So here's one where the firecrackers, from his view, go off at different moments. Notice that the one on that side goes off first, that second. Boom, they hit his eye at the same moment. So again, if he were naive, he would conclude that they went off at the same moment because he sees them at the same moment. But that's wrong. He has to post-process his observations to figure out what actually happened. And when he does that, he will rightly conclude that it was the firecracker to his left that went off first, allowing it the additional travel time to reach his eye because it's farther away. They did not go off at the same moment, even though he saw them at the same moment. So the reason I'm bringing this up is because in the example that we looked at, this treaty signing ceremony, I used some pretty loose language, right? I spoke about what observers on the train see and what observers on the platform see. And that's loose because I would really need to specify which observer on the train, which observer on the platform, how far away they are from the two presidents, and so forth. And I don't want to get into all of those details, nor do I want you to be confused into thinking that those details have any impact whatsoever on our conclusion. Because the bottom line is, what I was really referring to when I was using that loose language was what the observers figure out regarding what happened. I am assuming that the observers are smart, right? I'm assuming that they post-process whatever they see to figure out what actually happened. And indeed, in this particular case with the treaty signing ceremony, the individuals on the train and on the platform, they don't actually need to literally see anything at all. They can just think it through, right? Let's do it. Let's do it together, right? So if you are on the train, your reasoning again is two presidents equidistant from the light bulb, light travels the same distance, therefore they will receive the light simultaneously. Perfectly valid, sharp, correct reasoning. Now, imagine you are on the platform. Let's think it through without even any literal observations. From the platform perspective, they hear about the procedure of the treaty signing ceremony. Immediately, they conclude it's not fair. Why? They say, President of backward land is rushing away from the light. It has to travel further to reach him. Same speed will reach him after it reaches the president of forward land. Nothing to do with what they literally see. Rather, they're using their knowledge to figure out what actually would happen if they watched this treaty signing ceremony take place. So the upshot is that we really need to distinguish between two important ideas: to observe something versus to measure something. And when I use more precise language, which I'll try to use when it matters, when we talk about measuring something, what I mean is to figure out what actually happened, to figure out reality, that is, based upon your observations or your knowledge, plus, and this is the key thing, plus post-processing, to take your observations, whether it's your observations in this case of firecrackers, or whether it's your observations on the train, the treaty signing ceremony, to use your observations to post-process and figure out what actually happened. So in the example that we studied, where we have the two gentlemen on the train, from the train perspective, getting the light beam at the same moment, and from the platform perspective, they don't get it at the same moment. This is with post-processing. This is actually figuring out how reality works. This is not a matter of perception. So the bottom line then is we've concluded that after post-processing your observations, after doing what needs to be done to figure out that the baseball and the bat are described correctly by saying that the impact produces the sound and the light at the same moment, when you post-process to figure out that the firecrackers went off at the same moment, even if perhaps George sees one before the other, after you do that post-processing, you conclude that two events that are simultaneous for me will generally not be simultaneous for you if we are in relative motion. This is reality. This is not a matter of perception. That's the key thing to bear in mind. We are talking about how the world works, not merely some optical illusion that is fooling us. Reality is such that things that happen at the same time from one person's perspective do not happen at the same moment from another perspective if they are in relative motion. All right, let's get down to business, mathematical business, and let's do a calculation. Let's calculate the time difference from the perspective of one set of observers when certain events happen versus the perspective of another. And in particular, let's make use of the example that we've been focusing upon, this treaty signing ceremony on a train. Again, the scenario itself is not important. What is important is we've got two sets of observers. Those on the train say the events happen at the same time. Those on the platform say that these events did not happen at the same time. And I want to now calculate the lack of simultaneity from the perspective of those folks on the platform. Okay, let's see how this goes. And it's a pretty straightforward calculation. Let's set it up in picture form so that we know what we're doing. So let's imagine that this is a schematic representation of the train. And on there we've got the president from forward land, we've got the president from backwardland. And the story, as you now know quite well, is that there is this light bulb in the middle between them that sends out the beam of light heading off in both directions. So let's just put the light is headed this way and the light is headed that way, of course, at the speed of light. And then on top of this, the key thing is that the train itself is in motion. So let's say this guy is moving over to the right. Let's call that speed equal to v. OK, so what I want to now calculate is, from the perspective of those on the platform, what is the time, say, tb, and the time tf for the light that's traveling toward each of those presidents? How long does it take from the platform perspective to reach each of those presidents? Well, that's easy for us to work out. How does it go? From the perspective of the platform, how far does the light need to travel to reach the president from backwardland? Well, at first you'd say that if the folks on the platform say that the length of the train, let's call this length, and they find that the length of that train is, say, equal to L, then from their view, the light has to travel L over 2 to reach the president of backwardland. So the distance it needs to travel is L over 2. But that's not quite the end of the story, right? Because as the ball of light is in transit, we know that this train is sliding over. It's moving, after all. So in a time equal to tb, how much does it move over? It moves over an amount v times tb, which means the distance, according to the platform folks, for the light to reach the president from backwardland, that is the distance that the light needs to travel. How long does it take? Well, we know that if you take c times tb, velocity times time, that's how far the light can travel in a time tb. And for it to hit the president of backwardland, it had better cover that distance. So this must be equal to L over 2 plus v times tb. And now that's a little equation that we can solve. Bring vtb over to the other side. So we have c minus v times tb is equal to L over 2. And therefore, tb, solving for it, is L over 2 times c minus v. So that's how long it takes, from the perspective of those on the platform, for the light to travel from here all the way to reach the president of backwardland. Good. What about the time it takes the light to go the other way and hit the president of forwardland? How far does it need to travel to reach that president? So this is to backwardland. To forwardland, it needs to travel, well, you initially would say L over 2. But of course, as time elapses, the train is moving over to the right. How far will it move in time tf? Well, again, it's just velocity times time times tf. And therefore, the light doesn't have to travel as far by an amount v times tf. And therefore, the corresponding equation over here is velocity of light, the speed of light, times the time it reaches to the president must be equal to the distance it travels, which is L over 2 minus v times tf. And therefore, playing the same game, bringing the v to the other side, we have c plus v times tf equals L over 2. And therefore, tf is equal to L over 2 times c plus v. Different answer. That just reflects what we've already established, that the two presidents do not receive the light at the same time. But now we just want to go a little further and calculate the time difference. So let's calculate the difference between when the president of backwardland gets the light and when the president of forwardland gets it. And we have everything that we need. So we have L over 2 times c minus v minus L over 2 times c plus v. And let's simplify that a little bit, put everything over a common denominator. So we have L over 2 times, let's put it all over c minus v times c plus v. c minus v times c plus v. And then upstairs, what we will get is we have a c plus v from the first term, and then we have a minus c minus v from the second term to make that all equal to one another. And what we have upstairs, therefore, is, notice that the c's cancel against each other. The v with the minus v has a minus sign in front, so that gives us 2v. We have an L out front, and that's all over 2 times. Now, c minus v times c plus v downstairs, you'll recognize that as c squared minus v squared. And canceling out the factors of 2, we have our answer, which is v times L divided by c squared minus v squared. So that is the answer that we were looking for, and that's worthy of boxing that guy up. This is a formula that we will use pretty frequently in our calculations because, of course, in situations without a train, the notion will still arise that folks that are a distance L apart from our perspective, their notion of simultaneity will differ from ours, and we want to know by how much, regardless of the scenario, and that is the answer. Now let me, as long as we have these equations on the board, let me just point out one more thing to you. How would this calculation have changed if we were working in, say, a Newtonian perspective, not a correct relativistic one? What would Isaac Newton say would be going on here? How would the calculation change? Well, you see, what Newton would have said is the speed of the projectile, the speed of light, he would say it is increased when it's moving to the right because the train kicks it. How much would he say this is increased by? Newton would say this is not c. He'd say this should be c plus v because it's getting a kick from the train. Newton would say that, similarly, the speed of the projectile headed this way would be diminished because the train, the source, is moving in the opposite direction. And he would say this guy should be c minus v. Now, notice what happens. The v over here times tb, vtb, would be on both sides of the equation. It would cancel out. The speed of the train would be irrelevant to the calculation. Similarly over here, minus v times tf, minus v times tf, cancel from both sides. Again, irrelevant to the calculation. And that's why, from a Newtonian perspective, there is no relativity of simultaneity. There is no notion that different observers in relative motion don't agree on what happens at the same time because of the little modification to the calculation that we just did. So Newton would say no time difference at all, but Einstein, in the manner that we just described, says that there is a time difference. So let's just record our answer up here for clarity. We have found that the time difference between when the light reaches the two presidents, that is the time difference in the notion of simultaneity between those on the train and those on the platform, is given by LV over c squared minus v squared. Now, there are a couple key features of this formula that are worth emphasizing. Both are relatively intuitive, but it's good to spell them out. The larger the speed of the train, the larger the speed of one frame of reference relative to another, the larger the time difference becomes, right? You've got a v upstairs in the formula. The bigger that is, the bigger the effect is. Also, the bigger v is upstairs, bear in mind that this denominator, as v approaches c, this denominator gets small, so that also increases the effect as well. The other thing is, the larger the train is, that is, the greater the separation between the two folks in the moving frame of reference, the larger the lack of simultaneity from the platform perspective as well. That also is in here, right? So you've got this factor of L in this formula. The larger L is, the bigger the time difference from those on the platform relative to the folks on the train, saying that things happen at the same time. Now, formulas, of course, can be a little bit abstract. Let's plug in some numbers here to see what this turns into. So let's, for an example, imagine we're dealing with a train that is 10,000 meters long. That's a long train, but I want these effects to be a little bit more prominent so you can get a feel for it. And let's imagine that the velocity of the train varies from 100 meters per second all the way up to very close to the speed of light at the bottom. All I'm going to do right now is plug into the formula. You could do this at home if you would like. At 100 meters per second, that's a time difference. It's small. At 10,000, well, it's getting bigger, but it's still pretty small. At 1,000,000 meters per second, well, time difference is still pretty small. 100 million, it's starting to creep up there, but it's still a tiny fraction of a second. 200 million meters per second, right? That is really fast, but still the time difference has got a bunch of zeros after the decimal point. But just to show you that this effect is real and can make a difference, let's look at this guy over here. So in this rare case, I'm actually using the precise measure of the speed of light, not 300 million meters per second, but 299,792,458 meters per second is the speed of light. And I'm getting really close to that with all those nines after the decimal point. Plug that into the formula, and you will find that the time difference between when the president of forwardland and backwardland receive the light that those on the train say is simultaneous jumps to 83 minutes. 83 minutes. So according to those on the platform, president of forwardland and backwardland signed the treaty 83 minutes apart, even though everybody on the train says that they signed it at the same moment. OK, let me give you a little demo of this that you can play with on your own to get a feel for the lack of simultaneity from the perspective of those who are on the platform relative to those who are moving, say, on a train. Here it is. So what you do here is you pick the speed of the train. You then can pick the length of the train as measured by platform observers, and feel free to use meters or feet. And as you change the speed of the train, notice what happens. So here's the thing. At very low speeds, tiny, tiny time difference. Speed creeps up. Half the speed of light. It's still pretty small. Here we are at 90% of the speed of light. It's only starting to become a larger number. Still, it's pretty small. But it only kicks in a significant way over here. Only as we get really close to the speed of light does it start to kick up. That's why it took the genius of Einstein to figure this out. We live over here. The scales that we experience are over here. The effect is real but tiny. It's only when the speed of the train gets very close to the speed of light that this little formula that we have over here, only when v and c are very close to each other will this thing crank up to be a big number. But the point is, you can make that number as big as you want. You can make the relativity of simultaneity as large as you want by making the speed of the moving observers, the moving folks, in this case on the train. If their speed gets very close to the speed of light, you can make the relativity of simultaneity as big as you want. OK, those are the essential ideas that allow us now to understand quantitatively the time difference between events that we say on the train happen at the same moment, but those folks on the platform say happen at a different moment. The relativity of simultaneity strongly hints, in fact, almost necessarily requires, that motion, speed, must be affecting time itself. The rate at which time passes must be affected by motion. That's the only way that we really can conclude, as we have already, that simultaneity depends upon your perspective. I mean, in the treaty signing ceremony, if clocks on board the train agreed with clocks on the platform, then everyone would agree on what happens at a given moment. Everyone would agree on whether the president signed at the same moment. But they don't agree. And so clocks that are moving relative to each other must tick off time differently. Now, for us to make that idea precise, to us to really understand how it is that motion affects the passage of time, we need a way of measuring the passage of time. We need, of course, a clock, right? Now, you can use, for all that we are talking about here in relativity, you should feel free to use any clock that you like, right? Your favorite Rolex, your favorite grandfather clock, any clock that you'd like to use. I, however, am going to make use of a special kind of clock that's quite unfamiliar, but as you will see, it's a very powerful kind of clock for assessing the effect of motion on time. So I should spend just a moment addressing the issue of what is a clock, right? So what is a clock? A clock is any physical system that undergoes cyclical repetitive motion, and it does that cyclical motion. It undergoes those cycles in a uniform way, right? So if you're talking about using the Earth as a clock, the Earth spins around its axis in a uniform way, and we use that to say every time it goes around once, that's a day. We can talk about the Earth in revolution around the sun, right? It does that in a fairly uniform cyclical way, and we call each revolution a year. And on a more standard wristwatch, if you have, well, I should say one of the old-fashioned ones that has a second hand that's sweeping around, it does that sweeping motion cyclically, sweep after sweep after sweep, and we call each of those sweeps a minute, right? So that is what a clock is, conceptually. The new kind of clock that I'm going to introduce has that same kind of feature. Cyclical motion, a cyclical process happens over and over again, but the process itself is a little unfamiliar, because the kind of clock that I'm talking about is called a light clock. What is a light clock? A light clock is a contraption in which we have two mirrors that are facing one another, and a ball of light will bounce in between them. And every time the ball goes up and down, you can think of that as tick-tock, right? Tick-tock. The ball is just going up and down. So let me show you a quick visual of this kind of clock, this light clock. There it is. So every time it's going up and down, so let's do it. So it goes tick-tock, tick-tock. It's regular cyclical motion that you could use to measure how much time elapses between one event or another. The reading is up there at the top of this light clock. And what I want to stress at the outset is that this light clock, however unfamiliar it is, right? It is unfamiliar. You cannot go down to Walmart and buy one of these light clocks. But conceptually, a light clock is no different from any other kind of clock, which means any conclusion that we reach about the nature of time that makes use of this light clock as an intermediate part of the reasoning, that conclusion applies to any clock. It would just be harder to reach that conclusion with a clock that had a more complicated internal mechanism. Because, as I'll show you in a moment, the beauty of the light clock is that because the mechanism, the tick-tock mechanism, is so simple, we can very easily determine the effect of motion on the passage of time. Okay, so to do that, I'm going to want to introduce a second one of these light clocks, because I'm going to want to compare the rate at which time elapses on one compared with the other, not when they are stationary, as they are here, but I'm going to want to set one of them into motion. Actually, before I do that, let me tell you what you're going to see, just to prepare you, because this is a great, wonderful result that we're going to find, and I want you to be fully prepared for when it comes. Imagine in your mind that I have one of these light clocks, okay? And I'm going to walk with it. Now it's in motion. From your perspective, think about the trajectory that the light will travel, right? From your perspective, the light will start here, it hits the top of the mirror here, and then it hits the bottom mirror here. So from your perspective, the light will have undergone a diagonal up and a diagonal down trajectory as I'm walking with the light clock. So I'll show you this in a moment, but let me just address one quick question. First, you might think, well, if you're walking with this light clock with the two mirrors, won't the ball of light sort of miss the top mirror because you're moving as you're going along? Answer, absolutely not. What's the argument? The argument is simply this. from my perspective, okay, I'm undergoing constant velocity motion, right? Same speed in a fixed direction, which means, from my view, I can say that I am stationary, and it's you and the rest of the world that are rushing by me. And therefore, from my perspective, it has to be that the ball of light just goes up and down and up and down. Because in my view, I'm not moving. So the ball of light has to hit the top mirror. And if it hits the top mirror from my view, it has to hit the top mirror from your view too. The ball of light cannot, therefore, fly out into space. So what, therefore, would happen is this. Let's put these two clocks over to the side, and let's look at that ball of light undergoing its motion in the moving clock. Diagonal trajectory up and down. Now notice something. The amount of time that passes on the two clocks is different. Why is that? Well, think about it. Look at the trajectory of the light in the moving clock. Because it's a double diagonal going up and down on the diagonal, the trajectory that it follows for it to go tick and tock, and let me show you this in slow-mo, the trajectory that it follows to go tick and tock is longer, right? So let's take a look at that. Set these guys into motion. This guy has already gone up and down. He registers 1. This guy, because he's going on a longer trajectory from your perspective, and yet the speed of light is constant, longer trajectory, it's going to take it longer to get there, which means this guy's gone tick-tock. This guy has yet to reach the top of the mirror. So if we let this guy continue on, then notice that this guy is reached 2. This guy is just bouncing off the bottom. He's far away from reaching 2. Let him keep on going, and so on and so forth. You see that the rate at which you've got time elapsing on the moving clock is slower than the rate at which time elapses on your stationary clock. And it all comes down to the speed of light being constant. The perspective, that is, from the laboratory observers, those folks who are watching the moving clock rush by, they see that the ball of light in the moving clock is still bouncing up and down between the two mirrors, but from the perspective of those of us in the laboratory, the trajectory which the light needs to follow to go tick-tock in the moving clock, the trajectory, the path is longer because it's going along this double diagonal trajectory from our perspective. And if the path is longer, but the speed of light is the same, that means that the tick-tocks happen at a slower rate in the moving clock. Our clock's going tick-tock, tick-tock. The moving clock is going tick-tock, tick-tock. Time itself is elapsing slower on the moving clock. So this is this wonderfully amazing idea that we have now established with this light clock, that from the perspective of those in the laboratory watching a moving clock, they will conclude that time runs slowly on that moving clock. And again, I've used the light clock as a tool, as an intermediate step, because as we just saw, I can easily see the effect of motion on the passage of time. The same would be true if I used any other clock, a Rolex, a grandfather clock, because what we're talking about is how motion affects time itself. And the conclusion is that from our stationary perspective, a clock that's in motion will tick off time at a slower rate. We now know that time elapses more slowly on a clock that is moving relative to you. And we're going to shortly calculate the rate at which that moving clock ticks off time compared to your clock. But first, I want to address two vital questions to this issue of the slowing of time. And the first is, if you are moving with that moving clock and someone on the platform watching you says that your clock is ticking off time more slowly, do you feel that time is elapsing more slowly? And the answer to that is Absolutely no, you don't, because again, it goes back to that very same point that I stressed at the outset, right? When we had, say, George and Gracie out there in space. So they're out there in space and they were passing each other, and I emphasized that each could claim to be at rest and that the other is moving by them, right? So that very same idea here, we're only talking about constant velocity motion, fixed speed in a fixed direction. That tells us that the person that you see moving with that moving clock, that person can claim that they are at rest, and it's you that's moving. So from their perspective, time is elapsing as it always does. If you will, the light clock relative to them is going up and down, just as it always does. You and the rest of the world are rushing by them. So, bottom line is, nobody actually feels internally that time is ticking off more slowly because of the fact that everybody can claim to be the person, the clock, at rest. Okay, now, that being said, if indeed you are watching a clock that relative to you is moving, you should see that time on it is elapsing more slowly if you're not moving with that clock. So the question then is, why don't we ever notice that time ticks off slowly on a clock that's moving relative to us? Why did it take the genius of Einstein to figure this out? Why don't we know this in our bones? Why don't we experience this in everyday life? And the answer to that is the same answer that we've come to in analogous questions that we've encountered earlier. It all has to do with the fact that everyday experience only taps into a small little part of how the world is configured. And in this particular case, everyday experience does not involve us watching objects that attain speeds near the speed of light, which is where these effects kick in maximally. So let me just give you a little demonstration where you can see that idea in action. So this here is, if you will, your very own light clock that you can play with on your own. And what you do with this light clock is you set the velocity of the clock at whatever value you want, and it's all in fractions of the speed of light. Good. Okay. Now, if you set the speed of the clock to be relatively small, non-zero but relatively small, let's look at the rate of ticking on that clock compared to what it would be doing if the clock were not moving at all. And notice that the diagonal path here has hardly any diagonal to it at all, because the speed of the clock is so slow compared to the speed of light that light goes up and down with virtually no ability for the clock to move to the right during any of the tick-tocks. So the motion of the clock has very little effect on the passage of time when the speeds are slow. But when the speeds pick up, let's do another version of this. Let's put the speed, I don't know, 60% or so of the speed of light. Now, the clock can move significantly between each tick-tock because it's going quickly. It's going at a speed on par with the speed of light, half the speed of light, a little bit more. And now the diagonals truly are longer than the straight up and down. And just to emphasize that point maximally in this little demonstration, again, play with this. Here we are at 99.9% of the speed of light. So if I now turn this fella on here, wow, look at that. Look how far. It didn't even get to do its first tick of tick-tock. That's how fast this clock was moving relative to the speed of light. So whereas when it's stationary, it would go tick-tock, this one went tick. Didn't even get to the k of tick. That's how far this clock moved to the left because of its very high speed. So this clearly shows us that, again, it is the speed of the clock which determines the rate at which time on it will tick off more slowly than on a clock that is stationary. That's the key point. But we want to go further, because ultimately what we really want to do is to derive a formula for how much slower time ticks off on a moving clock compared to a stationary one. And I'll derive that mathematically for those of you who are taking the math version of this course in the next section. But let me give you the essential idea here. And what is the essential idea? Well, the essential idea can be gotten by a little bit of analysis on one of these moving light clocks. So here is our little schematic version of a light clock that's in motion. And if you think about the process of going tick-tock, based on what we've described in that little demonstration that we just did, the key thing to think about in order to know how quickly this clock will go tick-tock is to look at the length of the trajectory. So the light, little photon, if you will, starts here, and in order to go tick, it has to travel that journey, and to go tock, it has to travel that journey. And since the speed of light is constant, what is most relevant here is how long that journey is relative to how long that journey would be for the stationary clock. And for the stationary clock, it just goes up and down. So if I just mark that for good measure, let's give that guy a different color. Let's call this guy blue. So if this length over here is, say, equal to L, and this length over here is equal to D, then this one will be D as well. So this guy, to go tick-tock, the stationary one, it goes up and down. So it goes L plus L. It goes 2L to go tick-tock on the stationary clock. And on the moving, to go tick-tock, it's D plus D equals 2D. Now, again, since the speed of light is constant, this is telling us that the duration for each tick-tock on the moving clock, let's compare that with the duration for this guy to go tick-tock on the stationary. So that's the duration of tick-tock on the moving compared to the duration for tick-tock on the stationary clock. Well, that ratio is just the ratio of the distances, because the speed of light is the same. So that's 2D over 2L, which is D over L. So that is the essence of the issue. Tick-tock on the moving clock compared to tick-tock on the stationary clock is the ratio of the length of the trajectory in the moving clock from our perspective watching it compared to the length of the trajectory on the stationary clock. So that is the key formula describing the rate at which the tick-tocks happen on the two clocks. But now let me just take this a little bit further and note the following point, which easily can get confusing. It's a very simple point, so if ever you find yourself confused in this, calm down, take a deep breath, think it through, and you'll be able to work it out, which is this. If you're considering the amount of time that elapses between two events, right? If you're measuring the elapsed time between two events on any clock, but in particular on a light clock, you want to know the number of tick-tocks. That tells you how much time has gone by. Now, if the duration for each tick-tock is longer, then less time will elapse on that clock. Longer tick-tocks, tick-tock, means less time will elapse. So what that means is, if we are looking at not the duration of tick-tocks, but the elapsed time, so the elapsed time on, and I'll fill in which clock in a minute, divided by the elapsed time here, and I'll fill in the clocks right now. So if the duration of the tick-tock on a moving clock compared to the duration of tick-tock on a stationary clock, let's say this is a ratio of 5:1. That means that 5 times more time will elapse on the stationary clock, where the tick-tocks are faster, compared to the amount of time that elapses on the moving clock. So then this translates into the elapsed time on the stationary clock compared to the elapsed time on the moving. These are inversely related to the duration of the tick-tocks. This is equal to D over L. So again, if this length here is 5 times the length for the ball to go up and down, the ball of light to go up and down in the stationary clock, then that means the tick-tocks are happening 5 times as slow in the moving clock, which means 5 times more time will elapse on the stationary clock compared to the moving clock, because the tick-tocks are happening faster over here. So that means that we can now take the little formula that we have indicated over here and translate that into the elapsed time in the stationary clock to the elapsed time in the moving clock is the ratio of the length of that diagonal that we have over here to the length of the straight up and down. So now we've basically reduced the calculation of how much time slows on the moving clock compared to a stationary clock to really a bit of geometry and trigonometry. And I'll show you how that goes if you're taking the math version in the next section, but let me give you the answer. Here is the answer that we will establish. If this clock that we are looking at over here, let's say this guy has a velocity that's heading over this way, and this velocity is equal to v, then that formula takes the speed v as input and tells us how much slower time elapses on the moving clock compared to the stationary clock. Now, for those not taking the math version of this course, this is one of only 2 equations I'm going to show you. The other, of course, being E equals mc squared. But this formula is just as important as E equals mc squared, not quite as famous, but it tells us that the time that elapses on a moving clock is slow relative to that on a stationary clock by a factor of 1 over the square root of 1 minus v over c squared. This expression, this little formula, is so important, we give it its own name. We call it gamma. Again, we'll derive that in the next section, but I just want you to get a bit of a feel for this result before we do that. We are going to look at 2 clocks, and one clock you can imagine is here on Earth, which we will call the stationary one. One clock is on a rocket ship, so now we've gone from a train to a rocket ship, because we want some of these speeds to be able to be really fast. And what this demonstration will do, it simply takes the formula that I have told you that we will derive in just a moment. So just remember what that formula is. So this is equal to, we claim, 1 over the square root of 1 minus v over c squared. The demonstration will take the v that you input into the demonstration, calculate that, and show us the amount of time that elapses on the rocket compared to the amount of time that elapses on Earth. OK, let's do that. All right, so let's be conservative at first. I've chosen the speed of the rocket ship to be 12% of the speed of light. Set this guy in motion, and you can begin to see a bit of a time difference between them. It's hard to see, but there is a bit of a difference. But now let's crank this up, and let's go to 66, 67% of the speed of light. And now you really can begin to see that the elapsed time on the rocket ship is less from the perspective of those of us here on Earth looking at our stationary clock. And let's then be inspired, and you should do this on your own, again, to feel the formula, this formula for this object called gamma in your bones. I'm now at 95, I don't know, let me push it all the way. Let's go to 98.5% of the speed of light. And now you really begin to see the difference between these two. It's dramatic. Here we are on Earth, and hour after hour is going by in the usual way. But from our view, that clock in motion, time is ticking off very, very slowly. So this factor, this guy called gamma, this time dilation, as we call it, kicks in substantially for speeds near the speed of light. At everyday speeds, time dilation is still there, right? So this guy over here, where the velocity is in the denominator, that kicks in at any velocity, right? But that number is so close to 1 for pedestrian everyday speeds that we don't notice it. So clocks move around the world all the time. we don't notice that they're ticking off time at a different rate, only because that formula is such that gamma is very, very close to 1. So the ratio of time on the moving clock to time on the stationary is virtually indistinguishable from being equal to one another. But the effect is there nevertheless. Having said that, let me just emphasize one little loophole that we will come back to. It's kind of a curious loophole, which is that if you have individuals that are moving at relatively slow speeds, but they're very, very, very far apart, then that can amplify this effect. So there can be big differences in time, even at slow speeds, if you're talking about observers that are very far apart in space. We will come back to that and its curious implications as we go forward. But putting that to the side, if you're talking about observers that are reasonable distances apart, distances that might be planetary scales or even galactic scales, it's only when they're moving relative to one another very quickly that this time dilation effect kicks in substantially. But it is there all the time. So in some sense, we all carry our own time. This completely shatters the oneness of time that Newton envisioned, right? Newton envisioned that there's one clock out there in the cosmos ticking off second after second after second, the same for all of us. This shows directly that that's not true. We each carry our own clock, and our clock ticks off time at a rate compared to others that depends on the relative speed between us. Let's now work out the mathematical formula for the rate at which time slows on a moving clock. Again, just to get us on the same page, what's the essential idea? What we have seen is that the elapsed time on the moving clock differs from the elapsed time on a stationary clock. That just comes from considering the lengths of the paths that the light takes in each of those clocks to go tick and tock. And again, we're framing this in the language of light clocks, but it is true for any clock. Light clocks are only special that they allow us to see their internal mechanism so clearly that we can easily figure out how quickly time slows on the moving clock. Okay, so what we then therefore need to do, according to what we've already established, is we just need to calculate the lengths of the trajectory in the moving clock from our perspective versus the length of the trajectory in the stationary clock from our perspective. Okay, so let's just set this up similar to what we did before, but now we're going to put some mathematics behind it. So there goes the tick trajectory, and there's the tock trajectory. We will again call this length d. And if we're looking at the guy going up and down in the stationary clock, let's say this guy is over here. Let's call that length equal to L. So our goal is to calculate d divided by L. That's what we want to calculate. How do we go about doing that? Well, let's note that if this angle here is theta, then we're in the happy situation that we've got a simple right triangle at our disposal. So if I drop this guy over here, then I note that d over L can simply be gotten from looking at sine of theta, right? Because sine of theta is given by L over d, right? So that means if I look at sine theta to the minus 1, this will be equal to d over L, as we wanted. So the calculation of d over L comes down to calculating sine theta and flipping it upside down. So how do we calculate the sine of that angle? Well, here's the key idea. As the light is traveling from here to there, we know that its speed, of course, is equal to the speed of light in that direction. Now, as you will recall from doing components of vectors in basic geometry or trigonometry, if the speed of the light is c going in that direction, then it devotes a component of its speed equal to c times cosine theta in the horizontal direction. So this is the horizontal component of the light's speed. Now, the reason why I'm interested in the horizontal component of the light speed, again, the speed of light is c, but its progression in the horizontal direction is given by c times cosine of theta. Again, cosine is the adjacent over hypotenuse, so that gives us the projection of that speed into the horizontal direction. This must be equal to the velocity v of the clock itself, right? Because that's the only velocity for which the ball of light will keep perfect pace with the moving clock, which we know it must, because again we can give the argument that the stationary person sees the clock moving, but the person moving with the clock, from their perspective, the clock isn't moving at all, and therefore from their point of view it must be the case that as you're going along, right, as you're going along, the ball of light must be moving in the horizontal direction at exactly the speed of the clock to keep pace with it. That ensures that the ball will go up and down, as we know that it does. So this is a cool little formula over here, because if v is equal to c cosine theta, then that means that cosine theta is equal to v over c. So given v, the velocity of the clock, we can get cosine theta, not exactly what we wanted. We wanted sine theta, but that's fine, because you will also remember the famous little formula that is really just the Pythagorean theorem, slightly disguised, that sine squared theta plus cosine squared theta is equal to 1. And that being the case, we can now write that sine squared theta is equal to 1 minus cosine squared theta. And from cosine theta equals v over c, this guy is equal to 1 minus v over c squared. So sine theta is the square root of that. So that's the square root of 1 minus v over c squared. And then finally, flipping that upside down, sine theta to the minus 1 is equal to 1 divided by the square root of 1 minus v over c squared. And sine theta to the minus 1 is, in fact, d over L. So that, therefore, tells us that d over L, what we're after, is nothing but 1 over that quantity, square root of 1 minus v over c squared. And that is deserving of being called out, because that now is a derivation of the rate at which time elapses on the moving clock compared to the rate at which time elapses on the stationary clock. And that is this factor that we call gamma that we mentioned earlier on. And what I'd like to do is now show you a somewhat cleaner version of that derivation, because this is such an important point that it's worth seeing it done systematically more than once. And here is a video version of the same derivation. So there's the moving clock, and there's the main point, that the component of the velocity of that light in the horizontal direction must be equal to the velocity of the clock. And the horizontal component of the velocity of light is just gotten by taking c times cosine theta. And once you know that that's equal to the velocity of the clock, you are home free, because now we can just solve for cosine theta, given that, and the result between sines and cosines, as I mentioned before, you can go ahead and solve for sine theta, solving therefore for 1 over sine theta. And 1 over sine theta is nothing but the ratio that we are after. And therefore, we get our result, the gamma. The relationship between the elapsed time on the stationary clock and the elapsed time on the moving clock is simply given by 1 over the square root of 1 minus v squared over c squared, this famous time dilation factor gamma. So let's take a quick look over here. What I'm showing in this demo, and again, play with it at home to get a feel for these results, is a plot of gamma versus the velocity of the clock, the velocity of the ship, whatever object is moving. I'm going to always plot that velocity in units of the speed of light. So we can choose the speed, say, of the spaceship in this case to be 29% of the speed of light. And if you calculate gamma at that speed, you have something that's bigger than 1, but not a whole lot bigger. And 1 over gamma is a number that also will come into all our calculations, so you should have a feel for it too. And the point of this little demonstration is to note that gamma stays very, very close to 1. It's always bigger than 1, right? So bear that in mind. We have over here, it's 1 over the square root of this quantity. This quantity itself is always less than 1, so this ratio is always bigger than 1. There's always more time elapsing on the stationary clock compared to the moving clock. So gamma is always bigger than 1. But how much bigger is it than 1? And that we see here is that it doesn't get much bigger than 1 until, look at the steep rise in this curve over here. When the speeds get close to the speed of light, then it takes off and it shoots up. And in this graph, it doesn't get any bigger than 20, but it can be as big as you want, because again, as v gets very, very close to c, this gets very close to 0, and 1 over 0 soars to infinity. And this now allows us to go back to the demonstration that we looked at before and understand it in quantitative detail. So you played with this earlier, in which you saw that time on the moving clock goes off slow from the perspective of the stationary clock, but you didn't know the math behind this. Now you do. And to signify that, this demonstration now also has the time dilation factor. This is actually 1 over gamma that we are showing here, the right-hand graph that was on the previous demo. And again, as the velocity gets very close to the speed of light, 1 over gamma gets smaller and smaller, which means less and less time elapses on the moving clock compared to the stationary clock. This is the essence of time dilation. Let's take a look at a couple of examples in which we can see this effect of time dilation in action. And I'm going to focus on examples that have to do with space travel. So, first scenario, let's imagine that someone is taking a journey from Earth to the star closest to Earth among a collection of stars, Proxima Centauri, 4¼ light years away. And let's assume that the speed that they are able to attain is pretty fast, 536.8 million miles per hour in those archaic units, 80% of the speed of light in general units. And let's now work out some features of their journey. What does this journey look like? Well, let's take a look over here. So we have the ship heading out toward Proxima Centauri, 4¼ light years. The ship forgets to put the brakes on, burns up as it reaches the star. That is not vital to the calculation that we are going to do. Instead, what we are interested in figuring out is how long does this journey take according to clocks on Earth? And then we're going to work out how long this journey takes according to clocks that are on the ship. OK, so let's do that little calculation. Pretty straightforward to do. So the duration, according to the clocks that are on Earth, we all know how to work that out. We just need to know how far the ship is traveling according to those on Earth, divided by its speed. And we have all of that data given to us. So this is, we're told, 4.25 light years. And the speed is 0.8 times c, speed of light. Speed of light I'll write down as 1 light year per year. And now we can just plug that in to get our answer, 4¼ divided by 0.8. And if you plug that in to a little calculator, you get 5.31 years. OK, good. That's the straightforward part of the calculation. now let's work out how long it takes according to clocks that are on the ship itself. And of course, to do that, we need to first calculate gamma, the time dilation factor. So let's do that. So gamma, we know by definition, 1 over the square root of 1 minus v over c squared. So let's now plug in v equals 0.8 times c. So it's 1 divided by the square root of 1 minus 0.8 squared. C's cancel against each other. So let's just work what that is. So it's 1 over the square root of 1 minus 0.64. That's 1 over the square root of 0.36. So that's 1 divided by 0.6. 1 divided by 0.6, 6/10, which is the same thing as 3/5. So put that upside down, and we get gamma is equal to 5/3. Now, to work out the amount of time that has gone by on the ship, we know that less time has gone by on the ship. So we take our 5.31 years. So we take time on the ship equals 5.31 years. And we divide that by gamma, 5/3. And if you plug that in, you will get, this is approximately, if we round it off, to 3.19 years. So that's the answer that we were looking for. 5.31-year journey according to the clocks that are on Earth. 3.19-year journey according to clocks that are on the ship. Now let me use this example to also emphasize one point that is going to be something you're going to encounter over and over again when you do calculations in special relativity. So many times you'll calculate gamma and you'll say to yourself, what do I do with gamma? Do I multiply by gamma or do I divide through by gamma? And your inclination might be to try to go back to the basic equations and have the math tell you what to do. But to tell you the truth, the way we really do it, us physicists who work on this sort of material, we don't often do that. What we say to ourselves is, look, is the number that we're calculating, is it meant to be bigger or smaller than the initial number that we calculated? So in this case, the initial number, 5.31 years, is the time on the ship going to be more than that or less than that? We know it's going to be less because a clock in motion, as we're looking at it, ticks off time more slowly. If it's going to be less, and we know that gamma is always bigger than 1, to get something smaller than 5.31 years, you need to divide through by a number that's bigger than 1. So gamma must go in the bottom. So that's the most straightforward way to work out where the gammas go in any sort of problem of this sort. OK, so that's example number 1. Let me do another example. In this example, we are going to look at another space journey in which a ship will head out into space at 99.999% of the speed of light. But now it's going to do a round-trip journey. It's going to go out for half a year and come back. And we want to figure out how much time passes on Earth during that journey. OK, so let's take a look at this one. So this time, the rocket heads out into space, goes half a year on its own clock, turns around and comes back for another half a year on its clock. And our goal is to work out, given that 1 year has gone by on the ship's clock, how many years have gone by on Earth clocks? Again, this comes down to calculating gamma. And given the amount of speed, given the velocity that the ship is attaining, we can easily calculate that. So gamma, in this case, 1 over the square root of 1 minus. So the speed that we are given has a lot of 9s in it. Let me make sure I get the right number of 9s. So I believe I got 5 9s. 1, 2, 3, 4, 5. This is what we want to calculate. And again, I don't know about you. I can't do those calculations in my head. Maybe you can, which is great. But I just stick this into a calculator. And when I do that, I find the result 223.6 for that value of gamma. Now, what does that mean? Well, we are given that time on the ship equals 1 year. And we want to work out time on Earth. Well, how do we get that? Well, we say to ourselves, the amount of time on Earth we know is going to be bigger than the amount of time on the ship, so we must be multiplying by gamma, since gamma is bigger than 1. So we take 1 year for the time on the ship, multiplied by gamma, 223.6, and we come to our answer that 223.6 years have gone by on the Earth during this round-trip journey in which the rocket has gone out into space and come back. So that's a pretty dramatic example in which there is a sharp difference between clocks on Earth versus the clocks that are ticking away on the ship itself. And again, to get a feel for this, let's look at a couple of demonstrations. So here you have a nice little demo. Again, you should play with all of these. So you choose the speed of a rocket ship. Here it is at, let's say, 33% roughly, the speed of light. And we're assuming that you go on a round-trip journey, just like in the little example, so that the elapsed time in the rocket we assume is 1 year. 1 year has gone by. You've gone out and come back. You are 1 year older. How many years have gone by on Earth? This little demo calculates it. It's basically just calculating gamma for you, but putting in this language. And as the speed gets bigger and bigger, notice that the amount of time on Earth gets larger and larger. And in fact, it could become as large as you'd like by going at speeds that are closer and closer to the speed of light. Another demo where we can look at the same idea in a more graphical form. In this demonstration over here, again, you pick the speed of the rocket, but now it allows you to see graphically how the time on Earth increases as a function of the speed of the rocket. So look at that white ball. For low speeds, there's not much of a difference between Earth and the rocket, but look how it soars up as the speed gets closer and closer to the speed of light. And finally, let me just turn this demonstration around in another manner, which is, in this case, let's look at a fixed duration of time on Earth. Imagine a rocket that is going out and back, and we're fixing how many years have gone by on Earth clocks. How many years will go by on the rocket clock is what this demo shows. And again, it just gives you a feel for what's happening. As the rocket goes faster and faster, the amount of time on its clock when it returns gets smaller and smaller. So again, as v gets just near the speed of light, can't of course reach the speed of light. We'll explain why that is later on. But as the velocity gets very close to the speed of light, the amount of time on the rocket gets ever smaller compared to the amount of time that has gone by on the Earth clocks. Now, let me just mention that we've come upon something pretty striking here, because in these round-trip journeys, in essence, the person on the spaceship has undertaken time travel, right? I mean, if we say that only 1 year goes by, say, on the ship, but hundreds or thousands of years have gone by on Earth, when the person steps out of the rocket ship back on Earth and they look around, it will be thousands of years later, or millions of years later, depending on how close v for that ship was to the speed of light. So that's remarkable right there. Einstein, in a sense, has laid out a blueprint for how to travel to the future. Not science fiction from the point of view of fundamental physics. It is science fiction from the point of view that we can't achieve those speeds yet, but that's technology, that's not fundamental science. Now, the other issue that these round-trip journeys raise is a potential paradox that may well have occurred to you as you are hearing me talk about this stuff, right? Because I've emphasized now over and over again that anybody can claim to be at rest if they're executing constant velocity motion and the rest of the world is going by them. So what stops the person on the rocket ship from claiming that they're at rest, everybody else is moving, and therefore every other clock is ticking off time slowly, and theirs is the one that's going faster. Why can't we use that perspective? And indeed, we can't use that perspective. Here's the quick answer, and we're going to explain this in some detail later on. The person in the rocket ship is not actually executing constant velocity motion. Why? We saw it. They went out, and then they came back. They changed their velocity. And that change of velocity is what's responsible in this particular case for breaking the symmetry between the two views. It's only the Earth perspective that is really justified in claiming to be at rest in these scenarios, and therefore it is only the Earth clocks that are showing more elapsed time. But we will come back to the so-called twin paradox later on in these discussions. But the bottom line is that we now have not only a formula for the rate at which time on a moving clock ticks compared to that on a stationary clock, we now see that to apply it is pretty straightforward and comes to some fairly dramatic conclusions. Conclusions that incorporate a scientific version, if you will, of time travel. I have been talking as though time dilation is an established fact regarding how time itself behaves. And there's good reason for that, right? We came to this idea of time dilation based upon an experimental fact that the speed of light is constant. And then following in the footsteps of Einstein, we have parlayed that into an understanding that time on a moving clock ticks off more slowly than on a stationary clock. Good. Okay, all that's fine. But, you know, when you're talking about an idea that is as strange, that is as counter to experience as time dilation, well, you just are happier. You just are more convinced if you have some direct experimental support for that idea. So the question is there some direct experimental support for time dilation? And there is. There is a lot of experimental support. I'm just going to give you two little examples that really help solidify the idea that this really is tapping into the true nature of time. Okay, the first example is, look, the most flat-footed, straightforward way of verifying that time on a moving clock slows down. It is an experiment that was undertaken in the 1970s, and what happened in this experiment is very straightforward. Scientists took two atomic clocks. They put one of those clocks on an aircraft, and the other atomic clock they left back on the tarmac. They flew this plane all around the world, and they then landed the plane, ultimately, and compared the amount of time on the moving clock to the amount of time on the stationary clock. And lo and behold, when they compared the two clocks, they found that different amounts of time had elapsed on each. In fact, the time difference between them is exactly what Einstein's ideas predict. It's a touch more complicated to work it out relative to the formula that we have derived here. The formula that we derived, this gamma factor, plays a part in the analysis, but because this plane is flying around, it's not at constant velocity, gravity comes into the story. It's a little more complicated, but it absolutely establishes very directly that time on moving clocks ticks off at a different rate. And when you undertake the detailed analysis, taking account of all of the complexities that we're not going to talk about, it confirms all of the ideas that we have described. So that is, look, once you see that these two clocks show a different amount of elapsed time, you, I would think, should be convinced that these ideas are correct. But nevertheless, let me give you one other piece of experimental evidence that's sort of fun, and we're going to come back to it in a little while. It has to do with a species of particles called muons. You don't need to know what muons are, but they're very much like electrons. They're a little bit heavier. But the essential feature of muons is that they're unstable, which means that they disintegrate. They fall apart in a fraction of a second, which means that when these particles are produced, as they are in the upper atmosphere, they can drop down toward Earth, but at some point in the journey, the particle disintegrates. It falls apart into other particles. It breaks apart in essence. And the question is, how far can the particle travel before that disintegration kicks in? And that's worth studying for a moment. So the particle starts up here and drops all the way down to there. And the issue is, how far can it travel before it breaks apart? Now, you all know what the answer to that is. It must be the case that the distance it travels is equal to the velocity times the time. And this time here is its lifetime, right? How long it lives before it disintegrates, before it falls apart into other particles. Now, in the laboratory, scientists have measured the lifetime of these muons, and it turns out that the answer is 2.2 times 10 to the minus 6 seconds. And since scientists also know the velocity that these muons have in the upper atmosphere as they're coming down, they know how far they should be able to travel. And here is the remarkable thing. When you do that calculation, you find that the muon, you would think, should only have enough time before it explodes to go about that far. But observations show that the muon goes much further. What's the explanation? Well, let's think about time for a moment, because this is the time as measured in the laboratory. The muon is in motion, right? That means that its clock is ticking off time more slowly, which means that the muon, from our view, its clock is ticking off time slowly, so it should be gamma times delta t as measured in the laboratory when it's at rest. The way to think about this is, it's as if the muon, if you don't mind me putting it in slightly violent language, the muon has a gun to its head, right? And when a clock that the muon is carrying ticks off 2.2 times 10 to the minus 6 seconds, it pulls the trigger and it falls apart. But if the muon is in motion, from our view, its clock is ticking off time more slowly. So our watch will have long since gone by 2.2 times 10 to the minus 6 seconds, and the muon still will not have pulled the trigger, because from its view, that amount of time has not yet elapsed. So what this means is that the distance, d, that the muon should be able to travel, taking this time dilation into account, is now v times 2.2 times 10 to the minus 6 seconds, its lifetime when at rest, multiplied by gamma. So the formula then is 2.2 times 10 to the minus 6 seconds times v divided by square root of 1 minus v over c squared. And it's that formula. This number is bigger than just the product of the two things in the numerator. This fella over here makes it larger. That explains that the muon can go all the way from here to here without disintegrating. So let's get a feel for this result, that muons travel further than you would have thought based upon Newtonian reasoning because of this time dilation factor. So this little demo, what you do here is you can choose the speed of the muon there in the upper atmosphere. And this will show how far the muon travels before it disintegrates. So again, at slow speeds, not much of a difference from Newton, but then it really kicks in with a vengeance at high speeds. And in fact, this one lets you show the Newtonian answer. So that dotted line that you have on the bottom there, if you can see it, it'll be easier for you to see it on your own when you play with this. So this dotted line is how far Newton would say the muons will be able to travel before they disintegrate. So that's just 2.2 times 10 to the minus 6 times their velocity. But then if you take time dilation into account, you see that the muons can travel much, much further. And that's how we can explain how they can reach from the upper atmosphere down to the surface of the Earth, where Newton would have thought they would have disintegrated way before they hit Earth's surface. So that gives us two strong pieces of experimental evidence that time dilation is real, straightforward, direct experiments that can really only be explained by this idea that moving clocks tick off time slowly. There's a wonderfully startling implication of time dilation that isn't often as fully emphasized as it might. And I'd like to briefly describe it to you now. It has to do with the following fact. So we know from the formula for gamma that the effects of time dilation only really kick in a significant way when the relative velocity that's being studied in a given situation approaches the speed of light. That's all true. But there is another way in which the effects of time dilation, in which the effects of the relativity of simultaneity, in fact, can be amplified over very large distances. Over very large distances, these effects can become significant even when the speeds involved are ordinary, everyday velocities. So how does this go? Well, to set it up, let's first think about time for a moment from the perspective of experience, right? So we all generally think of time as a kind of continuous unfolding, a continuous flow. But for the purpose at hand, it's useful to also think about time in a different way, as a kind of series of moments, a series of snapshots, one moment after another moment after another moment. And any physical process can, of course, be described in this way. A flower, a wild animal running moment after moment after moment, horse running and so forth. It's just a series of snapshots that capture each subsequent moment in time. In fact, you can even go out into space, if you will, and think about the Earth in its orbit around the sun. Again, moment after moment after moment. Okay, so what I'd like to do is start with that way of thinking about things, and I'd like to compare my set of snapshots, my sequence of events that are unfolding over time, and want to compare my snapshots to somebody else's snapshots who's moving relative to me. And to do that, there's a related idea that I want to introduce, which is the concept of a now slice. And by a now slice, what I mean is I consider the world and I think about all things that are happening right now, like the stroke of 12 on a clock, or at that moment, my cat jumping, or perhaps other events like a bird taking flight at this very moment, say in Venice, or we can go cosmic on this too. So we can imagine at that very moment, a meteor just striking the surface of the moon, or go even further away, we can imagine a supernova explosion way in the far reaches of our galaxy. Now, a now slice is a slice in this picture here where I put down all those events which I say happen at one moment in time. And if I look at one now slice after another, this is the unfolding of one moment after another after another. So each of those events that lie on a given slice constitute those things that I say were real, were happening at a given moment. One now after another now after another now. There are 2 points that I want to stress about this. We give this picture a name that makes perfectly good sense. We call this space-time, right? Because we have all of space in each one of these slices. Imagine the slice goes on forever, includes everything that's out there in the cosmos at a given moment. And along this direction, of course, we have the unfolding of time. So we have space and time. That's where the name comes from. Second point is common sense and everyday experience would tell us that every single observer in the universe, regardless of their motion, should agree on what is on a given now slice. That's the Newtonian view of how the world is put together. But when Einstein comes into the story, that radically changes, because with Einstein we have now learned that the constant speed of light means that observers who are in relative motion do not have the same sense of simultaneity. They do not agree on what is happening at a given moment in time. And that has a startling implication that I'd like to describe. And to do that, let me use a little metaphor here. It's one that actually I used in my NOVA program, Fabric of the Cosmos, if you've seen that. But if not, it's a straightforward metaphor. Think about this whole expanse, this whole space-time expanse, as if it's kind of like a big cosmic loaf of bread. And what these now slices are, I'm basically cutting this loaf of space-time into pieces which represent all of space at a single moment in time from my perspective. If someone is moving relative to me, they have a different perspective of what now is, what is simultaneous, and that means they carve up the loaf at a different angle from me. So let me just show you that schematically. So let me imagine I consider the bird's eye view of that picture just because it's easier for me to draw. And let me write down my now slices in there. So from the bird's eye view, I will draw space at one moment of time, space at, say, the next moment in time, the next moment in time, and so forth. So these are all my now slices. And just so that I have these labeled in a way that we all understand, put it down here. Going to the right in this picture is what I consider the future. And going this direction is what I consider the past. Now, somebody is moving relative to me, and let's say they are also interested in drawing space-time slices. So let's draw theirs. And because they're moving relative to me, they will slice up this region of space-time at, say, a different angle relative to me. They slice the loaf with a knife that's angled relative to my slice, because their notion of simultaneity, what's happening at a given moment, say, differs from mine. Now, if we are dealing, and this is the point, if we are dealing with low velocities, the person far away has a low velocity. So we're not talking about velocities near the speed of light. What that translates to in this picture is that the angle that we have here, this angle is relatively small. So in the vicinity of where that person is sitting, low velocity motion has virtually no impact. But the point, and I'll show you an animation of this in a moment, is that over larger and larger distances, let's say I am over here, and let's say somebody else who's doing the moving is far away, over very large distances, a tiny angle can get amplified into a very large difference in time, a very large difference in our conception of what's happening at a given moment. So let's take a look at that idea in animated form. Let's imagine we are looking at a big expanse of space and time, and we have a character, an alien, very, very far away in space, and we have a more familiar looking character, a human being sitting still on a bench over here. Now, if initially these two individuals are not moving relative to one another, they share the same idea of simultaneity if there's no motion, so they slice through the space-time loaf in the same way. They both agree on what's happening at a given moment in time. Okay, but now let's change things a little bit. Let's let our alien friend hop on an alien bicycle, say, and let's say the alien starts to ride away from me. because of the relative motion between the alien and me or the guy on the bench, the alien has a different conception of simultaneity, a different notion of what's happening now. And what that means is when the alien slices up the space-time loaf into all of space at a given moment, the now slice will cut through at a different angle. And again, the point is, small velocity means small angle, but consider a small angle over larger and larger and larger distances between us, and that small angle turns into a big change in time. So in fact, the alien's now slice actually sweeps into the past. And it can be a significant sweeping into the past. When you put in some numbers, as we'll do later on in this course, you find that the sweep goes beyond when that guy was a baby, goes further back in time than that, and in terms of events on Earth that the alien would claim to be happening right now from his perspective, it might be hundreds of years ago. Say, Beethoven putting the final touches on the Fifth Symphony. Now, the thing that's not completely obvious about this and does take some mathematics, and if you're taking the math version of this course, we will do the math. If you're not taking the math version, I hope this is sufficiently exciting that you might take the math version of the course. But putting that to the side, why did it swing to the past and not, say, to the future? Here's a quick way of thinking about it. Remember the treaty signing ceremony. President of Backward Land, right? Backward Land was rushing away, that president, and he signed the treaty late, right? He was not the one who did it first, he did it second, if you recall. So in essence, if you are moving away, you are sweeping to the past. You are old news from that perspective. But that also means, thinking now from the treaty perspective, the president of Forward Land, if you are approaching, if you're going forward, your notion of simultaneity should sweep into the future, and indeed that is the case. So if the alien hops on the bike again, but turns around, say, and doesn't ride away from Earth, but rides toward the Earth, then indeed the alien's notion of what's happening right now on Earth does sweep from what we consider to be the present into what we consider to be the future, and might include strange things from our perspective, like this guy's great-great-great-granddaughter maybe teleporting from one place in the universe to another. So the point is, the whole notion of what you consider to be real, what you consider to be taking place right now, is totally dependent on your motion, right? So initially, when the alien was not moving, say, relative to us, let's put ourselves in the position of the guy on the bench. From our view, we agree with whatever the alien says is happening right now, whatever's real, we totally agree, right? Now, when the alien gets on a bike, we don't suddenly discount the alien's perspective because he's on a bike. So if the alien then says that other events are considered to be now, to be real on his now slice at a given moment, we should accord that statement the same status, the same believability as when the alien wasn't moving relative to us. So if the alien tells us that things in our distant past are real, they are on his now slice at a given moment, we need to take that into our perspective on what's real. If the alien tells us that things in our future are on his now slice at a given moment, we need to take that into account too. So what this collectively tells us is that the traditional way that we think about reality, the present is real, the past is gone, the future is yet to be, that is without any real basis in physics. What we're really learning from these ideas is that the past, the present, and the future are all equally real. Time dilation is one of the strangest counterintuitive concepts that you're ever really going to encounter. And it's nice to have a kind of mental mnemonic, a kind of shorthand way of thinking about this strange idea that perhaps makes it a little bit more intuitive. I'd like to give you such an intuitive way of thinking about time dilation now. And let me say, you can justify the explanation I'm about to give you mathematically. And if you're taking the mathematical version of this course, we will justify it a little bit later on. But if you're not, don't worry about it. But this gives you a nice way of thinking about why it is that time ticks off more slowly when a clock is in motion. Here's the idea. Forget about time for a moment. Let's just think about space. And imagine that we have a car that's headed due north at 100 kilometers per hour. Now imagine that the car steers off and drives to the east without changing its speed. Now its motion in the northward direction will not be as quick as it was previously because some of the northward motion has been diverted into northeast motion. So what that means is motion can be shared between dimensions, and when motion is shared in that way, motion that was fully devoted to one direction gets diverted to another direction, so motion in the initial direction slows down. Let me just show you a little visual on that. So here we have our car. I'm going to show three versions of the car. One's going due north, the others are going northeast at various angles. And there you see the point. This car has traveled much further in the northward direction than these cars because these cars have diverted some of the northward motion into eastward motion. So the idea is when you go in a different direction through space, you divert some of your initial motion into that new motion in the new direction. Good. Okay, now let's take that idea and apply it not to space, but to space and time. Okay? So right now, here I am, and you would say that I'm not moving relative to you, say. But of course I am moving, right? Look at my watch, right? My watch is ticking second after second after second, taking me forward in time, forward in the time dimension, if you will. Good. Now, imagine that I get up and I start to walk. Einstein basically told us that as I walk, I divert some of my previous motion through time into this motion through space, which means I move through time less quickly. Much as over here, this car goes less quickly in the northward direction because it's diverted some of the initial north motion into east motion. When I start to move, I divert my initial motion through time into this motion through space, so my passage through time slows down. That idea, to me, is the most straightforward, intuitive way of understanding time dilation. You can make it mathematically precise, but putting that to the side, if you want to think about why it is that a clock slows when it's in motion, simply think to yourself, when it's sitting still, all of its motions through time, when I see it moving through space, it has diverted some of that motion through time into motion through space, so it passes through time more slowly. That's why time ticks off slower on a moving clock. The constancy of the speed of light we've seen in the context of all of the ideas of special relativity has a dramatic impact on our understanding of time. It also turns out, remarkably, that the constant speed of light has a dramatic effect on space and also on mass. And we're going to talk about both of those, but for now, let's turn to the first one, the implications of the constant speed of light for our understanding of space. So first is, why would we expect motion to affect space? Well, it's pretty straightforward, right? Because speed, as we emphasized, is distance divided by duration, which of course is space divided by time. So if we learn, as we have, that the speed of light is constant, well, we've also learned that time is not constant. So that means that space must in some way compensate for the non-constant aspects of time in order that the ratio stays the same allowing the speed of light to be unchanged. So in schematic language, in order to ensure that the speed of light is constant, space must adjust itself in tandem with time so that the ratio for light stays fixed. So the picture you should have in mind is something like this. If we consider that time is not constant, therefore space must change too in relation to motion, so that the ratio space over time is such that the speed of light can remain unchanged. And what we'd like to do is take that rough idea and make it explicit. We'd like to now determine what the effect of motion is on space. How are we going to do that? Well, let's work in the context of a concrete example. Let's imagine that we have a train, and we want to ask ourselves, how would you measure the length of a train? Well, that's a pretty straightforward thing to do when the train is stationary, right? Because if the train is stationary, you take out a tape measure and you measure the length of the train, right? So let's get things going. Let's imagine that that is the situation, and we're going to consider the length of a train from the perspective of somebody on the train. So that will be our fearless train rider, George. From his view, the train is at rest relative to him, so he pulls out his tape measure and he simply stretches it from one end of the train to the other, and that way he measures the length of the train, and let's say he finds that the train is 210 meters long. Good. Okay, that's all perfectly straightforward. Let's now imagine that our second character, Gracie, she is on the platform. So from her view, the train is in motion. So she has to use another approach to measure the length of the train, right? She can't really pull out her tape measure and measure the length of the train because the train's rushing by, right? So that's not a way that she's going to measure the train's length. Instead, she does something more clever. Let's assume that she knows the train's speed. Let's also assume that she has a stopwatch. What she can do is the following. She'll start the stopwatch just as the front of the train is passing her. She will stop the watch as the rear of the train passes her. So she knows how long it took for the train to pass by her. She knows the speed of the train, and she simply multiplies them together. She multiplies velocity times time to get the length of the train, right? So let's see her do that. There she is on the platform. She has her stopwatch handy. The front of the train goes by. Boom, she starts the watch going. When the rear of the train passes her, boom, she stops the watch. She gets the elapsed time, in this case 5.9 seconds. She multiplies it by the known speed of the train in order to get the train's length. That's her approach. Now here is the remarkable fact. The two approaches, George's approach, where he simply used a tape measure, Gracie's approach, where she uses this watch and the known speed of the train, they yield different answers, right? So if you multiply this out, just in this particular example, 30 times 5.9, 177 meters. Numbers, I should say, which I've made up just to illustrate the point, which is that Gracie has gotten a shorter length of the train compared to George. Now, at first sight, that is hugely surprising, right? But the question is, does this actually puzzle George? Assuming that George has taken the discussion that we've already had to heart, and he fully knows about time dilation. With the notion of time dilation, does the discrepancy in the length of the train from his perspective and from Gracie's perspective, does it puzzle him? And the answer is no. Because from George's perspective, here's what he says. He says, look, I understand Gracie's approach. She's using length equals speed or velocity times elapsed time. But I also know that Gracie, from my perspective, right, I'm now George, Gracie, from my perspective, is in motion. Clocks in motion tick off time at a slower rate. If a clock is ticking off time at a slower rate, it'll show less elapsed time, and therefore it will, in that multiplication, yield a shorter length. So from that point of view, George understands why it is that Gracie got a shorter length, but the question remains, who is right? Is the length of the train 210 meters, as George says that it is, or is the length of the train 177 meters, as Gracie says that it is? Now, you can probably guess the answer to the question of who is right based on what we have discussed so far. The answer is they are both right. The answer is length itself is a concept that we need to rethink. We normally think about length as the length of an object, but in fact, the length of an object depends on its speed when you measure it. Now, where does that idea really come from? That idea comes from the following fact that we have emphasized repeatedly. Simultaneity is in the eye of the beholder, right? Now, to measure the length of an object, you need to measure its front and its rear simultaneously at the same moment. Now, if two observers have different notions of simultaneity, they will therefore have a different notion of the length of an object. No single result is solely right. No result is wrong. They're all equally good. Now, having said that, just a little bit of language. We generally call the length of an object, when you measure it when you are at rest relative to the object, as George is in the case of the train, we call that the rest length of the train. We call it the proper length of the train, but that just calls out a particular perspective, the perspective of somebody not moving relative to the object. But fundamentally, you can measure the length of an object when it has any speed relative to you, and you will get a different answer depending upon the speed of the object. So the general conclusion then that we are reaching is that moving objects are shortened along the direction of their motion. And let me stress that it's only along the direction of motion that the object will appear shorter. The height of the object will not change at all. And a little tiny argument can establish that. For instance, if you were to imagine that the train were going into a tunnel, right? And let's say it just barely fits. Now, if it were the case that from one person's perspective, the height of an object, not in the direction of motion, if that were to change, let's say I were to say that the height of objects gets smaller. Well, then from my perspective on the train, the tunnel will be smaller. I won't be able to fit. I should smash into it, right? From the perspective of someone who's on the tunnel, it'll be the train that will be shrunk in that direction, and so it will fit. Now, however weird relativity is, it can't be the case that in one person's perspective, there's a crash of the train into a tunnel, and from another person's perspective, there's not a crash. That would really be a contradiction. That would be a paradox. That can't happen, and therefore we learn that it can't be the case that dimensions that are perpendicular to the direction of motion, they are not changed at all. They stay fixed. And so we describe the shortening of an object along the direction of motion. We call that length contraction, or we call that Lorentz contraction. That is the language that we used, and let's take a look at a simple example of that. So here is a case where we're looking at a New York City taxi cab moving pretty quickly along, and along the direction of motion, the taxi cab is shrunken. It is shorter along that direction than it would be when it is at rest. So let's take a look at a demonstration which will give you a feel for the amount by which an object appears shrunken along its direction of motion when you are looking at it. So this little demonstration here allows you to pick the speed of this taxi cab as it's rushing by you. And again, get a feel for this in your bones. As the speed creeps up, not much of an effect on its length, but when the speed approaches the speed of light, the object gets ever shortened along the direction of motion. Now, you can ask yourself a natural question at this stage, which is, does the object in motion really shrink? And if it does, like, what's the force that's squeezing on it? Now, that's a natural question, but it's pretty loosely phrased, because the main point that we have come to is that the notion of length itself requires a notion of simultaneity, because again, if you're measuring the length of an object in motion, if you first say measure the back of the object and the object moves and then you measure its front, let's say I'm measuring the length of a fish in a pond, right? If it's swimming along and I first measure its tail and I let the fish swim and then I measure its nose, well, I'll get a different length than I would if I measured the front and the back, the nose and the tail at the same moment. So it's critical in talking about the length of an object to commit to a notion of simultaneity, and that requires choosing a frame of reference, because observers in motion don't agree on what happens at the same moment in time. And because of that, different vantage points differ regarding what happens at the same moment. We come to the conclusion that an object in motion has a length that depends upon its speed, because its speed determines the degree of the lack of simultaneity between two perspectives. So if we ask the question again, do objects in motion shrink? The best answer I can give you is yes and no. It definitely is the case that an object in motion has a length from my perspective that is shorter than when that object is at rest. But it's not as though someone has come in with a vice and crushed the object down. It simply is that the old idea that there's a universal notion of the length of an object needs to be updated. By relativity, the length of an object depends upon its speed when you measure it. And that is a surprising result. The length of an object depends on its speed. Now, give you a couple other little examples of that to have in mind. And both of these examples make use of the idea that we discussed earlier, the relationship between observing something and measuring something. So back then, I described how we're mostly focused upon reality. So we don't really care so much about human perception. We care more about what happened in the world to be responsible for what we see. But sometimes it's kind of fun to look at what we literally would see if some of the effects of relativity were visible to us. And in this example here, we are now going to look at a taxi cab, but done more precisely. So this is how a rushing taxi cab would literally look if you could see it rushing by at high speed. Notice that the taxi cab appears kind of twisted, right? In the last frames of that little video, we could see the whole back bumper of the taxi cab, even though ordinarily, if a taxi cab was rushing by us, we wouldn't be able to see the whole bumper. We'd only see the part that was nearest to us. The reason for that is a little bit complicated. It makes use of the fact that when we look at something, we are seeing light from the object. Light takes different amounts of time to reach us from different points on a three-dimensional object, because those three-dimensional points are a different distance from our eye. If you take that into account, then that little video gives you a really good sense of what it would be like to literally see an object rushing by near the speed of light. The second example puts us inside the taxi cab itself, shows us what it would be like to look out the window of a taxi cab that's rushing through a city near the speed of light. And as you can see, the world around you, not only does it have the length contraction that we've described, if you take into account the finite light travel time, the differences from one point to another, you see that space has a kind of warped, distorted, curved look. The world around you seems to be curving in around you when your speed approaches the speed of light. So again, if you could find a taxi that could travel near the speed of light, and if you had really good eyes, so you could actually see the world around you as it was rushing by you at very high speed, that is what you would see. So these are some very strange effects that the constant speed of light has on the nature of space, but they all follow directly from the analysis that we've already done with time. So once you know that time has weird features, you know that space must have weird features too, in order that in tandem they can keep the speed of light constant. Let's now work out the mathematical formula that will allow us to figure out the amount by which a moving object is shortened in its direction of motion if we know what its speed is. And what's the essential idea there? Well, we're going to just do a little bit of algebra, simply making use of Gracie's approach for measuring the length of the train, and we'll compare that to a similar calculation that George could do. And we'll see that George's answer will always be different from Gracie's. Gracie's answer is going to be shorter than George's if she's watching him rush by. OK, so again, what's Gracie's approach? She simply says that the length of the train is equal to the product of the speed of the train times the amount of time, according to her, I'll call this now T. Gracie, the amount of time on her watch between when the front of the train passes her to when the end, the back of the train passes her. Good. OK. Now bear in mind that George could actually play the same game. We described him measuring the length of the train using a tape measure. But look, George could, on the train, as he's going along, he could look at Gracie. He could start his watch when he passes her. He could stop his watch when she passes the back of his train. And in that way, he could get a length, which would be the length of the train from his perspective, which would be v times the amount of time that elapsed on his clock. Good. Now we can compare these two because we know that the amount of time on Gracie's clock is going to be shorter than the amount of time on George's clock, right? Because we know that a clock that's in motion, and again, from George's perspective, Gracie's clock is in motion, so that means that this gamma, which is bigger than 1, goes downstairs. So the amount of elapsed time on Gracie's clock is less than the amount of time on George's clock. And therefore, we can now plug that back in upstairs. So gamma downstairs means we have T times George times, this is 1 over the square root of 1 minus v over c squared. So putting it downstairs brings upstairs a factor of 1 minus v over c squared. And now we are done, because if we plug that into this equation over here, we have v times T Gracie, I'm now going to write as T George, times square root of 1 minus v over c squared. And now I look over at this expression here, and I recognize that the piece of this in brackets, v times T George, is just the length of the train from George's perspective, which means that the quantity that I have on the right-hand side here, this can be rewritten as the length of the train according to George, in the brackets, times the square root of 1 minus v over c squared. So then, putting it all together, we now learn that the length of the train, according to Gracie, is equal to the length of the train according to George times this factor of 1 over gamma, which is 1 minus v over c squared. And again, this quantity over here, this is 1 over gamma. This is always less than 1, which means the length of the train, according to Gracie, is always less than the length of the train, according to George. So basically, you can see it right here. This all comes from the time difference between their two measurements of how long it takes the full length of the train to pass one location in space. And basically, space is compensating for that time difference in just the right way, actually, to keep the speed of light constant. But the bottom line is, the length of the train, according to Gracie, she's watching it rush by, will be the length of the train, according to George, times this factor that is less than 1. So now we can go back to this demonstration of these ideas with a little additional understanding now, because we have an understanding of where the amount of contraction comes from mathematically. So in this expression, we now have gamma shown as well. We didn't have that before. So you should play around with this to get a feel for it. And there you see it. As gamma gets bigger, then 1 over gamma gets smaller and smaller. And that's the amount by which this is contracting. And that is the mathematical version of the idea that we described earlier qualitatively. That's the quantitative way to work out the degree to which an object rushing by will be shortened along the direction of motion. All right, now let's put Lorentz contraction, length contraction to work in a handful of examples. So the first example that we'll look at is actually one that we encountered earlier, where we had a space journey, where we had a ship going from Earth to Proxima Centauri. And you may recall that we calculated a variety of things associated with that journey. Let me remind you of the data and the results that we found. We took the speed of the ship to be 80% of the speed of light. We're going to still choose that to be the speed now. The distance between Earth and Proxima Centauri, we approximated that as 4¼ light years. And we first worked out the duration of that journey according to clocks on Earth. That's pretty straightforward. It's just the distance divided by the speed, which we found gave us 5.31 years. If you remember, if you don't, that's the answer that we found. We then worked out the duration of the journey according to clocks on the ship. And we found, using the time dilation formula, that the duration was not 5.31 years, but rather 3.19 years. Good. OK, that's what we found earlier. Now we're going to take it a little further and describe things in terms of a kind of potential puzzle that we will encounter. It's not really a puzzle. The way we'll resolve the issue is, of course, by making use of what we've just described, Lorentz contraction. OK, here is the potential puzzle. So if indeed it is the case that the distance between Earth and Proxima Centauri is this number of 4¼ light years. Let's just write this out. So if that distance there is 4.25 light years, and indeed, if the duration of that journey, according to those on the ship, delta T ship, is, as we found it to be, 3.19 years, then the potential puzzle is, how could the ship cover 4¼ light years in 3.19 years? I mean, light itself, from the perspective of those on Earth, would take 4¼ years to cover that distance. How could the ship cover that distance in less than 4¼ years? That's the little puzzle. Now, of course, it's not really a puzzle. We just need to think it through. How do we think it through? Well, let's bear in mind that when you're talking about the distance between Earth and Proxima Centauri, 4¼ years is the distance according to those on Earth. But those on the ship have a different view, right? Because on the ship is moving from Earth to Proxima Centauri, which means from the perspective of those on the ship, that distance between Earth and Proxima Centauri is moving this way, right? They claim to be stationary with the rest of the world rushing by. And when a distance, when a length rushes by, we know that it becomes Lorentz contracted, right? So let's work that out. So the distance between Earth and Proxima Centauri is Lorentz contracted. And let's put in some numbers. We know that the Lorentz contraction factor, again, comes from our favorite number gamma. So what we do is we take 4.25 light years, and we divide through by gamma to get the Lorentz contracted distance. And we know what gamma is. You guys have now done many of these calculations, so you're expert at this. So I can do this quickly. If the speed is 0.8 c, then we get a 0.8 squared here. And I won't bother taking you through all the details. Either you can do it yourself, or you may simply recall that we found that gamma equals 5/3 for v equals 0.8 c, which means now if we look at this distance, rather than it being 4.25 light years, which is what people on Earth say it is, we now divide through by gamma, and that's dividing through by 5/3. So we're now looking at 3/5 of 4.25 light years. And that we can easily work out. This gives us 2.55 light years. And that is wonderful, because 2.55 light years presents no puzzle to be covered in 3.19 years. No longer do you need a speed bigger than the speed of light. You're now taking a larger number in years than you are covering a distance in light years, so the velocity will be less than 1. And in fact, let's work out what that velocity is using these numbers. So if we take v now to be equal to the Lorentz contracted distance, 2.55 light years, divided by the duration according to those on the ship. So now we're doing an apples to apples ratio. It's the distance according to those on the ship and the time according to those on the ship. And that's the kind of calculation that you want to do, where you're using quantities calculated from the same perspective. 2.55 divided by 3.19, encourage you to work it out. And if you do, you will find that it's 0.8 c, as it had to be, right? Because that is the speed of the ship that we are given, and therefore that is equivalently the speed with which the distance between Earth and Proxima Centauri is rushing by the ship from the ship's perspective. So let's just box that little guy up, as this is the answer that we were looking for. So the velocity is indeed 80% of the speed of light when we take into account the Lorentz contracted distance between Earth and Proxima Centauri and correctly use that in an apples to apples ratio. The distance according to those on the ship, the speed at which that distance is rushing by the ship will be gotten by using the duration of the journey according to clocks on the ship. And when you do the ratio in that way, indeed you get 80% of the speed of light, just as it had to be. OK, let's now take a look at a second example of Lorentz contraction in action. And in this case, we're going to look again at an example that we studied earlier, which offers us a similar kind of potential puzzle. We're going to look at this case of muons falling toward the Earth. And you may recall in this example that we mentioned earlier, we noted that time dilation plays a key role in allowing the muons to travel the distance from where they begin to where they end without disintegrating en route. And let's now give some numbers associated with that and see in detail what it means. OK, so here is the distance that the muon travels. And as in the statement of this situation, let's assume that v is equal to 0.994 times the speed of light. And if you go ahead and calculate gamma for this, I'm not going to do that. You can easily work it out. 1 over square root of 1 minus v over c squared. That turns into 9.14. Okay, let's hold that in mind. Now let's look at a potential puzzle in this situation. We are told that muons only live for 2.2 times 10 to the minus 6 seconds. And yet, if we look at the distance that the muon travels in this particular example, let's give this a number, an experimentally verified number, 5.9 kilometers. The question is, what does that mean for the speed of the muon? Because again, if it travels 5.9 kilometers in a time from its perspective, which is 2.2 times 10 to the minus 6 seconds, then from that you can get a velocity of the muon with respect to the Earth just by doing distance divided by time. And if you do 5.9 kilometers divided by 2.2 times 10 to the minus 6 seconds, the result you get is quite large. In fact, if you work it out, as I have worked it out for you here, it comes in at more than 9 times the speed of light. So what in the world is going on? Well, it's obvious what's going on. We've done the wrong calculation here, right? Because when we're talking about things from the muon's perspective, this distance is length contracted. It is Lorentz contracted, right? So rather than going 5.9 kilometers, the distance from the muon's perspective is equal to 5.9 kilometers divided by gamma. It's shortened, and that distance is 0.65 kilometers. And now, if we use that length in calculating the speed, 0.65 kilometers divided by 2.2 times 10 to the minus 6 seconds, lo and behold, as it must, this gives us 0.994 times the speed of light. Again, properly speaking, from the muon's perspective, it is the Earth that is rushing toward it at this speed. But the key fact that I want to emphasize here is, again, from the perspective of the muon itself, it is only traversing 0.65 kilometers. It is not traversing the length that we would ascribe to it of 5.9 kilometers. And that's how its speed works out to be the correct value, a value that is less than the speed of light. All right, another example of the utility of this idea of Lorentz contraction. Let's consider the following example. Imagine that Gracie, she's just turned 18, very excited, and she decides that for her 19th birthday, she wants to celebrate it on the planet Zaxtar. Now, here's the issue. Zaxtar is pretty darn far away. It is, we are told, 1 billion light years away. So at first sight, the notion that Gracie could travel from Earth to the planet Zaxtar in 1 year, even though the distance between these guys is so incredibly far, that just seems kind of preposterous, right? So this distance over here is 1 billion light years. Is that what we were told? Yeah, goodness gracious. So this is 10 to the 9 light years. Can she travel from here to here in 1 year? Naively, no. But the answer actually is yes when we take into account all of the effects of relativity. Let's see how that goes. So from Gracie's view, if she is rushing along at a speed v, how long will she say? That is, what will she say is the distance from Earth to Zaxtar? Again, from her view, she's stationary. Zaxtar is rushing toward her. And because of that, the distance between Earth and Zaxtar will be length contracted. So she will say the distance is 10 to the 9 light years. But now she's going to multiply that by the contraction formula, 1 minus v over c squared. So that, from her view, is equal to the distance between Earth and Zaxtar that needs to be negotiated. And she wants to negotiate that in 1 year. So what does that mean? Well, if we look at velocity of Gracie times the time for Gracie, which I can just now hardwire in at 1 year, she wants velocity times time to cover that distance of 10 to the 9 times the square root of 1 minus v over c squared. So the question is there a v such that this equation will hold true, right? So that the distance that she covers, velocity times time in 1 year, will be equal to the Lorentz contracted distance from her view between the two objects. Well, this is just an equation now, right? We can just solve this equation, and it's straightforward to do that. And let's just work it all out for good measure. So let's square everybody up, because you have a square root over here that we want to solve for v within. So we have v squared times 1 year squared. This is equal to 10 to the 18 times 1 minus v over c squared. And the units, I'm just going to carry these over on this other side so that we have them. So it's light year squared. So this whole thing over here was in light years. So now we squared up, and the units are light years squared. Sometimes it's good to keep the units along for the ride just to ensure that at the end all the units work. That is a nice diagnostic to make sure that you haven't made any mistake. OK, so this is now a calculation that we can carry out. So let's bring all of the v squares together. And what do we have then? So we'll have v squared times, well, what do we get? So we have a v over c squared and a factor of 10 to the 18 over there. So let's now bring that over with a plus sign to the other side. So that's this guy over here. And the role of the c over here is just to change these units. So c, 1 light year per year. So when you take c squared, multiply by light years squared, the net result of that is to give us a year squared, which is exactly the right units that we have over here. I don't know if you need me to do that. OK, I'll quickly do it. So we have 1 light year per year. This quantity is squared. It's in the denominator over here, so it's 1 over that. And we're multiplying that by a factor of light years squared over here. And in my haste, I've actually left this out. So it's 1 light year per year, I should have said. So then when you put all these guys together, the years squared comes upstairs. And the units are exactly what you need them to be to combine them. Good. That was a little diversion. Now let's carry out the rest of the calculation. V squared times 1 plus 10 to the 18. What are we left with on the other side? Well, we're left with 10 to the 18. And then the fellow over there is just giving us a factor of 1 light year per year squared. So let's call that c squared. So that will get our result in the units of the speed of light. And now we can just solve for v squared. And it is equal to 10 to the 18 divided by 1 plus 10 to the 18 times c squared. And now if we just take the square root of that, the speed at which Gracie needs to travel is equal to the square root of 10 to the 18 over 10 to the 18 plus 1 times c. So that shows us that Gracie has her work cut out for her to achieve that high speed. But because of length contraction, she can actually travel all the way from here to here and only age 1 year. One way of thinking about that is time dilation. That's another way of solving the same problem. This time, I'm wanting you to think about this in terms of length contraction for the other concept. From her view, from the view of a space traveler, she's not actually traveling that far. From our view, it's very far away, 1 billion light years away. From her view, it's not, because this factor over here, when v is very close to c, as this is very, very close to c, this factor here is very close to 0. So like the taxi cab, that distance is length contracted, Lorentz contracted, and she can, in fact, cover it in 1 year. All right, one more example of applying this idea of length contraction. And what we're going to do is consider a light clock again. But the light clock in this case will be in an interesting configuration. It's going to be turned on its side. And what we're going to see is by demanding that the length of time, the amount of time, I should say, for the light clock to go tick-tock should be the same regardless of whether it's vertical or on its side. We're going to be able to have an alternate derivation of the length contraction formula. So we're going to make use of the fact that two clocks must tick off time at the same rate regardless of their orientation in space. And in order to make use of that, we're going to consider a light clock that is ticking horizontally, not vertically. And we want to calculate how long it takes that clock to go tick-tock and demand it's the same as the amount of time when the clock is vertical. And so let's record here that when the clock is in its usual orientation that we're used to, when the clock is vertical, if it's stationary relative to us, that guy ticks at a speed of 2 times L, has to go up and down, and if the length between the mirrors is L, when it's stationary, it's 2 times L over C. And if this guy is now in motion, we're going to compare the vertical clock in motion to the horizontal clock in motion. We know when this guy is in motion, it ticks off time at a different rate, where the factor of gamma comes into the story. So it ticks at a rate gamma, remember it ticks slower, times 2L over C squared. So this is the amount of time that it takes the clock to go tick-tock. And now I want to explicitly do that calculation, but for the horizontal clock. OK, so let's look at the horizontal case. And let's break the calculation of the tick-tock into the 2 natural pieces that we have on the board right here. So when this guy is, say, moving to the right, let's say the amount of time it takes for the ball to go tick, let's call that amount of time, let's call it t right, because the photon is moving to the right. And when we look at the second part over here, for it to bounce to the other mirror, let's call that amount of time tock. We'll call that t left. So the total time for the horizontal clock to go tick-tock will be tr plus tl. So we're going to equate this equal to tr plus tl. And now it's incumbent upon me to calculate tr and tl, which will only take us a moment. OK, what is tr? Well, how far does the light need to travel to go from here to here? Well, that distance, whatever it is, must equal velocity times time. And t right is the amount of time. We just need the distance. Well, the distance, of course, is equal to, let's call it L prime. Whatever the length between the 2 mirrors is from our perspective watching this move, it's got to be L prime plus, well, how far did the clock travel from here to here? Well, that's just velocity of the clock times the length of time that we are looking at it, which is tr. Familiar construction now, allowing us to calculate tr. So we have c minus v times tr equals L prime, and therefore t right is equal to L prime divided by c minus v. Right? This should be familiar from the calculations we did with the precedent to forward-land and backward-land. This is just a version of that same story. What about for t left? So we have c times tl. That must be equal to L prime. But now the ball of light doesn't have to travel as far because the clock is helping it. It is moving in the opposite direction to the direction of the ball of light. So we should subtract off v times tl. And that means that c plus v times tl must be equal to L prime, which means that TL must be equal to L prime divided by C plus V. Okay, we are now cooking with gas, because if we add TL and TR together, what do we get? So we get L prime over C minus V plus L prime over C plus V. That's equal to L prime. Let me put all the stuff that is multiplying L prime over a common denominator, C minus V times C plus V. And that C plus V, C minus V means I need to multiply this guy by C plus V, the first term. The second term, I need to add in this guy. I need to multiply by C minus V in the numerator. So putting those both together, we note that the V's cancel against one another. And we are left with 2L prime times C divided by C minus V times C plus V is C squared minus V squared. OK, now, what we want to do is compare that to this expression, because I said that t right plus t left must be equal to the same amount of time for a tick-tock on the moving vertical clock. So I'm going to put the final part of the calculation up here. So we are left with gamma times 2L. How did I get a C squared in there? You guys should have stopped me at home if you saw that I had the extra square in there. So let me just fix that over here, right? So this guy over here, of course, is 2L over C times gamma. Where did that 2 come from there? I don't know. It was a mistake. Next time, you should feel free to correct me. I'll let it go this time, but let's keep going. So we have gamma times 2L over C. That is equal to 2 times L prime times C divided by C squared minus V squared. This equation now allows us to solve for L prime, which is, perhaps I should have written it down, but I said it. It's the length between the two mirrors from our perspective as this guy rushes by. We now just solve for L prime, which is straightforward for us to do. And I'll leave the rest of the algebra to you, because it's just 2 lines. But you will get at the end of the day that L prime is equal to L divided by gamma. And you will recognize that that is the very same length contraction formula that we have already derived. This is an alternate derivation which comes from this kind of slick way of packaging the ideas that a light clock should go tick-tock, tick-tock at a rate that doesn't depend on whether it's ticking horizontally or vertically, and demanding that they both go tick-tock at the same rate requires that the distance between the two mirrors as the clock is rushing by is less than the distance between the two mirrors when it is vertical, and the factor between them is indeed the length contraction factor gamma, just as we know it must be. So let's briefly recount where we've gotten so far. And what we have seen in essence is that observers who are moving relative to one another do not agree on some very basic things. They do not agree on time. They don't agree on the notion of what happens at a given moment. They have different conceptions of simultaneity. And they do not agree on how long it takes for something to happen. We've also seen that observers in relative motion do not agree on space, right? They do not agree on the length of objects, and they do not agree on the distance between one point and another. All of that is great. All of it is stunning. What we want to do now is to find a general mathematical framework that will put all of these effects together in one mathematical framework. We want to kind of find a unified mathematical structure, if you will, that will embrace everything that we have found so far. And in the end of the day, what it's going to provide us is with a systematic kind of turn-of-the-crank approach for working out the relationship between the observations of two sets of observers that are moving relative to one another. That's where we are headed. Now, What are some of the essential ideas? To get the ball rolling, we need to think of reality, much as we have been doing, as a collection of events. That's all that reality is, right? A firecracker explodes, a baseball gets hit by a bat, somebody jumps off of some high mountain and dives into the water. Every one of those physical phenomena can be thought of as an event. And reality is nothing but the collection of all of these events that happen across space and throughout time. And that way of framing it is vital because events, each and every one of them, occur at some point in space, and they occur at some moment in time. And what that means is, if we want to understand the relationship between the observations of two sets of observers, we have to be able to address the following question: where and when do I say sequence of events take place? Where and when does somebody else say that that sequence of events take place? It may be surprising at some level that that kind of question would hold so much importance for the nature of reality, but we've already seen hints, or even more than that, we've seen evidence that this question is vital because different observers don't agree on where and when things happen. Means that space and time are not what we thought they were. But what we want to do now is to set up a framework for answering that question in a more systematic manner that'll take into account all of the effects that we have already discussed. So relativity of simultaneity, time dilation, Lorentz contraction, we want them all to be built into this framework. To do that, the first order of business is we need an efficient, effective way of describing where and when events take place. And that takes us to the subject that we are now going to consider, the subject of coordinate systems. And I'm going to begin with the discussion of coordinate systems using the familiar example that you already have encountered over the course of many years of schooling. That is coordinates for space, and a little bit more precisely, Cartesian coordinates for space. So this is a subject that we are all familiar with, but just to make sure that we're all on the same page, let me take you through this material that you probably already know about, just so that we all are starting from the same place. So to talk about coordinates in space, let's start with a simple example. So if we're looking at coordinates to describe locations, say, in a city like Manhattan, what do? Well, we can set up a coordinate axis, those are the red lines, and we can use streets and cross streets, or streets and avenues, as a way to delineate location in the flat plane of the city. But of course, the city itself, we know, is not really flat. If we dive in to Manhattan, for example, we find there are buildings, there are tall structures, of course, and we need, therefore, to extend our coordinate system so that it can describe not only where things are in the street and avenue sense, but also where they are in the vertical direction as well. So you can think about x and y as the streets and avenues, and you can think about z as the coordinate that gives us the position of an object in the vertical direction. So if, for example, some event were to take place, a flashing bulb goes off at the Empire State Building at some particular location. If the Empire State Building is, say, at the origin of the xy part of the coordinate system, that event will be at 0 and 0 for that location being at the origin of the system, and 6 would indicate the height at which that flash took place. And if we look at another flash, I don't know if you saw that it went by quickly, so let me show you that again. So if you look at another flash over there at the Chrysler Building, in this coordinate system, that might take place at x, y, and z at 4, -3, and 5. So that is a very basic, simple example of coordinates that describe three-dimensional space. And I want you to think about a three-dimensional coordinate system as a tool, a powerful tool that allows us to delineate the series of locations that may be occupied by any object in motion. So if we look at a baseball going through this 3D space, we can delineate its trajectory by highlighting the points in 3D space that the baseball goes through during its journey. And the flashing lights there, that is the highlighted points in this 3D grid, are a record, if you will, of where the ball was during its journey. Now, of course, if we had a very refined grid, this would be a continuous highlighted line that would give us a record of the trajectory of the baseball through that 3D space. Okay, so that's a fairly standard idea of coordinate systems in 3 dimensions. Oftentimes, for simplicity, we will consider coordinate systems not in 3 dimensions, but in 2. And that is even easier to deal with. Let's imagine we start with a schematic version of our 3D coordinate system. To turn it into a 2D system, all we need to do is say, take a bird's eye view and then project out, squash out the z direction, and then we have a nice 2-dimensional system that is used to describe the location, say, of 2 buildings in the city. There's our Empire State Building, and there is the Chrysler Building. Even more than that, we will sometimes simplify even further still. And I have to tell you, for most of the calculations that we're going to do, we're going to make use of the simplification that I'm about to describe, where rather than just going down to 2 dimensions of space, we'll actually go all the way down to 1 dimension of space. So we squash out, if you will, the y-axis, and we're left with the x-axis, describing the positions of objects along a straight line. Now, you may recognize this is actually fairly accurate. If you think about each of these ticks as being 2 city blocks, then if you're familiar with how things are laid out on 5th Avenue in Manhattan, that's not a bad little schematic description of where those particular objects are. But the bottom line is, this is the way we go about setting up coordinates. Ideally, we'd always work in 3 dimensions. It's often too complicated, so we either work in 2, and for the most part, in many of the examples we'll talk about, as I mentioned, we'll do 1-dimensional examples. That will be rich enough to reveal most of the mathematical structure that we are heading for. An important feature of coordinate systems is that there is no unique way to lay them down, right? You can really choose to orient your coordinate system any way that you choose. And the idea is that different coordinate systems amount to giving different coordinate labels to the same location. Let me give you an example to make that concrete. So if we take this 2-dimensional system, the red one, we can also lay down a green system, which is rotated relative to the red system. And let me just pull them apart so you can see them separately. Each of these coordinate systems is as good as the other. Notice, though, that the coordinate labels that the Chrysler Building gets in the 2 systems are different, right? So there's no way to say that one system is right, one system is wrong. They're both equally good ways of describing where things are, but the coordinate labels are different from one another. And we will encounter different coordinate systems all the time, because ultimately we're going to apply this to observers that are moving relative to one another, each of whom has their own coordinate grid. That's where we are headed. And what we're going to do is always distinguish the different coordinates in 2 such coordinate systems, either by colors, but for the most part, I'll distinguish them in the conventional way of having one set of coordinates, say the xy coordinates over here, and these coordinates we'll typically call the x prime, y prime coordinates. And the kinds of examples then that we will study will require us to set up a dictionary between one set of coordinates and another. And this, again, is something that I think many of you have already encountered, but it's perhaps worth going through it just to make sure that we are all on the same page. So let's look at 2 little examples. where we'll set up some coordinates and we'll set up a dictionary between them. So let's set up some initial coordinate system. So I've got, say, my xy axes. So let me choose a more reasonable color. So here's my x, and here's my y. And I'm going to thin that line out a little bit. And let's imagine we now put another coordinate system in here. Let's choose, I don't know, one that's rotated relative to the first, say something like that. And that system is one that we would call x prime and y prime. And first off, just to refresh your memory on how you use these coordinate systems, these different systems, let's say you've got some point over here. In order to get the coordinate values of that point in the xy system, what you do is you drop a line parallel to the y-axis over there, and you drop a line like that parallel to the x-axis. And this location, let me call that x0, and this location, let me call that y0, means that you associate the point with the coordinate labels x0, y0. Now, for the other system, let's just change colors on that. You play the same game. We drop a line over here parallel to that axis, and we drop one over here parallel to the other axis, and just as in the case before, we use those values. So this guy over here, let's call this guy x prime 0, and let's call this guy over here y prime 0. And that means that this point, let me give it a name, P, can either be called x0, y0 in the original blue system, but P can also be called x0 prime, y0 prime in the red system. Two different coordinate labels for the same point. And what we want to do, and we will do this in the more general case, ultimately when time comes into the story, but let's start where everything is much more familiar. We want to set up a dictionary between these two coordinate systems. So how do we set up that dictionary? Well, that's a straightforward calculation I think many of you have already seen. And if you've already seen these, you can skip ahead. But if you haven't, or if you want a little refresher, this is worth just bearing in mind how this goes. So let's consider this point over here, say in the x prime, y prime system, this guy x0 prime, y0 prime. And we want to know what coordinate labels that would be associated to, say, in the blue system, the xy coordinate system. So the little xy down there indicates that I'm trying to figure out the coordinate labels in the blue system. How do I do that? Well, it's pretty direct. So let me take this guy and note that I can write it as x0 prime times 1, 0 in the prime system plus y0 prime times 0, 1 in the prime system, which means if I can take this little guy over here, which is 1, 0 in the prime system, or this little guy over here, which is 0, 1 in the prime system, if I can rewrite each of these in the blue system, the xy system, I can plug in, and then I would be done. I would have my answer. How do I figure out, therefore, what 1, 0 prime is equal to in the blue system? Well, let's say I tell you that this angle through which I've rotated the system is equal to theta. Well, you know, therefore, that if I zoom in over here, and if you let me draw it a little bit bigger over here, so we got angle theta. This is 1 because I'm looking at 1, 0 in the prime system. We know this is a nice little right triangle that we can draw to get the length along the blue axis, which of course will just be cosine of theta in that particular case, because that's adjacent over hypotenuse. Hypotenuse is equal to 1. So that tells us that this guy can be written as cosine theta along this direction. That's that length over here. What about the coordinate value of this guy in the y? Well, that I would have to drop this and look at that right triangle. And as you can see, the length of the blue segment, the other leg of the right triangle, gives the y coordinate value. And as you can see, that would just be equal to sine theta. Same idea, but now I've just got the right triangle with the other side of the triangle relevant to the calculation. So that's 1, 0 prime. What about 0, 1 prime? What is that equal to? Well, I want to now take that point and project it left and right, and it's the exact same calculation, except now you see that I'm going to get a minus sine theta along this direction, and I'm going to get a plus cosine theta in the y direction. So now I have succeeded in writing 1, 0 in the prime system in terms of the xy, the blue, and similarly for 0, 1 prime. And as I said, now I'm cooking with gas because I just plug those into the equation that we have over here. So this, therefore, is equal to x0 prime, that's just a number, times cosine theta times sine theta in the second slot, plus y naught prime times minus sine theta cosine theta in the second slot. And now I can just expand this out and get my answer for the coordinates of P in the xy system. So we find that x0, y0 are equal to, putting this guy through the parentheses and collecting the terms in the first slot, I get x0 prime times cosine theta minus y0 prime sine theta. And then in the second slot, I have an x0 prime sine and a y0 prime cosine, both with a plus sign. So it's x0 prime sine theta plus y0 prime cosine theta. And there we have it. So that gives us our dictionary that allows us to go from one coordinate system to the other. And this may, again, likely is something that you've seen before. But this is a nice little model for the kinds of machinery that we are looking for, but ultimately when we're including time in the story as well. That's where we are headed. But now at least we have got our base. We understand coordinate systems, a second coordinate system, and the dictionary that allows us to go from one coordinate system to another. And the next thing that we are going to do to get a feel for it, you should play around with it a little bit. And this demonstration is one that lets you do that. So in this particular case, you can choose the xy coordinate of a point at will. That's the yellow guy over there. And you can choose the angle that rotates one coordinate system relative to the other. And what the demonstration does, it tells you the coordinates of the point in the rotated system. So basically, it just makes use of the calculation that we just did to figure out what the new coordinate label of the point is in the new system. You should play with this, but let me just emphasize one point before we break, which is this. The yellow point itself, it's not moving at all in this way of thinking about things. It's the coordinate systems that are moving. And it's therefore just the label that we use in the coordinate system of the rotated system relative to the unrotated one that changes. And that is, again, a model for where we're going, because we are ultimately going to find that events out there in the world, they are the anchor, if you will. They are the unchanging ingredient in reality. And we're going to find that the different perspectives of one observer relative to another provides the labels, if you will, much as the different coordinate systems provide the different labels from one frame to another. So now we've reviewed how to translate from one coordinate system to another if those two coordinate systems are rotated relative to one another. There's an even easier case that will be of relevance to us, which is when we are looking at coordinate systems that differ by a translation, where you slide one coordinate system relative to another. So let me just do that example quickly for completeness here. So again, let me set up my little system, set up my coordinate axes. Here's axis number 1, the y, axis number 2, say the x. And now the new system that I want to talk about just amounts, in essence, to moving the coordinate grid over, say, from the right to the left or from the left to the right. So let me just overlay that so that we can see it. And imagine that we're told that the amount by which the coordinates have moved over, let's say this amount, this distance here, say, is equal to a. Now, what is the way of translating from one coordinate system to another? Well, it's immediate. So if this is the xy system as before, this is the x prime, y prime system as before. And let's imagine that we have some point P, I don't know, put it right over here. If P in the blue system, the xy system, has coordinates, let's say they're x naught, y naught, what will the coordinates of that point, what will those coordinates be in the red system? Well, if we have slid the red system over to the right by an amount a, that means the coordinates of this point x naught will be diminished by that amount because the coordinate system has moved under it, if you will. What about in the y direction? Well, we haven't done anything there at all, so that guy remains unchanged. So that's a nice, really simple dictionary that allows us to go between the two coordinate systems if a translation is involved. Now, you know that we sometimes like to get a little bit fancy when we're talking about physics and coordinates, and indeed what we can do is consider where we do the general case, where you both translate and rotate at the same time. It's not hard to work out. I'm not going to do the mathematics for you here, but it just is a combination of what we've already discussed. Instead, I'm going to let you play with it, again, by fiddling with some of these demonstrations. So let's take a look over here. So this is a case which will first just have the translation. So that's real simple. That's what we just described. Choose a point at will, slide the coordinate system back and forth, and make sure, it's simple, but make sure you understand how it is that these coordinates are changing in the translated system. But if we look at another example where we put both of those effects together, then it's a little bit harder just to eyeball. So now imagine that you choose the coordinates of a point. Let's put it over there. And now let's both slide the new coordinate system, but also rotate it. And doing that, it's a somewhat more complicated mathematical dictionary. It's just a combination of the two effects that we've already been talking about. But again, it gives you at least a more intuitive feel for how it is that change of coordinates looks numerically when you look at some explicit example where you've got control of both the angle and the displacement. Okay, that's all that I really want to talk about on the issue of coordinates for space. The next thing that we are going to turn to is our real interest, right? This is stuff that's old hat to most of you, but our real interest is to take these ideas and apply them to time. We know now how to specify where an event takes place using coordinates in space. But of course, when you're talking about events, you need to not only say where they happened, you also need to talk about when they happened. And so we need to figure out a way of doing that. And the standard approach in special relativity, it may seem a little extravagant, But here's what we are going to imagine doing. We're going to imagine putting a clock at every single point in space, right? And we're going to use the clocks much as we use the coordinate grids of a spatial coordinate system. Namely, the spatial coordinates tell us where an event happens, and the clock sitting at that location tells us when the event happened. So it's a kind of curious idea. Let me show you a couple pictures to make it a little bit more intuitive what we're talking about here. So imagine that we have our 3D coordinate system in space, the red grids as before, but now as you see, we have put a clock at every single point in space. Now, of course, I haven't used every point. I've just used the intersections of the coordinate axes because it's only there that I can draw a picture that would be sensible. But you should imagine that every single point in space has a clock ticking away, and we use that clock to figure out when an event took place. Now, that's sort of using, if you will, old-fashioned analog clocks. If you want to bring us a little bit up to date, we can take a look at a coordinate system in which the clocks that we put at each intersection of the coordinate lines is a digital clock. It doesn't matter what clock that you use, but the point is, in order to describe where and when an event takes place, this is the kind of structure that we are going to set up. A coordinate grid of the 3D sort for space, and then we are going to consider putting a clock at every location. Now, just to give you a feel for how we make use of this, let's now imagine that we consider, say, that baseball. Remember that baseball that we spoke about earlier, moving through three-dimensional space. We can use this structure to not only record where the baseball went, but also when it was at a given location. So here's the ball going through space, and now we can give a more refined description of its trajectory by, as before, recording the locations in space that it passed through. Those are the flashes. But every time it goes by a given clock, we stop the clock in order that we have a record of where the baseball was and also when it was at that particular location. And that idea is general, right? So we're going to use this basic geometrical architecture, if you will, for specifying where and when any event takes place, right? So whatever it is, a firecracker goes off, you look at the coordinate system. You read off the x, y, and z values, so you know where the firecracker exploded, and you also look at the clock at that location in space, and that tells you when the firecracker exploded. That is the basic setup that we will be using. Now, for simplicity, as I've mentioned before, we're often not going to use these pretty structures, these three-dimensional structures. Instead, we're often going to do a version where we only have one dimension of space. So let me show you what that would look like if you had a baseball moving through one dimension and you want to specify its motion. How would that look? Well, starting with 3D here, let's now collapse this down to 2 and then to 1. And now let the baseball go across. And you are recording when it was at every location that it passed through in this one-dimensional space. So it's much simpler, of course, than the kind of trajectory that we were describing over here. But nevertheless, the simplicity of this picture will be very useful to us. And then once we have the equations under our belt, we will be able to generalize those equations to the three-dimensional space. So I'll show you those equations at the end as well. OK, so that is the basic setup for describing when and where events take place. Good. There is something vital to this discussion, however, that has been a little bit hidden in what I have shown you. It is, of course, absolutely essential that the clocks that we are using, when we have these clocks located at every point in space, those clocks had better be synchronized with one another. If they're not synchronized with one another, then the meaning of the readout on the clocks, well, it's useless. It's meaningless. We won't know what it means if the clocks themselves are not aligned with one another in time, if they're not synchronized. So the question is, how do we synchronize a large collection of clocks? Again, it might seem like it's one of those questions that, it's just a detail that you shouldn't really worry so much about. Just assume that we've synchronized the clocks. But as we're going to see, it's vital that you really think about this issue because it will play a key role in our understanding how to translate from one set of observations to another when observers are in relative motion. Okay, so let's take this synchronization question seriously. What's the most straightforward, natural suggestion that you might make? Well, gather all the clocks together in one location, start them all going, and then take the synchronized clocks and move them to each and every location in space. That's the most natural suggestion that you could have. What is the subtlety with that? Well, we know that clocks in motion tick off time at different rates. So you might synchronize them as a group right here, but then when they fan out all over the universe, that motion will disrupt the synchronization. They'll no longer be in sync. So that is not going to work. Rather, what you really want to do is have the clocks already at their appointed locations, okay? So they're already out there, so you don't have to move them, so you don't have to worry about that subtlety. But now the question is, if you've got all these clocks out there, how do you synchronize them? Here's the approach that we are going to take. Let's imagine that the clocks are all in the off position. They're not ticking yet. And let's imagine that you have a lot of friends, okay? So many friends, so many coworkers, if you will, that you can assign each one of your friends to each one of the clocks that are out there. So every clock now has a person, an observer, who's with that clock. One special person at the origin. Let's just, for argument's sake, take that person to be me. What I'm going to do is I'm going to set off, at a given moment in time, a bright flash. And when I set off that bright flash, I'm going to start my clock ticking forward in time. Then, when you, one of my friends, one of the observers out there with a given clock, what you're going to do is the following. You are going to know how far away you are from me, okay? And when the flash goes by you, you're going to start your clock in motion. But you're going to be clever about it because you know that there's a certain travel time for the light to reach you. So you're not going to start your clock at 0 the way I did. You're going to start your clock a little forward in time, the amount by which is simply the length of time, the duration of time that you know it will take light to travel from me to you. And each and every observer in the universe will do that. They wait for the flash. When the flash comes by, they start their clock, but they have already made their clock forward in time. They have set it forward in time to account for the light travel time from my clock to your clock to their clock. That ensures that all the clocks out there will be perfectly synchronized. That's the idea. Let me show you that in a 1D and a 2D example so we can see that in action. So here is a 1D system. The flash goes off, and each of these individuals knows how far away they are from the origin. And when the flash went by, they set their clock in motion, but they didn't start it at 0. They started it with a delay, with the amount of time they set it forward equal to the travel time that they know light will take to go from the origin to them. Let me show you that again as that went by a little bit fast. Okay, now watch as the light goes by. That one sets to 2, to 3, to 4, to 5, and now they're all in sync. That's the way we can have a whole collection of clocks that ultimately are all ticking forward in time, and they're all having the same readout. Let me show you a 2D version of the same story. So now we have an observer, a person at the origin. They set off their flash. Each of these people know how far away they are from the origin, and they set their clock ahead by the amount of light travel time so that when they're all ultimately turned on, all of the clocks agree with one another. That's the way we can have a whole collection of clocks throughout the universe that are all in sync with one another. And to get a feel for that, it's good to play around. So here's a little demonstration that you can use to do that. And in this demonstration, you can view it as a little puzzle if you'd like. So I'm not going to do this one for you. For each of these clocks, you are going to set it to the amount of time that you think it should start, so that when the flash of light goes by, if it then starts ticking forward from that amount of time, all the clocks will be in sync. So you can choose any value that you want for these guys. So let's say I was to put that one at 16. I'm going to do this wrong, just so you see how it looks when it fails. So I'm going to choose these to be random numbers. You're going to choose them to be sensible numbers. And if I chose those values and I start this going, the flash goes out. And look what happens. I set that guy to 16. That was wrong. And notice that it's not in sync with the rest of the clocks. You're going to be smarter and simply figure out the value that each clock should initially be set to in order that the collection will be in sync after the flash goes by. The flash, again, is what starts each clock ticking forward in time. Bottom line is, when you make use of this procedure we've spoken about for laying down a coordinate grid in space and for putting a clock at every location in space to give us an understanding of time, that yields what we call space-time coordinates. And in 3D, those coordinates are t, x, y, z. In 2 or 1 dimension, you just drop 1 or 2 of the coordinates. Again, we'll typically focus on the 1D case where we have t and x. Collection of coordinates of this sort is called a frame of reference. And you should think about it, as we've seen, as providing a nice systematic way of locating an event in space and time. It gives you the location in space and the moment in time for any given event that takes place. And you can really think about this, and I just want to quickly emphasize this point, as providing a systematic procedure for dealing with the issue that we discussed a little while back, the difference between what it is to measure something and what it is to see something, observation versus measurement. Because remember, we had this issue that we spoke about, which is when you look at something, you're not seeing it as it is, right? It takes light travel time to go from the object to your eyes. You need to post-process to figure out what happened that's responsible for the light that you are now seeing. In this approach, no post-processing, right? Because to work out what happened and when happened, you use the coordinate at the event and you use the clock at the event. There's no light travel time that comes into describing when and where an event takes place if you've got a space-time coordinate system, if you have a reference frame. And we'll find that it's a very powerful tool for being able to describe the observations of one set of observers relative to another set of observers. That ultimately is where we're going. We're going to set up 2 of these space-time coordinate systems and try to set up a dictionary between them. We now have described how we set up a space-time coordinate system for a given observer. We have coordinates that are spread out through space. We have clocks that are spread out through space as well that allow us to specify when an event takes place. But our ultimate goal will be to consider 2 frames of reference that are moving relative to one another, and to set up a dictionary that allows us to translate between when and where each of those sets of observers say given events take place. Now, to do that, let me set up a little bit of language. I'm going to often describe one set of observers, one space-time reference frame that I'll call team platform. And as the name indicates, I'm going to imagine that that's the frame of reference, say, that we are in. We are stationary relative to that frame. We'll call it team platform. And we're going to contrast that frame of reference with the second frame that's moving uniformly relative to the first frame, and I will call that frame of reference team train. So it's as if one coordinate system is being carried along by a train, if you will, and we're going to compare that to the coordinate system that we have stationary with respect to us. So To get a little feel for what that's like, let's start with 3D example. So there's our, say, spatial coordinate system. Here is the train frame moving relative to us. It sweeps through us, relative to us, and that's the relative motion of the coordinate systems that we are talking about. Now, that animation is inaccurate in a number of ways, right? Because when we lay down a coordinate system, we generally imagine that the coordinates go on forever, right? X, Y, and Z typically don't have an end to them. So if we have one system moving relative to another, each of which extends infinitely far, then a better picture would be something like this. So we have the blue system moving relative to the red system and just keeps on moving at constant speed in a fixed direction. It just keeps on moving forever. That's the two coordinate systems that we are going to try to relate to one another. Now, Team Train, of course, has clocks as well as coordinates in space. So if you let me go back to the finite picture just because it's easier to draw and to see, what we really want to do is consider not just how the spatial part of the coordinates move relative to one another. We're also going to be concerned with understanding how the clocks in one frame of reference relate to the clocks in another frame of reference. Now, those pictures are pretty, but they're a little complicated to deal with because they are in 3 dimensions of space. What we'll actually deal with in detail are examples in which we have 1 dimension of space. So this is the analog in 1 dimension. I've displaced the 1 dimensions in this vertical direction so you can see it more clearly, but really these should be on top of each other, and the idea is the blue system, the train frame, is moving relative to our frame of reference, the platform. So this is Team Train, and this is Team Platform. So in this one-dimensional case, the coordinates that will be relevant will be, say, t and x for the red system, and we'll have other coordinates that we will call t prime and x prime for the train system. And our goal is to set up a full dictionary between these guys. But let me ask at the outset one leading question, if you will, which is this. How do the clocks of Team Train look to those who are in Team Platform, in the platform frame of reference? And perhaps I should say the reason I'm using the word team is because I am imagining that there is an observer stationed at each and every location who's responsible for setting up the synchronized clock. So that's where the language comes from. So if you have all of these people here looking at that frame, the question is, what do the clocks look like from their perspective? And vice versa, what do the clocks of Team Platform look like to those folks who are constituting Team Train? And I'm going to go through the answer to this in some detail. But before I do, let me just emphasize that you pretty much can give me the answer, at least qualitatively, to that question already, because all you need to do is think back on the treaty signing ceremony, right? That's a very potent example. It plays a direct role here. What do I mean by that? Well, in the treaty signing ceremony, those folks who were on the platform, those people on the platform, right? They did not agree that the president of Forwardland and Backwardland signed the treaty at the same moment, even though the presidents of Forwardland and Backwardland thought that they did. So to those on the train, the 2 presidents were in sync. To those folks on the platform, the 2 presidents were not in sync, which basically translates into this picture that the relativity of simultaneity comes to bear, meaning that each team will claim that the other team's clocks are not in sync with one another. Amazingly, the relative motion between the 2 frames of reference ensures that even if every person in each team does their job impeccably, sets their clock at the right moment when the flash goes by, just as we described, if they do that correctly, nevertheless, those people who are looking from Team Platform toward Team Train and those from Team Train toward Team Platform will claim that the clocks are not in sync with one another. And I'd like to spell that out in detail for you mathematically now, so we can really get a sense of how it is that these two sets of observers have such different conclusions about the nature of the clocks in their frame of reference. Okay, so let's now go through the clock synchronization procedure that those observers in team train undertake, and we want to analyze it from the perspective of those people in the platform. Okay, so how does this go? Let's look at the blue frame that's going by, and the idea is the flash of light goes off, and when it reaches the person over there at x prime, what does that person do? So now let's fill in some equations so we know what we are talking about. So team train, they follow the same clock synchronization procedure that we have discussed, which means that the person at x prime says to themselves, how long did it take the light to reach me? And they say, well, it took an amount of time, distance, divided by the velocity of light. So they say, I had better turn my clock on and set it equal to x prime over c, and then allow it to tick forward in time. That's what they do. And that's true regardless of where they are. So x prime is the variable in there. Regardless of the value of x prime, that's the approach to synchronize the clocks. Now, those in team platform, so they criticize what they see happening in this moving frame of reference for a number of reasons. Let me spell them out. So reason number one, those in the platform say, hey, you set your clock to x prime over c, but that distance is not actually equal to x prime, right? From the perspective of those in the platform, we have length contraction coming into play, which means that they claim that that distance is actually x prime over gamma, not equal to x prime. They also say you were moving to the right. So you were moving away from the beam that was coming toward you, just like the president of Backwardland, right? So you're moving away from the light. And what does that mean? It means that it takes longer to reach you. How long does it take to reach you? Well, let's work that out. So from the perspective of those in the platform, okay, they say that the amount of time that it takes that ball to reach that person, well, it must be an amount delta t such that when you multiply it by the speed of light, you get a distance. What distance does the light need to travel? Well, it has to travel this distance over here, which is x prime over gamma, according to those in the platform. But the light also has to travel from where it was emitted to the initial location here before it travels that final part of the journey. That is, it has to travel a distance equal to the amount of displacement x prime experienced to the right from the perspective of those in team platform. What is that? Well, that's just the velocity of team train times delta t. So very similar equation that we have encountered numerous times before. So this tells us, therefore, that delta t times c minus v must be equal to x prime over gamma. So according to those on the platform, the amount of time between when the flash went off and when the person at x prime received it is equal to x prime over gamma times c minus v. Now, there's a third effect that the platform observers also say comes into play, which is they say that the clocks in team train, they say they're in motion, so team train clocks tick slowly, right? So there we have our time dilation effect. So the folks in team platform say, this is the amount of time that we say went by from when the flash went off till when it reached this person at x prime. But they say your clocks are ticking off time slowly. In particular, this clock at the origin is ticking off time slowly. So they say that delta t prime, the amount of time that actually has gone by for team train is equal to delta t divided by gamma. And we have our formula for delta t. So that means this is equal to x prime divided by gamma squared times 1 over c minus v. And now let me just simplify that guy a little bit. Write this as x prime. So gamma squared downstairs, it's 1 over square root of 1 minus v squared over c squared. So that comes upstairs as 1 minus v over c squared divided by c minus v. And that we can simplify as well. So let's just pull out this as x prime over c squared times, let me write this as c squared minus v squared. That's the same thing. I pulled out a c squared on the bottom, over the top, I should say. So c minus v, and I write it like that because now I have my answer, x prime over c squared times c plus v, which as well can be written as x prime times x prime over c, that is, times 1 plus v over c. OK, so that is the answer according to those who are in the platform. They say that is the time at which this person should set their clock. So when they look over here and that person sets their clock to x prime over c, what do the people in team platform say? Well, according to team platform, what then is going on? They say that this individual over here should set their clock initially to that value when the flash goes by, namely x prime over c times 1 plus v over c. But instead, they set their clock to x prime over c. And what then is the difference between these two? The difference between these two is equal to x prime times v over c squared. So according to those in the platform, this person over here has set their clock to a value that's too small, too early. In other words, that clock will lag behind the clock at the origin of team train, because when the clock at the origin of team train is reading that value, this clock will read the value x prime over c. So according to the observers in team platform, this number is the amount of time that the clock at x prime lags behind the time that we have over here. So this clock will lag behind this clock by an amount given by this expression. Now this expression, of course, works also if you're looking at clocks on the other side. Just replace x prime by minus x prime. What that will mean is clocks on this side are going to be ahead of the clock at the origin. So according to those in team platform, we now have this wonderful result that the clocks are not in sync. Namely, although team train has done an impeccable job from its perspective in synchronizing its clocks, we learn that team platform says the train clocks are not in sync. They are out of sync. And in particular, we have learned that the leading clocks, the clocks that are in the direction of the motion, okay, those clocks are behind in time. And those clocks that are in the rear of the motion, those clocks are ahead in time. So that is a very different picture from what the folks in team train are saying, but nevertheless, that is where this analysis takes us. So we can look at a little mathematical demonstration of that. So let's look at that over here, where in this demonstration you get to play with choosing which frame of reference you are interested in, and you can choose the relative speed between them and see how the clocks differ in time. So let's imagine that these two frames are moving relative to each other. You choose the velocity. The velocity will just be indicated here. You won't actually see the frames moving relative to each other. And now you can choose one frame or another as your reference frame, okay? So if this is your reference frame, so in the examples we're talking about, schematically, that would be the train. That's what we've been putting above. When the train looks at the platform clocks, they see that they are out of sync for the same reason that we have described. But the one that we have described directly is this one. Here we are in the platform. All of our clocks are in sync, but those in the train are not in sync. And again, those that are in the direction of the motion are ever further behind because of the x prime in the formula that we just derived. Those that are in the rear of the motion are ever further ahead. And by changing the speed of the two frames, you can make the time difference between those clocks larger and larger. So what then is, say, a video picture of what this would look like? Let's take a look over here. So if we consider the view from team platform on team train, here's what we have found. So from these guys' perspective, the beam of light that's headed left or right has different distances to travel, just like in the treaty signing ceremony. So when the observers in team train carry out the synchronization procedure, from the perspective of team platform, the collection of clocks will all be out of sync. Those that are further to the right, again, will be further back. They'll lag the clock at the origin. Those clocks that are to the rear of the motion, they will be ahead in time. And again, this is nothing but the treaty signing ceremony spelled out now in full glory, right? So just as the president of Forwardland signed first was ahead in time, the clocks that are in the rear of the motion will be ahead in time. And just like the president of Backwardland signed the treaty second, was lagging in time, the clocks that are in the direction of the motion will be lagging the time at the origin as well. It is nothing but that example spelled out in detail. We now know that clocks that are in sync from the perspective of one set of observers are not in sync from the perspective of another set of observers moving relative to them. And we're going to make use of this asynchronous nature of clocks in motion to carry out the goal that we have set for ourselves, which is to have a nice systematic dictionary, a mathematical formula from the coordinate system of those in the platform to the coordinate system of those in the train, including in that coordinate system the clocks of each set of observers. That's where we're ultimately heading. But before we do that, I thought it would be kind of fun to take a moment out from that task and just look at the way in which we can use this realization of asynchronous clocks to understand some of the things that we have already encountered and to use it to come to some pretty surprising conclusions about some things that we've yet to discuss. Okay, so the first example that I'd like to look at is the issue of length contraction, but now viewed from a different perspective, right? So when we initially spoke about length contraction, what do we do? Let's think about it again, reflect back. So we had Gracie on the platform. George is rushing by on a train, and she seeks to measure the length of his train by using a watch, right? So when the front of his train passes, she starts the watch. When the back passes, she stops the watch. What does she do with that duration of time? Well, she multiplies it by the speed of the train to get the length of the train. Velocity times time is the length. And we concluded that that number would be smaller than the number that George, who's on the train, claims to be its length. And we understand that because her clock is ticking slow from George's perspective, so she gets a smaller length. That all makes good sense. But here's the thing. Using our coordinate system that we've now spent some effort setting up, there's another way that Gracie and her team of friends in team platform can measure the length of George's train. And this particular way that I'll now show you doesn't seem to make use of the rate at which time elapses on her clock at all. So I'll show you the video in a moment. Let me just quickly tell you what you're going to see. Right. So Gracie's new approach is this. She has set things up with the engineer of the train in which George and his compatriots are moving. She set it up so that the front of the train is going to pass by her at exactly 12 noon. Let me do it this way. So the train is going to come in, and at exactly 12 noon, she set it up so that the front will pass her. She says to all of her friends that are flanking her on left and right, she says, when the back of the train passes you, look at your watch. If your watch also says 12 o'clock, raise your hands. Why? Because since Gracie's measuring where the front of the train is at 12 o'clock, it's right where she is. If she knows where the back of the train is at 12 o'clock, and she'll know that by looking at her friend whose hands go up, she'll just measure the distance between her and her friend, and in that way, she will measure the length of the train. Okay, let's see that in action. So here it is. We've got the train coming in to the station. Oh, it's coming from this side. So it's set up so that 12 noon, it just passes Gracie. She puts her hands up, and it's this person over here. It's this member of her team who found that the back of the train was passing her at 12 noon, and all Gracie then needs to do is look at the length between her and her friend. So again, just so you can see this in a little bit more detail as we're going to analyze this, the train is coming in. She has already set it up so that at 12 noon, it's all worked out. It is just passing her. She puts up her hands. Her friend down the line is waiting for the back of the train to pass, looks at her watch. It's also 12 noon, so she raises her hand, and it's the distance between the two that they will now claim is the length of the train. And the reason why I'm describing this alternate approach to measuring the length of a train is because in that scenario, the rate of time that elapses on Gracie's clock seems irrelevant, right? We haven't had any time elapse on her clock at all, really. We just set one moment in time when the front of the train was passing her. So the question is, since the rate at which time ticks on Gracie's clock and her friend's clock seems not to matter, how do George and team train now explain the fact that Gracie and her team get a shorter length for the train than he and his team do? Let's work out the claim that they make now to explain the discrepancy in the lengths. Here's how it goes. It makes use of course, the asynchronous clocks. So what George and team train claim is that the clocks in Gracie's frame, in team platform, they claim those are not in sync because from team train's perspective, the platform is moving, right? And in a little bit more detail, they claim that Gracie's clock, right? They say that Gracie's clock is ahead of her friend's clock. Why? From the perspective of team train, right? Team train, when we saw the animation, was coming in this direction, right? Which means from the perspective of team train itself, the platform is moving that way, right? If the platform is moving that way, we know that clocks that are in the rear of the motion are ahead. Gracie would be in the rear. She's in that direction relative to her friend. So Gracie's clock, according to this reasoning, would strike 12 noon before her friend's clock did. What does that mean? Well, the location of the front of the train is measured first. The train continues to move, and only then is the location of the back of the train measured. So according to team train, it's obvious why team platform gets a shorter result. They measure the location of the rear of the train after it has moved forward. So let me show you what that then would look like in a little animation over here. So now we are in George's and team train's perspective, okay? Coming into the station, there's the platform. They claim that Gracie throws up her hands first, and then her friend throws up her hands, thereby measuring a shorter length. Let me show you that in a little more detail. That went by a little fast. So here we go. Going to watch it slow down a bit, and we'll put some stops in the middle. George is coming in. 12 noon, Gracie throws up her hands, okay? Now, I want you to focus on the clocks. Let me make them a little bit more visible. So I've made the second hand longer so you can see it. Notice that the clocks going this way are ever further back, right? They are ever late. That's the asynchronous nature of the clocks. So from George's perspective, the clocks to the right have yet to reach 12 noon. So it's only later on, when there's enough time elapsed for these clocks to go forward, that Gracie's friend, her clock will finally reach 12 noon. But in the interim, the train, of course, has moved, and therefore they will get a shorter length. They're only measuring that piece of the train because the train is moving. So if we now take a look at this in full glory, George and his train, they are coming in, and they find that Gracie throws up her hands first, her friend throws up her hands second, and in that way measure a shorter length for the train. So it's a nice application of this asynchronous nature of clocks. Now we have another way of thinking about length contraction that all has to do with one set of observers not agreeing on what the other set says are clocks that they claim are in sync. The other set of observers say that they are not. We understand how Team George, Team Train explain the fact that Team Platform says that the train is shorter than the length that they think it is. Okay, all that's good. Now I'd like to ask the question, how does Team Platform, how does Gracie and her friends explain Team Train's claim of having a longer length train? We should be able to explain that too. Here's one quick way of thinking about it. Team Train decides that they are going to leave an imprint of their length so that Gracie and her friends in Team Platform can examine the length of the train at their leisure without it speeding by, right? So what do? They get 2 cans of spray paint, right? They put one in the back of the train, one in the front of the train, and they ride through the platform, and at an appointed moment, each of those cans of paint, the button is pushed, and it sprays out a splotch on the platform. Team Train continues to go, but now Gracie and her friends can look at the 2 splotches and simply measure the distance between them to get the length of the train. So the question is, will Team Platform now have an explanation for why that length is longer than the length that they directly measured for the length of the train? Well, asynchronous clocks come into the story again, because I'll show you a little picture of this in a moment, but think it through with me. Think it through with me. So what's going to happen here? So from the perspective of Team Platform, the clocks in Team Train are not in sync, right? So the train is coming in. It's rushing by. Let's do it this way. The train is rushing by this way. From there, I'll do it this way so you can see the front. Rushing by this way from their perspective. We know that clocks in the rear are always ahead, right? So if Team Train has worked out that at 12 noon, from their perspective, both of the cans of paint will be fired, well, Team Platform will say noon happens first on the clock over here. This clock lags behind. The clock in the front lags behind, which means they will see this paint fired, train continues to move, and then that can of paint fired. And therefore, of course, the splotches will be further apart because the train moved before the front splotch was made. That is the idea. So we can see a little picture of that. There it is. Train is coming in. And from Team Platform's perspective, splotch and splotch, right? And the distance between these 2 splotches is long. Team Platform agrees with that. It is longer than the length of the train that they measured, but they aren't at all confused by that, because they say that this splotch over here was made after that the train moved, and that's why the splotches are further apart. So again, asynchronous clocks come to the rescue in giving us an understanding of one set of observers' observations of how things are versus those of another. It all fits together. It all works. All right, one more example, a kind of surprising example where asynchronous clocks change our prediction or understanding of what would happen in a fairly simple situation. And what I have in mind here is to consider the motion of a bicycle wheel, right? So normally what you would think, based upon what we have discussed so far, is, if a bicycle wheel is rushing by, you would think that it would be Lorentz contracted. So it would be squashed along the direction it's moving. It would not have any of its height change, so the circle would kind of turn into an oval, turn into an egg. But it turns out that that is not the full story, because if you think about it, the bicycle wheel itself is an object where you can imagine that there are clocks on it, right? It has a reference frame associated with it, so it can have clocks on it. And again, if you have the bicycle wheel rushing by, you know that the clocks in front are going to be behind those in the rear. They always lag behind. Now, what that will mean is very interesting when you consider the motion of the spokes. So let me draw a little picture so that we can see what I'm referring to. And let me use a little piece of graph paper to try to keep this reasonably close to the shapes that I'm talking about. So imagine that we have a bicycle wheel. It's not a bad circle, I guess, right there. And let me draw some spokes on this. And I don't know what color. Let me choose green spokes for the heck of it. So imagine, in fact, let me just draw one spoke to be simple about it. So that's a spoke which at a given moment in time is vertical, right? Now this wheel is rolling. Now what will that mean? So let's look at the spokes a little while later, and I'm going to contract this up a little bit because it's assumed to be moving to the right with some speed, but I'm really interested more in what's happening with the spokes right now. And notice the following. So if you consider the fact that from the perspective of those who are moving with the bicycle, right, they would claim that as the wheel turns, the spoke that we see over there will go from the vertical position to, say, the horizontal position. And what we mean by that is that at one moment in time, let's say, for argument's sake, that at 12 noon, the spoke has now turned from its initial position into the position that we now see. So it's rolling along in that direction. Now, 12 noon, right, from the perspective of those who are moving with the wheel. So 12 noon, 12 noon. From our perspective, as we're watching this go by, what do we say? Well, we say that the clocks that are in the front are lagging behind. So that means that the spoke reaches 12 noon here first, but the clock over here has not reached 12 noon yet. It's behind, which means that the spoke must not yet have made the full turn. So from our perspective, what that means is, so I'll draw a rough picture here, and I'll show you more precise ones in a moment. So if I draw the shape of that spoke, then it'll look something like that. It will look bent to us because this guy over here has not yet reached 12 noon from our perspective. It'll take a little while longer. This guy will have to rotate down. That will take a little bit of time. This guy will rotate up in that amount of time. So we will never see straight spokes going from one side of the wheel to another. So let me show you a more precise picture illustrating that idea. So let's look at a bicycle wheel. Ordinary wheel at low velocity would look like that. Let's let it go by at high velocity and see what it looks like. So, that went by a little too fast. So let's slow it down so we can see what's going on. So still high speed, but we'll slow down the animation so we can see it. At high speeds, we begin to see Lorentz contraction, right? It's oval shape, but look at the spokes. The spokes have the kind of shape that I was describing before because of the fact that the clocks in the front are lagging behind the clocks in the rear. Spoke first hits there, and then its other end hits the horizontal position, which means the spokes are bent. So that's a kind of cool idea. You can play around with that in a little animation, or I should say a little demonstration over here, where you can pick the velocity of the wheel. Now it's going in the opposite direction, but it's the same idea. It doesn't matter. And you can pick the number of spokes that you like, all color-coded. So you can see this is a blue spoke, this is a green spoke, and they are all bent, and that effect becomes bigger and bigger and bigger. And if you had one going by at really high speed, the effect would be really significant. So this shows us an interesting example where asynchronous clocks show us that for an object in motion, it's not just Lorentz contraction that comes into play in terms of the distorting effects on the object. The asynchronous clocks come into play too and yield this unexpected feature of a bicycle wheel that the spokes will not be straight from our perspective. One other interesting example where we can make use of asynchronous clocks has to do with the perspective of different observers regarding the temporal order of events. Which events happen first, which events happen second. So let's look at an example. Imagine that we have two firecrackers, and we're told that they are set off 30 feet apart. We are told that from the perspective of, say, the ground frame, that will be the frame of our fearless character, Gracie, we are told that they go off at the same moment, simultaneously. And what we are asked is, if Germain is moving to the right with a particular speed, half the speed of light, George is moving to the left with a speed of half the speed of light, half a foot per nanosecond. The question is, what will they say regarding which firecracker went off first? Again, not a matter of what they see. We're talking about what they will figure out, what they will post-process to learn about what happened from their perspective. Okay, so let's take a quick look at that example. And let me make sure I've got the data of this example straight. So here we have our two firecrackers. And let's write down the data associated with this little scenario. We're told that these guys are 30 feet apart. So let's get that down. 30 feet. And we're told that from Gracie's perspective, these two firecrackers explode simultaneously at the same moment, right? That's with her post-processing. That's what, from her frame of reference, actually happens. Both firecrackers go off at the same moment. We're then asked to work out what happens from a different perspective. So we bring another character, Germain, into the story. And we're told that Germain is moving relative to Gracie, and we're told that her speed is equal to a half a foot, 0.5 feet per nanosecond, which in our approximation that we like to use of the speed of light being 1 foot per nanosecond, this is 0.5 c. And we're told that her motion is that-a-way, to my right, looking at the picture here. So let's put that into the picture as well. So this motion is heading off that way. Okay, that's all we need, right? So from Germain's perspective, right, Germain says, I am standing still and the rest of the world is rushing by me, which in this case would mean the rest of the world is rushing this way, right? She's headed off that way from Gracie's perspective. From Germain's perspective, everything is heading that-a-way. Now that's important because what we have seen is that clocks which are in that direction, in the direction of motion, lag behind. And that's all we need to do to figure out, from Germain's perspective, which firecracker goes off first. So let's label these guys so we can know which firecrackers we are talking about. What should we call these events? Well, let's call this event A. Let's call this one over here event B. And from Germain's perspective, clocks in this direction are lagging behind, which means that firecracker goes off first. That firecracker on the left, A, goes off second. So Germain concludes that B goes off first, then A. That's the temporal order that Germain concludes. In fact, we can go a little further. We can actually work out the time difference from Germain's perspective between when the firecrackers go off. How do we do that? Well, we know that the time difference is going to depend upon the lack of synchronicity between the clocks at A and B. From Germain's perspective, those clocks are not in sync. B is ahead of A. How far ahead is it? Well, we have our nice little formula for that. So the lack of synchronicity between the clocks is gotten by taking the velocity of the frame of reference times the distance between the clocks, delta x prime, in the frame that's moving, divided by c squared. And this, now we can plug in some numbers. So we have 0.5 feet per nanosecond on v. The distance is 30 feet. And speed of light is 1 foot per nanosecond in our approximation. And therefore, working this out, the units work just as we want, and we get 15 nanoseconds as the lack of synchronicity between the clocks at B and A. So for instance, if B is 12 noon when that firecracker goes off, the clock at A will be 12 noon minus 15 nanoseconds behind. Now, we're not quite done in working out the time difference between when the firecrackers explode from Germain's perspective, because if this clock is lagging behind that one by 15 nanoseconds, there's another effect that comes into play, which is these clocks are in motion, so they're ticking off time more slowly. So from Germain's perspective, how long will it take for those 15 nanoseconds to go by? Well, it will take longer by a factor of gamma, the time dilation factor. So we should work that out. So what is gamma in this case? Well, gamma is 1 over the square root of 1 minus v squared over c squared. V is half of the speed of light. So we get 1 minus a half squared, which is 1 minus a quarter in the denominator. So this guy here is 1 over the square root of 1 minus a quarter, which is 3/4. And therefore, this is 2 divided by the square root of 3. And now we take that 2 divided by the square root of 3, gamma, multiply it by 15 nanoseconds, because the clocks in motion are ticking off time more slowly. So our clock will elapse more than 15 nanoseconds in order for A to catch up to B. And multiplying gamma by 15 nanoseconds, you can just work this out, put it into a calculator, and the result you get is 17.3 nanoseconds, approximately. So that is the time difference, according to Germain, between when A and B explode. Good. Second part of the question, well, that's now quite straightforward for us to work out. What about from George's perspective? Only difference. George has the same speed, we're told, half a foot per nanosecond, but rather than moving to the right, he's moving to the left. So now we just take our results and we reverse them. So according to George, it's not going to be that B goes off and then A. Instead, he will say that A goes first and then B. Because again, from George's perspective, if he's traveling that way, he says the rest of the world is actually traveling this way, which means clocks in the front are lagging behind. B is lagging behind from his perspective. And then the exact same calculation tells us that the time difference between these is the same, 17.3 nanoseconds. And again, it's good just to compare this with where we started. We said that according to Gracie, these two firecrackers explode at the same time. They are simultaneous from her perspective, whereas Germain says that B explodes first, then A, and George says that A explodes first and then B. And let me emphasize, this is not some kind of optical illusion. This is not an issue of human perception. Each of these individuals is correctly calculating the reality of what happens from their perspective. And we see that asynchronous clocks are vital to understanding of how these three individuals come to a different understanding of the order of events. So again, we have found Gracie says A and B, they go off at the same time. Germain says B goes first, then A. And George says A goes first, and then B. Different description of the same events, different understanding of the temporal order of what unfolds. Okay, let's look at one more example of an application of asynchronous clocks in a moving frame of reference. And in many ways, this is the most important example in this module. I mean, all of the examples are important, but this one really has a chance of clarifying for you an issue that is very confusing when you first encounter time dilation, which is this. In time dilation, we learn that if I am looking at a clock in motion, I will conclude that that clock ticks off time more slowly than my watch, than my clock. Good. Okay, that's all straightforward. The confusing part, however, is if we now put ourselves in the shoes of the person that was moving. They look back at my clock. They say that I am in motion, and therefore they say that my clock is ticking off time more slowly than their clock. And the tension, the logical tension is, how can both of these perspectives be correct, right? How could it be that I can say that your clock is ticking off time slowly, and you can look back at me and say that my clock is ticking off time slowly, and yet we're both correct? No contradiction. Well, there is no contradiction, but I want you to see now how we can resolve that apparent tension. And I'm going to do so in the context of a little example. So let's imagine that we have a situation where, let's imagine that our character Gracie, well, let me just go back to the video. Our character Gracie is doing a skateboard time trial, right? So she's timing how long it takes for her to go from the starting line to the finish line, and George is doing that timing too. And we want to compare the amount of time that each will claim that that journey took. And to do that, let's set up a little chart over here that will help us to keep track of all of our results. So the upper two panels here are going to be from George's perspective. So let me just mark that so we can keep this all straight. So we're going to look from here to here. This is going to be George's perspective. And what I want to do is fill in the times on all of these clocks that each will claim for the amount of time that elapses from, say, the start. This is the start of this time test, and this is the finish. And after I do this from George's perspective, I'll do the same thing from Gracie's perspective, and we'll compare what we find. OK, so to put numbers in, let me assign a certain velocity to Gracie. So I'm going to imagine that she's going to travel along pretty quickly at 12/13 times the speed of light. Quick for a skateboard, but it will be good for our purposes. And let me also note that the length of the track, I'm going to pick a particular length for it from the starting line to the finish line. I'm going to choose that just so that the numbers work out well. I'm going to choose this to be 156 light minutes. So that's how long it would take light to go from the starting line to the finish, 156 minutes. Now let's work out from George's perspective how long it takes Gracie to go from the start to the finish. That's pretty easy for us to do. So delta t for this race, this time trial, according to George, is just going to be distance divided by speed. So that's 156 light minutes divided by the speed, which is 12/13 the speed of light. Speed of light is 1 light minute per minute. So if I want, I can keep these units here for just a moment. And dividing through, I get 169 minutes. So according to George, therefore, at the start of the race, Gracie's clock reads 0. His clock reads 0. And this is his teammate's clock at the finish line, not moving relative to George. So in the same team, and therefore, according to George, this will also read 0. And our little calculation tells us that George will say at the end of the race, to finish, 169 minutes will have gone by on his team's clocks. OK, straightforward. Now let's work out from George's perspective how much time will have elapsed on Gracie's clock. How do we do that? Well, according to George, the amount of time that goes by on Gracie's clock, it's going to be less. It's a clock in motion. It ticks off time slowly. How much less? Well, we take the 169 minutes, and we divide through by gamma. Now, what is gamma for v equal 12/13 c? Well, you can work that out, or simply remember that for those numbers, it's 13 divided by 5. So we can just put 13 over 5 here. And then dividing through 13, 5, 65 minutes. So according, therefore, to George, this clock over here, Gracie's clock, will read 65 minutes by the time she crosses the finish line. Now let's do the same calculation, but from Gracie's perspective. So what is Gracie's view? Her perspective is the following. So first off, Gracie says that she is stationary, and it's the rest of the world that's rushing by her, which means that the distance between the starting line and the finish line, according to Gracie, will be Lorentz contracted. It is a track in motion, so from her perspective, it is shorter. So therefore, when she calculates delta t for this time trial from her perspective, she does distance divided by speed. What is the distance? Well, she takes the 156 light minute distance. She divides that by gamma. That's the Lorentz contracted length of this track. And she divides that further by the speed. Now, you could call it her speed, but more precisely, it's the speed with which the track is rushing by her. And that is 12/13 times the speed of light. So putting those numbers in, remembering that gamma is equal to 13/5, then we'll be left with, we'll have a 12/13 cancels against the 12/13. You'll have 5 times 13. And indeed, you find 65 minutes, just as George found. So what Gracie is therefore saying is that from her perspective, her clock begins at 0 at the start of the race. So let's mark that again from her perspective. And at the end of the race, it's 65. So that's good. So George is saying 65. She's saying 65. No contradiction. But here's where the tension comes into the story. Because if Gracie now calculates the amount of time that she says, so slightly non-standard notation here, so let's just follow it. This is the amount of time that Gracie says elapses on George's clock. She says that his clock runs slow, and therefore less time will elapse on his clock than on hers. So she takes the amount of time that elapsed on her clock, 65 minutes, divides through by gamma. Again, that's 13/5. And what do you get here? So the 13 goes in here 5 times, times 5. So you get 25 minutes. So at the end of the race, right, when the race is finished, what this is telling us is that according to Gracie, George's clock, which she agrees started at 0, as her clock did, will read 25 minutes at the end of the race. And that's where the tension comes from, right? So according to George, at the finish, his clock will read 169. According to Gracie, it'll only read 25 because from her perspective, it's taking off time more slowly than her own clock, which she says will read 65 minutes at the end. So how do we resolve this problem? Well, as I mentioned at the outset, it all comes down to asynchronous clocks. What do I mean? Well, let's go back to the start of the race, according to Gracie, right? From Gracie's perspective, this race starts, and from her view, Team George is rushing this way, right? She's stationary. From her perspective, Team George is rushing this way, which means from her perspective, this clock will not be in sync with that clock. This clock will lag behind. It's in the front of the motion, in the direction of the motion. This clock, therefore, will be ahead. How much will it be ahead? Well, we can calculate it. We know how to do that. So the time difference comes from taking the velocity, which is equal to 12/13 c, multiplied by the distance between the clocks in Team George's frame itself, which is 156 light minutes, and dividing that by c squared. What do I get from that? So 13 into 1/5 is 12, 144. 144 minutes, which means that according to Gracie, this clock in Team George's frame doesn't read 0 at the start of the race. Instead, it reads 144. It starts ahead. Now, if it starts at 144, that means if we add over here 144 to the 25 that she claims George's clock reads at the end. Again, this is going to be now 144 ahead of 25, and that gives us 169. So, according to Gracie, this clock in George's frame of reference will read 169, exactly what Team George said from their perspective. So everything now works out perfectly well. So just to summarize what this gives us, we find, therefore, that according to George, it takes Gracie 169 minutes to cover the track. However, George says that Gracie's clock runs slow, and therefore, on her watch, only 65 minutes will go by. What does Gracie say? Well, as we calculated here, she says, indeed, 65 minutes do indeed go by on her watch, but she says that George's clock ticks off time slowly, and only 25 minutes will go by. So there are three interesting times on the board: 169, 65, and 25. And in order to bring everything into cohesion, consistent results, we now take into account this final fact over here, that according to Gracie, George's clocks are not in sync. That clock is 144 minutes ahead of this clock, and we take that into account. 25 minutes go by on Team George's clocks. This guy didn't start at 0. He started at 144, so it ends up at 169. So as Gracie crosses the finish line, her watch says 65, and George's clock at the finish line, the clock in Team George at the finish line, reads 169. Everybody agrees on what those clocks say. So the difference, therefore, between this 169 and this 25, from Gracie's perspective, that's nothing but the relativity of simultaneity realized in the context of asynchronous clocks. Bottom line, George says that Gracie's clock runs slow. Gracie says that George's clocks run slow, but for everything to be consistent, the asynchronous nature of clocks kicks up this clock at the finish line, starts at 144, and therefore finishes at 169, just as Team George claimed. That is the way that you can have two individuals in relative motion each claim that the other's clock is ticking off time slowly, and there's no contradiction. Because the only direct comparison that Gracie can make is with Team George's clock at the finish line. And indeed, everybody agrees on the data at the finish. George says 65, 169, and Gracie says 65, 169. It all works. It all hangs together. So that's this beautiful way in which asynchronous clocks avoid any tension that you might have thought there would be between each individual claiming that the other's clocks run slow. That is a perfectly sensible situation so long as you take into account this asynchronous nature of clocks in the moving frame. Now, finally, we're going to complete the task that we set ourselves to find the mathematical formula that will relate the space and time coordinates of one set of observers that we are calling team platform to the space and time coordinates for another set of observers, the ones that we have been calling team train. Okay, so how are we going to do this? We basically have all the ingredients in place. But let me start by asking a leading question that will push us right into the calculation we want to do. If it were Isaac Newton who was trying to set up a dictionary between these two frames of reference, what would he say is the mathematical formula? And that's something that we can directly work out. So let's set up the situation. There is team train, the blue frame. There is team platform. At the origin, they set their clocks so they're in sync with one another, and then the blue frame continues onward. And what we want to do is focus our attention on one particular point that I will call the point P over here. And the point P is at the coordinate x prime in team train's frame of reference. Where is P from the perspective of team platform's coordinates, according to Isaac Newton? Well, the first thing is, when Newton approaches a situation like this, he assumes that time in the train and time in the platform are the same. In fact, he doesn't even address that question. It was just so obvious back then that there was one notion of time that worked for everyone that it went without saying that you didn't have to set up any kind of fancy dictionary between the time in one frame and the time in another. Good. So we have disposed of that part of the story. But what about the position of that coordinate? Well, we can dispose of that pretty quickly too. Because what Isaac Newton says, he says, look, the distance that the blue frame has traveled in an amount of time t, that of course is v times t. And therefore, if you want to figure out where this point is in team platform's coordinates, you just now need to take v times t and add to it x prime, which is the distance according to the blue frame and the red frame between the origin and the point P, to get the total x equals x prime plus vt. And there you have it. That is the dictionary that Isaac Newton would set up between team train and team platform. Now, we recognize that this is not right because there are significant subtleties that Einstein and relativity bring into the story. First of all, clocks in team train from the perspective of team platform are not in sync, and vice versa. We also know that time is dilated. So if we're in team platform, looking at team train's clocks go by, they are ticking off time slowly compared to our clock. So you can't just do this t equals t prime business any longer. And finally, of course, lengths are contracted. When we look at team train, the distance between points shrinks as a function of the velocity of team train. We need to take all of these effects into account. Let's do it. Let's work it out. Let's update the dictionary that Isaac Newton would give to us. Okay, now, to simplify things, we are always going to assume that as the train frame passes by the platform frame, the clocks at the origin in each frame are both set to 0. That's how we begin when the origins cross. We don't have to do that, but by setting the origins equal to one another, it just makes life a little bit easier. So we're going to do that. And we're going to, again, focus on an arbitrary point called x prime in the moving frame. And we are going to work out where it is at time t in the platform frame, making use of all of those effects. OK, so here's our setup. there is the blue frame, team train going by, and there is the flash of light that the blue frame uses to set up its clocks. But at the moment, let's focus on the spatial part, not on the temporal part. OK, so let's take into account all the corrections that we just noted that Isaac Newton was not aware of, but we are. OK, so how does that go? So first off, let's make use of our understanding of Lorentz contraction to say that the distance from here to here is not actually x prime, but instead this is x prime divided by gamma. OK, we have to take that into account. Let's do what Newton did as well in terms of understanding how far team train has moved in an amount of time that is equal to t from the platform perspective. And if the amount of time t has gone by, according to the platform people, then velocity times time will give us how far the blue system has moved over to the right. And using that, we now can say that the distance from the origin in team platform, so let me do this a little bit cleaner now. So from the origin to this location over here, according to the platform folks, we have vt over here. We have to add to it x prime over gamma. So if you put those both together, we now have x, the location of that point from the perspective of those in the platform frame, is equal to x prime over gamma plus vt. And oftentimes we like to simplify, not really simplify, we like to solve for x prime. It's a cleaner looking expression, so let's do that. Multiply, let's subtract this guy off from the other side, so we get x minus vt, and then let's multiply that by gamma. And this over here is therefore equal to x prime. So x prime is equal to gamma times x minus vt. So let me record that over here. X prime is equal to gamma times x minus vt. That is the relationship that we find. That's worthy of boxing up, because this is 1/2 of what we are looking for. This is 1/2 of the Lorentz transformation. Now let me point out, as long as we have this over here, that I could, of course, solve this one too for x prime. So x prime is equal to x minus vt. That's what Newton would say. And now we see that the difference between Newton and Einstein is a factor of gamma, the famous factor that we have encountered over and over again. So the dictionary between the two when we come to space is just a factor of gamma different. Now we will turn to relating the time part of the coordinate systems. Now let's turn to the second half of the Lorentz transformation equations. Let's work out how time in one frame looks to time in the other. And let me just stress at the outset an obvious at this point, but very important point, which is there's no meaning to talking about relating the time of the platform frame to the time of the train frame, because the clocks in each frame are out of sync from the perspective of the other. So team train says there isn't a single time for team platform. Team platform says there isn't a single time for team train, because all the clocks are out of sync relative to one another. So instead, the calculation that we're going to do is to relate the time t of team platform. From team platform's perspective, they have a single time. That's fine. But we're going to relate that time to the time t prime in the moving frame at the location x prime, because you need to specify where the clock is that you are talking about, because the clocks are out of sync relative to one another. So let's do that calculation and see where it takes us. Do it over here. Set up a little worksheet here. So when the origin of team train coincides with that of the platform. They both set their clocks to time 0, and that's the moment when, for instance, each sends out a flash to synchronize their clocks. So from the get-go, we are assuming that the origins cross, so let's record that. So we have t equals t prime at the origin. These guys coincide when they both are equal to 0, when the origin of this guy and the origin of that guy just pass one another. They flip the switch, both clocks read 0, and then they tick forward. OK, that's how we're setting things up. Now, what are the key equations that we need? So first off, we know that the time t from the platform perspective that elapses, that number is always going to be bigger than the amount of time that elapses in the train frame, and it's bigger by a factor of gamma. Gamma always bigger than 1. So we know that this is the relationship between the time that will register on this clock and the time that will register on that clock. They're both agreed, but then this one ticked off time more slowly, right? So this will always be bigger. So if that reads 3, this will read 3 times gamma. That's the relationship between those clocks. Good. We also know that the reading on this clock stands in a very specific relationship to the reading on that clock. What is that relationship? This guy is in the front, and therefore this guy is always going to lag behind. Asynchronous clocks, right? We've worked out, in fact, the amount of the asynchrony. Let me remind you of that relationship. So the time t prime on the clock x prime will lag behind the time t prime on the clock at the origin over here by an amount that's given by the velocity v times the distance between them as measured in team train. That's where x prime comes into this equation over here, divided by c squared. OK, that's nice, because now we can solve this one for the time t prime at the origin is equal to t prime at x prime plus vx prime over c squared. And now I can take that equation and put it into this one over here, and we have the time t, and again, this is the t for the platform frame, is equal to gamma times t prime at x prime. I'm not even going to bother writing that. We'll just assume that if there's an x prime in the formula, it means that we're talking about the time on the clock at x prime in that equation. And this is basically what we were after. It's in a form that's not quite as convenient as we'd like. I'd rather this be in a form that mimics what we have over here, right? So here we have x prime in terms of x and t. I'd like that one to be in the form of t prime equals something in terms of x and t. But that's easy to do because we recognize that team train can equally well claim to be at rest with team platform moving in that direction with speed v. If it's moving that direction with speed v, we can use the same equation where we interchange the roles of platform and train. So let me interchange the roles. Let me call this t prime equals gamma and t. Now v becomes minus v from the perspective of team train, and x prime, changing the roles of who is stationary and who is moving, x prime becomes x, and that therefore is the relationship between t prime and t and x. And indeed, that is the second half of the Lorentz transformation equation. So to summarize where we've gotten then, we've now derived a formula where given x and t, we can figure out both x prime and t prime. We have a nice systematic dictionary for doing that. And that dictionary is x prime equals gamma times x minus vt. That's the one that we derived over here. And t prime is equal to gamma times t minus vx over c squared, the one that we have derived over here. And collectively, these two equations are known as the Lorentz transformation. That is the dictionary we were after. You now give me x and t in the platform frame, and I can give you t prime and x prime in the moving frame of reference. Okay, let's get a little feel for this, as we always like to do, by playing around with a little demonstration. So in this demonstration, you, the user, get to pick the values of t and x for some event. So choose whatever values you'd like. Choose the speed v of the moving frame of reference. And this little demonstration, if you see right down here, if you can come in real close, these are small, come in real tight on this guy over here, you see that as I vary the velocity, this factor in front is changing, that's gamma changing. The factors inside are changing wherever the v's appear in the Lorentz transformation formula, and we are getting the final result over here for t prime and x prime for given values of t and x. So in essence, what we have done now is found a turn of the crank, a mindless approach where given when and where something happens in one frame of reference, we can figure out when and where it happens in another frame of reference. And all of the effects that we have discovered through diligent effort have been included in this formula. We have in there the relativity of simultaneity, right? The clocks are out of sync. We have time dilation. Gamma is there all over the place. We have Lorentz contraction. That came vital into our calculation of the relationship between x prime and x. It's all been packaged in a general systematic formula. And what that means is, in some sense, you don't have to think any longer. Now that's good and bad. It's good to think, right? It's good to struggle with these ideas and really parse through in your mind what are the physical features, what are the effects that are driving the relationship between one set of observations and another. But you know, after a while, you want to just be able to get to the answer. And when you get to that stage, especially when you don't want to make a mistake and leave out some vital effect, the Lorentz transformation becomes a very powerful tool. You just plug in and turn the crank. As this demonstration shows, you can just have a computer program that turns the crank for you. So now all this wondrous physics has been packaged in a simple set of mathematical formula. That is what the Lorentz transformation gives us. So we now have the Lorentz transformation equations in hand. That's good. That's exciting. Let me give you a couple of notes, a couple of observations, extensions of these ideas that are worthwhile to keep in the back of your mind before we head onwards. So, observation number one. I have only spoken about x and t and x prime and t prime. Poor y and z haven't had any role in anything that we have discussed. And the reason for that is we've been looking at motion just in one dimension, so y and z basically just come along for the ride. And that means that if I write out the Lorentz transformation equation, including y and z, and y prime and z prime, the additional two equations are pretty simple. Y prime equals y, and z prime equals z. There's no change in the y dimension from team train to team platform. Similarly, z prime and z. So if we were to extend, that is, team train and team platform, to have a y and a z, and a y prime and z prime, they would just come along for the ride. Okay, note number two. I've pretty much already made use of this in the derivation, but what you call team train, what you call team platform, is a matter of perspective, in that team train can claim to be at rest with team platform moving, or vice versa. And that means that the equations we derived must have a simple incarnation from the other reference frame's perspective. And indeed, we already have indicated what that is. So if the relationship between t prime and x prime and t and x has a minus sign where the v is concerned, it's going to be a plus sign if you go to the other frame of reference, because from their view, the other frame is moving in the opposite direction. That's the only change. So to go from t and x to t prime and x prime, that is the equation that you use. Again, y, z, y prime and z prime just coming along for the ride if we're just moving in one dimension. Another point that's worth emphasizing is that you can make the Lorentz transformation equation look a little more symmetric if, instead of framing it in terms of t and x, you use c times t and x, right? So the speed of light, we choose these clever units where it's equal to 1. That can obscure the symmetry that's inherent in these equations because ct has the units of a length. It's a velocity c times a time. That's a length. And so if you frame the Lorentz transformation in terms of ct, that's a length, and x, which is also a length, there's a chance that the equation looks more symmetric between them, and indeed it does. So just throwing in factors of c in a way that keeps the equations the same, notice now that ct and x are playing exactly the same role. They're just interchanged from one equation to the other. If you like to think about transformations using matrices, which are the way that we can describe linear transformations, you can do that as well with the Lorentz transformation. So sometimes you'll see the Lorentz transformation in this form, where we look at a column vector which has ct, x, y, and z. And given that, the transformation between the two has this nice, simple matrix form. Final point is this. I showed you some fun animations early on where we had clocks at every grid point in a three-dimensional space. And we had three-dimensional grids of clocks moving through other three-dimensional grids. But then I said, those pictures may be nice, but we're not going to work with the full three-dimensional examples most of the time because it's a little complicated. And as you see, we've only focused on these one-dimensional examples over here, but yet it's really rich, right? We've been able to come to these surprising conclusions about space and time. Having said that, it's nice to at least see once in your life what the Lorentz transformation looks like if you do allow motion in a full three-dimensional space and you take account of x, y, and z for both the stationary and the moving frames. Here is what the Lorentz transformation looks like in that case. So to make the formula a little bit easier to read, we introduce this notation beta. So beta x, beta y, and beta z, the ratio of vx to c, vy to c, and vz to c. And in terms of that motion, if that is the motion of the moving frame, then the relationship between c, t prime, x prime, y prime, z prime, and ct, x, y, and z takes this form. Now do you understand why we didn't do the three-dimensional case? It's a pretty complicated looking formula. You can derive it. It's not actually that hard to derive. We don't typically make use of this in many of the calculations because it becomes unwieldy, but nevertheless, it's good to see that you can do it, and this is the way in which the space and time coordinates in the moving frame relate to those in the stationary frame if the two frames are moving with that velocity vx, vy, and vz. Now, that is a complicated formula to actually deal with analytically, but of course, you can program a machine to do the work for you. And in this demonstration that you'll play with on your own, the full three-dimensional Lorentz transformation is taken into account. So we imagine in this demo that we have a torus, a donut, if you will, and we're going to ask ourselves, what will the donut look like from the stationary frame if it is moving with a velocity that now can be through the full three-dimensional space? So you get to pick the direction that this guy is going to be moving by moving this around in this space. And you can pick the magnitude of it, not just its direction. And by moving this around, you can see that the donut can take on a variety of interesting shapes based upon the motion that the frame of reference that it is stationary in, the frame of reference that is moving relative to us, that is, causes the object to have a distorted look. So it's fun to play around with this. It's using the equation that we have up there on the board. It's a little bit involved to work out by hand, but there you have it. That's the impact of the full three-dimensional Lorentz transformation. Before the review that we have at the end of every module, I want to give you a kind of overarching summary of where we have now gotten. Okay, so what we have found is that we should think about reality in the following way. So reality is nothing but a collection of events, right? So firecrackers explode, races begin, objects fall. They're a collection of events. Now, remember, what is an event? An event itself is nothing but something that takes place at one single location in space and at one single moment in time. And of course, that's why we like to talk about firecrackers exploding and guns firing, because it really intuitively gives you that sense of it happening at one moment in time. But think about reality as just a grand collection of events, which are things that take place at one particular position in space, one moment in time. So if you want to make a list, therefore, of what constitutes reality, well, we can make a little table, if you'd like. And why don't I make this sort of neat for us here? So let's imagine that I have a little chart like this. And let's say I've got, well, let me, while I'm at it, put this guy over here too. Extend this guy a little bit. So imagine, therefore, that I have event number 1. It can be, say, a gun firing or a firecracker exploding, whatever. Some event number 1, some event number 2, some event number 3. And in principle, I could list out all the events that constitute reality. It would be a pretty long list, but this is, in principle, how I could delineate what comprises reality. Now, when I look at these events from the perspective of two different observers, let's look at them from the perspective, say, of Team Platform and the perspective of Team Train. Team Train and Team Platform will all agree on the events themselves. Every observer agrees on the events. The only way that they differ is in where and when each of them says that the events take place. So Team Platform might say event number 1 took place at T1, X1, and say event number 2, perhaps they say it takes place at T2, X2, and event number 3, say at T3, X3, and we could keep on going if we wanted to. Team Train will assign its own space-time coordinates to those events. So Team Train might say that this event number 1 happens at T1 prime, X1 prime, T2 prime, X2 prime for event number 2, and say T3 prime, X3 prime for event number 3. They all agree on the events. They just don't agree on when and where those events take place. And what the Lorentz transformation gives us is a simple, comprehensive mathematical dictionary that allows us to translate from the space and time coordinates according to one observer to the space and time coordinates according to another observer. That's all that the Lorentz transformation is. So the result that we have found is that T prime is equal to gamma times t minus vx over c squared, and x prime is equal to gamma times x minus vt. So if you know the t and x coordinates for a given event, you can use this transformation to fill out this table, and vice versa, using the inverse Lorentz transformation that we wrote down, where interchange the primes and unprimes and change the sign of the velocity, because from Team Train's perspective, Team Platform is moving in the opposite direction. This is all that the Lorentz transformation is. And again, the physics behind this transformation is nothing but the ingredients that we have carefully painstakingly derived, right? Time dilation, Lorentz contraction, and asynchronous clocks. So the second thing that I'd like to do in this little wrap-up of Lorentz transformation is just show you how to get Lorentz transformation and time dilation and asynchronous clocks from the Lorentz transformation itself. Since we use those ideas to get this result, we should be able to extract them back out, and it's straightforward to do that. Now, to do that, let me also bear in mind that I'm assuming, as we always do, that Team Platform and Team Train, that their origins, the space-time origins, agree, so that when t and x are both equal to 0, t prime and x prime are both equal to 0 too. And I mention that because really the right way of thinking about this Lorentz transformation is in terms of the coordinate differences. But when an event takes place at that space-time location, and you're looking at its coordinate distance from the origin, or more precise, I should say, the coordinate difference, not distance, coordinate difference from the origin, I would just be subtracting off 0 and 0, so don't bother writing it down. But the general result that we have seen, you will recall, is that I can write delta t prime is equal to gamma times delta t minus v delta x over c squared, where now I'm looking at the space and time coordinate differences between two events. It could be two of the events that I have on the board here. And delta x prime is equal to gamma times delta x minus v delta t. And for good measure, let me put down the inverse transformations just so that we have them on the board here. So delta t is equal to gamma times delta t prime plus v delta x prime over c squared. And delta x is equal to gamma times delta x prime plus v delta t prime. OK, good. That's worthy of a little box, just so that we have it right in front of us. OK. Good. Now, let's use this to just see where Lorentz contraction and time dilation and asynchronous clocks arise in this little formula. It will just take us a moment. So let's do number one. Let's look at time dilation. So the canonical situation is I am looking at a clock that's in motion, right? Now, if the clock is in motion, in its own frame of reference, which would be the prime frame of reference, delta x prime will be equal to 0. Now, if delta x prime is equal to 0, I can use this little equation over here and write delta t is equal to gamma times delta t prime. And notice that because delta x prime is equal to 0, this term over here drops away. And that's the result I have. And there you have it. That is time dilation. The amount of time between two events on my clock will be bigger than the amount of time in the moving clock by a factor of gamma. So manifestly, we have now extracted familiar time dilation from the Lorentz transformation. OK, let's move on and look at length contraction or Lorentz contraction. How do we pull that out? Well, it's as easy. So in the canonical example of Lorentz contraction, I'm looking at an object in motion. And what I do is I measure its front and its rear at the same moment in time, right? So that means the separation between those two measuring events, delta t is equal to 0. I measure the front and the rear at the same moment in time. Now, I also know in these canonical examples that delta x prime, the length of the object, according to those moving with it, is the rest length of the object, L naught. What do I measure using the Lorentz transformation for the length of the object itself? Well, which formula shall I use? Let's use formula number 2 over here, because delta t is equal to 0. That will make that a particularly nice formula. So we find delta x prime is equal to gamma times delta x. And I don't have to write anything else down, because again, come in over here, delta t is equal to 0. And now if I just solve for delta x, the length that I measure, I get delta x prime divided by gamma, which is equal to L naught divided by gamma. The length I measure is contracted by a factor of gamma. So there we have length contraction or Lorentz contraction, again, coming right out from the Lorentz transformation equations. And just for good measure, let's finish this up and talk about asynchronous clocks in the moving frame of reference. So how does this work? Well, again, canonical example. I'm looking at clocks in a moving frame of reference, and I look at two of those clocks at the same moment in time from my perspective, simultaneously from my perspective. So again, that means that delta t is equal to 0. That looks like a delta gamma. Sorry about that. Let me just clean that up a little bit for you. So delta t is equal to 0. That looks better. Now, with delta t equal to 0, let's use this third of the Lorentz transformation equations. So if you zoom in on here for a second, if delta t is equal to 0, I can take the gamma, immediately divide it through, and therefore just set delta t prime plus v delta x prime over c squared equal to 0. So let me just do that over here. So this tells me, therefore, that delta t prime plus v delta x prime over c squared is equal to 0. And therefore, I conclude that delta t prime is equal to minus v delta x prime divided by c squared. And you will recognize that as telling me that there is a difference in the readings of the clocks in the moving frame of reference that is given by the velocity of the frame of reference times the distance between the clocks as measured in that frame itself divided by c squared. And you will recall that is exactly the formula that we have derived earlier, that we have been using for the asynchronous nature of clocks in the moving frame of reference. So the bottom line is we now see how all those familiar features that we have derived over the course of the previous modules are completely embedded in these Lorentz transformation equations. You can pull them out by carefully applying these equations. And indeed, these equations are nothing but an encapsulation of those ideas. So when you look, for instance, at an equation like this, right? If you focus in here for just half a second, you see right away, in fact, let me use this one over here instead. You see right away that this term over here is nothing but the time dilation factor, and this term over here is nothing but the asynchronous clocks in the moving frame of reference. That's what that formula means. Every time you see that formula, I want you to think about these physical features. When you see that gamma, time dilation. You see this v delta x prime over c squared, just don't think of it as a formula. Think of what it means. This is the asynchronous nature of the clocks in the moving frame of reference. And similarly over here, in this formula, it's better actually to divide this through by gamma. In fact, let's use this one, the one that we used before. So if you think about this as delta x prime over gamma, that is Lorentz contraction. That's length contraction. And the remaining term over here, delta x minus v delta t, that's just the usual Galilean motion of one frame relative to another. So the reason I'm emphasizing this is I don't want you to look at these equations just as mathematical symbols. Every time you see them, think about the underlying physics that is embodied in those equations. Nothing but time dilation, Lorentz contraction, asynchronous clocks in a moving frame of reference. And collectively, it all is just, again, telling us reality, collection of events, different observers assign different space-time coordinates to those events. They all agree on the events. They don't agree on where the events happen or when they happen. And the Lorentz transformation equations give us the dictionary to go from one to another. That's what this is all about. We now have the Lorentz transformation equations at our disposal. We've derived them. Let's put them to work. Let's see how to use the Lorentz transformation equations in a couple of concrete examples. First example, I'm going to apply the Lorentz transformation to our friend the light clock, right? We've not seen the light clock in a while, but it provides a nice little example to show how these equations work. So there it is. There's our light clock. we have the bouncing ball of light, starts on the bottom mirror, bounces up, and reaches the top mirror. And let me do a little bit of analysis on this. And what I'd like to do is figure out from the perspective of team stationary what the relationship is between where the ball of light begins and ends, its tick-tock motion, from their perspective compared to that of a person moving with the light clock itself. Okay, so how do I set up that question a little bit more mathematically? This is the prototype that we always will do in the Lorentz transformation equations. We are going to first fix on the events of interest to us. So what are the events? Well, let's call them event number 1 and event number 2. And in this particular case, they are simply that the light ball hits the bottom mirror. That's what happens at the very beginning of this episode over here. So it hits the bottom, and then the second event is going to be that the light ball hits the top mirror. So I'm not going to worry about what happens to the right of this moment. I'm only concerned with event number 1 and event number 2. Let's write down the coordinates from the perspective, say, of team moving, right? So team moving is holding on to the light clock, so they are moving with it. So what do they say? Well, from their perspective, of course, let's again choose our time to be optimal to the problem. So we're going to say at t prime and x prime equals 0, 0. That is where this event takes place from the perspective of team moving. So we'll say t1 prime x1 prime equals 0, 0. Okay, what about event number 2 from their perspective? Well, from the perspective of team moving, of course, the light clock is staying at a fixed location, right? They're moving with the light clock. So from their perspective, the x-coordinate of the clock is not changing. And how long does it take? Let's say it takes 1 unit of time, say 1 second, for it to go from the tick at the bottom to the tock at the top. And therefore, we'll call this 1, 0. So this will be 1, 0, according again to team moving. Let's now use this data to figure out what the space-time coordinates of these events are according to team stationary, right? So team stationary, and we don't have to think about it at all any longer. We don't have to think about time dilation or clocks out of sync or length contraction. It's all built into the formalism, all built into the equations. So what do we do? Well, we're going to assume, as always, that the origins of these guys line up. So we're both going to claim 0, 0 as the space-time coordinates for this initial event. But we want to work out what team stationary says about the second event. Where do they say it happens, and when do they say it happened? Let's just plug into our equations. And to do that, I'm going to need to specify, of course, a speed for the clock. And let's choose that speed to, say, be v equals 4/5 c. And of course, I choose that because if I then calculate gamma associated with that, gamma is 1 over square root of 1 minus v squared over c squared. So we'll get 1 minus 16 over 25, which is 5/3, a nice number to work with. So we can now write out our equation that x for the second event is going to be equal to 5/3, that's gamma, times x prime, which is 0. And we have to add to that plus 4/5, which is the velocity, times t, which is 1. That is, I should say, t prime is equal to 1. So here, this guy has come into the equation over here. Here is v times t. And therefore, without thinking, we know that the event upstairs took place at 5/3 times 4/5, which is equal to 4/3. So in the coordinate system that's stationary, this will happen at the location coordinate 4/3. What about the time? Let's again plug in. So t, we know t is equal to gamma times t prime plus vx prime over c squared. That's the formula we derived. Now we're just going to plug into that. And again, I will always choose units where c equals 1, so I don't really have to worry about it at all. So 5/3 times 1, so there's our t prime, plus vx prime over c squared, but x prime for this guy is equal to 0, so that just gives us v times 0, which is 0, and the result we get is 5/3. So whereas t moving says the space-time coordinates of this location are 1, 0, we've now calculated that the same event, according to team stationary, takes place at 5/3, comma, 4/3. And again, the beauty, or the pitfall, depending on how you look at it, is that we got this result without having to think. We already now have length contraction issues and asynchronous clocks and time dilation. It's all built in, and we're able to just turn the crank and get the answer. Let's take a look at another example of the Lorentz transformation equations in action. This one is particularly fanciful, where we are envisioning that the year is 2887 way in the future, and the Chicago Cubs have won the World Series. So bear with me. I know that's fanciful, but it's worth it for the little example. So, and they were playing the Yankees, and what are we told? Well, we're told that they are celebrating by firing a cream pie from home plate toward their ace pitcher at 4/5 the speed of light. He's being doused with champagne 40 feet away. Therefore, it hits him 50 nanoseconds later, right, because he's 40 feet away, and it's going 4/5 of the speed of light. The Yankees, who lost the game, are getting out of town. They are traveling at 3/5 the speed of light, and they happen to be traveling exactly the same trajectory that the cream pie is following, going from home plate toward the pitcher. What are we asked to figure out? We want to know where and when do the Yankees say that the pitcher gets hit by the cream pie. Okay, so that is a pretty long-winded way of setting up this problem, but let's take a look at it and see what we get. Let me just draw it so that you don't have to keep thinking through what we have found in the description of the problem. So what is it? So we have over here, we've got our home plate, we've got our pitcher over here, and we have our projectile, which is this cream pie thing, which is heading off in this direction. And of course, we have the Yankees frame of reference, which is moving off to that side too. Let me indicate that a little bit more clearly, so that the Yankees are moving along this direction, and we're told that they are heading out of town pretty quickly. They're going at 3/5 the speed of light. This guy is going at 4/5 the speed of light. So what are the relevant events in this particular case? It's always good to set it up this way. So event number 1, the relevant event there is that the pie is launched. And of course, relevant event number 2 will be that the pie hits the pitcher, right? Those are the two events of relevance to the problem that we're looking at here. And let's write down some coordinates. So from the perspective of those in the stadium who are not moving, the stadium coordinates, let's just set things up as we always do, so that the time of the first event and the position of the first event are simple. We put those at the origin of our coordinate system. And we'll also do that for the Yankees as well. So they're flying away at 3/5 the speed of light, but we'll make sure that the origins all coincide. So t prime 1 and x prime 1 will also be equal to 0, 0 for the Yankees. Now, let's write down the coordinates for event number 2, the pitcher getting hit. So that's T2 and X2. It reaches the pitcher 50 nanoseconds later, and the pitcher is, we're told, 40 feet away. So if I include the units in, might as well do that. And the question that we are asking ourselves is, what, according to the Yankees, are the time and position of that second event? So this is what we are trying to figure out, and that's something that we can now do by just plugging into the Lorentz transformation equation. In fact, let me just do it up here so I don't have to bend as much. So what do we have? So we have T2 prime. We know that's equal to gamma times, and I'll work out gamma in a moment. So that's times 50 nanoseconds. So that's the value of T2. And we are told you subtract from that Vx over c squared. So x is 40 feet, and the speed is 3/5 c. So that's Vx divided by c squared. And we know what gamma is because the Yankees have a velocity of 3/5. So gamma is 1 over the square root of 1 minus 3/5 squared, 9 over 25. And that gives me 16 over 25 square root. Flip it upside down. That gives me 5/4. So that then tells me that T2 prime is equal to 5/4 times 50 minus 120 over 5. And all this is in nanoseconds. So if you just plug that in to crank out the numbers, well, let's just do it. So this is 5 times 250 minus 120 is 130. And then the 5's cancel, and you have a 4 on the bottom. So we have 130 divided by 4 nanoseconds. So that is the answer for the first question mark, 130 divided by 4 nanoseconds. What about for the second question mark? So x2 prime, that's equal to gamma, 5/4, times x minus vt, and x in this case is 40 feet, minus, that's a 40, not a 6, so 40 minus v, 3/5 c, times t, which is 50 nanoseconds. And what does that give us? So that gives us, if we pull all those factors together, I'll leave you to check the arithmetic, but that gives me 50 divided by 4 in the units of feet. So 50 over 4 feet is the second number that we are looking for. And there you have it. We have now worked out from the perspective of the Yankees when the ace pitcher of the Cubs gets hit by this cream pie. Now, of course, who cares about this particular problem? But my point in doing this little calculation for you is look at the power of the Lorentz transformation formula. We would have had to take into account all sorts of physics to work this out if we were doing it piecemeal. We'd have to work out the Lorentz contraction of the distance, according to the Yankees, between home plate and when the pitcher gets hit. We'd have to talk about the asynchronous natures of clocks in order to transform 50 nanoseconds from the perspective of the stadium to whatever time the Yankees would have claimed it. We don't have to do any of that when we have the Lorentz transformation formula. We plug and we chug. And that's the beauty. As I said, it's also the potential pitfall because you don't want to stop thinking. You always want to think about what's going on. But as a means of efficiently getting to the answer of problems, the Lorentz transformation cannot be beat. Let's look at one final example where we put the Lorentz transformation to work. And this example is particularly nice because it shows how all the pieces of what we have been developing fit together. Okay, so what is the question at hand? we are going to imagine that a laser is at the origin of team platform. We switch it on just as team train goes by, right? The laser is firing. Team train folks, George and his friends, are looking at the laser, and we want them to calculate the speed of the laser from their perspective. We know what the answer has got to be. It has got to be the speed of light, but it's very useful to see how all the pieces of what we have developed will fit together to ensure that the speed of light is constant. It has to be that case. We've used that in our very derivation, but it's nice to see it all in action. All right, let's do the calculation over here, and let's set up our little problem. So what do we have? Let me set up a coordinate grid here in one dimension. So here we go. Let's make this the platform coordinates. Let's imagine that George and his friends are rushing by, and they are going like this at some velocity equal to v. And what happens, we are told, is that at the origin of the coordinate system, we have this little light bulb. And just as the origin of the moving frame and the origin of the stationary frame cross, the light beam is sent out. Okay? So let's then look at the two events that will be of relevance to our calculation. So what is event number one? Well, now you should have some feel for what we will put here. Event number one is that the light is emitted. What is event number two? Let's call event number two that the light, let's say that the light passes position x equals velocity of light times time from the perspective of those in the platform frame. So event number two, whatever, we can put this down here. Let's call this location x equals c times t. Now, we want to work out where and when this second event took place from the perspective of the moving frame. Again, we're going to assume that they all agree on what happens at the origin. Okay, so from the perspective of team platform, what are the coordinates of relevance to us? So, of course, we have t1, x1. We'll take that to be the origin that gets us going. And for t2 and x2, well, those coordinates, in fact, define the event itself. So t2 will just be equal to t, and x2 will be c times t, which is where the second event takes place. Good. Okay. Now, let's look at team train. Let's just plug into the Lorentz transformation to work out the coordinate values that they will ascribe to the second event. So t2 prime will be equal to gamma times, well, we know the formula. It's t minus vx over c squared. What is x? X is c times t, right? So we got c times t over here. And therefore, we can write this guy out. Well, let's just leave it like that for the time being. Let's get x2 prime into the story. That will be gamma times what? It's x minus vt. And x in this case is ct. And vt is just vt. OK, so we now have the time and space coordinates according to team train of the second event of the light passing a given location. How do we use those to get at the velocity of light according to team train? Well, velocity of light, according to them, is gotten by looking at the distance that the light covered divided by the time that it took it to get there. So that's gamma times ct minus vt divided by gamma times t minus vct over c squared. OK, so now we can look at this equation, cancel out the gammas. Let's also note that we have a t a t and a t that we can cancel out too. So we're left with c minus v divided by 1 minus v over c. And lo and behold, that's the same as c times 1 minus v over c divided by 1 minus v over c. Those guys cancel, and the only symbol that is left standing on the board is 1 factor of the speed of light equal to c. So it all works out just as we knew it had to. Space and time conspire in just the right way to keep the velocity of light equal to the speed of light, as it must, but it's great to see how it all fits together. Just when you thought all the examples were over, one more, just for good measure. It's a quick one, so just stay with me. In this problem, we're going to imagine that a sprinter is running in a stadium with a velocity that we're now allowing to have all three components, x, y, and z components to the velocity. Let's imagine some explosion takes place at stadium coordinates, and there they are. I won't bother reading you the details. You can see what they are. And the question is, where does the explosion take place from the perspective of the sprinter, who is, of course, a frame that's in motion? Now, look, it would be a bit of a chore to work out the answer to this, and I'm not going to work it out by hand, but rather this is one example where you can make use of one of the demonstrations that we have, put it to good use, and you can work out the answer just by letting the computer do the work, right? So you should do this on your own. I won't do it for you here, but you see that you can choose the coordinates of any event. So if you want, and you should, choose these coordinates to be the coordinates of the explosion. You can choose the velocity of the moving frame to be whatever you want in 3 dimensions here. And then all that this little demonstration does is make use of the complicated 3-dimensional Lorentz transformation formula, that is 3-spatial dimensional Lorentz transformation formula, to work out what the coordinates of that point look like from the perspective of the moving frame. So play around with this. This is not something that you're really ever going to get a real intuition for, but it is something which at least you should know in principle is a calculation that you can do. Earlier on, we came to the conclusion that the way velocities combine, the way speeds combine in relativity, must differ from what we expect based upon Newtonian physics, based upon common experience, right? It's very simple. If you run toward or away from a beam of light with a speed v, you would expect, based upon the usual way that we combine speeds, that the light would approach you at c plus v or c minus v, but that doesn't happen, and therefore we know that speeds must combine according to a different mathematical rule. And in fact, if you remember, I told you that the failure of speeds to combine according to that equation, c plus v or c minus v, is not special to the speed of light. It is indicative of a general new way that speeds combine in relativity. And I gave you a formula for that. So just in a concrete example, imagine that there's a cheetah that runs with speed w, and imagine that you are running away or toward the cheetah at speed v. What will your view be on the speed of the cheetah? It will not be w plus v or w minus v. Instead, we noted that the new formulas look different. They have this funny factor in the denominator. And that funny factor in the denominator is very important because it ensures that if any of the speeds involved are the speed of light, if we are not looking at a cheetah but we're looking at a laser, this velocity combination law ensures that the speed of light will not be increased or decreased if you are running toward it or away from it. So all of that we've already mentioned. What I want to do now is derive this formula for you. All we need is the Lorentz transformation law that we have at hand, so let's make use of it to understand how velocities combine in the special theory of relativity. Okay, so to do that, let's imagine, as in the statement of the problem, that we have, say, this cheetah over here, and this cheetah, say, is running along at some speed w, and imagine that you, who surprisingly look very much like the cheetah, just you're drawn at a slightly different angle, you are running toward or away from the cheetah at a speed v. So in this case, you're chasing after it. So let's do this example over here and work out the velocity combination law for it. The other case will follow just by changing the sign of v. Okay, so what are we going to do? So let's start with platform coordinates. All right, so from the platform perspective, that's us watching this scenario unfold. What would we say? Well, imagine that these guys both start at the origin. So that would mean that at time 0, they're both crossing x equals 0, which means where will the cheetah be at time t? Well, at time t, the cheetah will be at location w times t, just velocity times time. Okay, where will u be? You're running after this cheetah, so let's call that u. Where will u be? Well, u will be at location t, v, t, at time t. Okay, now what I'd like to do is work out from the perspective of you, not the platform, but from your point of view, where is the cheetah in your frame of reference at time t when it's at location w times t? Well, we can work that out. So t prime is equal to gamma times t minus vx over c squared. That's a general formula. But now for x, of course, we can put in w times t. So this is gamma times t minus v over c squared times w t. And from that, we can get half of our problem solved because you know the time at which the cheetah will be at a given location. Now we just got to work out the location from your view. So again, performing the Lorentz transformation from the platform frame to your frame. X prime is equal to gamma times x minus vt. Now x in this case is w times t minus vt. So we have gamma t times w minus v. Okay? So from your perspective, the cheetah will be at location x prime, given by this formula, at time t prime, given by this formula. So from your perspective, running after the cheetah, what will its speed be? Well, we take distance divided by time. So v of the cheetah from your perspective, that's just equal to x prime divided by t prime. And we can just plug in what we have. So it's gamma times t times w minus v from over here, divided by gamma times t minus v over c squared w times t. And what do we have? So the gammas cancel against each other. We've got a t in every term. Those cancel against each other. And what we're left with is w minus v upstairs. And downstairs, we are left with 1 minus vw over c squared. And there you have it. So there is the relativistic velocity combination law. The speed of the cheetah from your perspective is not w minus v, which is what Newton would have said, which is what common sense says. Instead, we have the correction factor that we noted earlier, 1 minus vw over c squared. Again, where does that come from? It comes, again, from the Lorentz transformation on time. It comes from the relationship between clocks in the moving frame compared to clocks in the stationary frame. But there you have it, simple derivation showing us this new way of combining velocities. Now we have derived it. Now that we have derived the relativistic velocity combination law when the objects are all moving in the same direction or opposite directions, that's the formula that we have over here. Again, if you replace v by minus v, it would be the formula in which you are running toward the θ. It would be w plus v over 1 plus vw over c squared. That's good, but we'd like to take this formula one step further, right? We'd like to have the formula when the velocities involved are not always in the same or opposite direction. What is the relativistic velocity combination law? That is, when we allow motion in the full three-dimensional space. So let's do that derivation. It's not particularly hard, and it will actually be very useful to us. This is not simply an academic exercise at this point. Well, I guess you could say this is all an academic exercise from some perspective, but we're trying to figure out how reality works, and we will find that the three-dimensional relativistic velocity combination law will be very useful in deriving something else that you have heard of, E equals mc squared. So we will make use of this later, so it's not simply a matter of showing that we can do it. It will be useful. Okay, so how are we going to do this? Let's choose a train frame. So we'll put it in this language. So in the train frame, we're going to have the train frame has a velocity v, and we're going to take that guy to be in the x direction. But where we are going to be more general is we are going to consider an object, and the object, be it a cheetah or something else, we're going to have its velocity from the perspective of the platform. Okay, so we're watching this object, and we're going to take the velocity from the perspective of the platform to be general. So it's going to be wx, wy, and wz. And what's our goal? So our goal is to work out, of course, in this particular case, what is the velocity of the object from the perspective, from the POV of the train, right? So it's a variation on the same theme. So now we are taking the velocity of the object to be known from the perspective of us in the platform. We're watching it go. We're also watching a train rush by us, right, in the x direction. And we want to work out, if we were to put ourselves in the perspective of the train, what would the velocity of the object now be? Okay, so let's set up some coordinates. So in the platform coordinates, again, let's assume that the origins align at t equals 0, the same game, so we don't have to worry about that. So in the platform coordinates, at time t, where is the object? Well, if this is its velocity, then at time t, it's going to be at wxt, wyt, and wzt. Good. Now we need to transform this space-time coordinate of the object to the perspective of the train, and that just requires that we undertake a Lorentz transformation. So we want to work out t prime, x prime, y prime, and z prime. These are the train coordinates that give us the space-time coordinates of this event, that the object passes through this point at this moment in time. So let's just put down the Lorentz transformation. And again, this is not the complicated Lorentz transformation because the speed of the train is in the x direction. The complexity is that the object that we're concerned with is moving in x, y, and z. Okay, so we have gamma times, I'm just going to write down the formula that we already know. So it's t minus v times, well, what is the x position? The x position is wx times t, so that's vx divided by c squared. For x prime, we know that x prime is gamma times x minus vt, so that's wx t minus vt. And what about y prime and z prime? We know that they just come along for the ride when the motion is in the x direction. So that then will just be wy times t and wz times t. OK, so that's the Lorentz transformation, which takes this location that the object passes through in time and space and shows us what the time and space coordinates are from the perspective of the train. All right, well, there we're cooking with gas. Oh, and let me just emphasize, since there are a lot of velocities going along here, this gamma, of course, is 1 over the square root of 1 minus v over c squared. It is the velocity of the train that comes in, of course, to the gamma factor. We're going from the platform to the train, and that's the relevant velocity. OK, now that we have this on the board, we can now work out what wx prime and wy prime and wz prime are, the speeds of the object from the perspective of the train. How do we do that? Well, we take x prime over t prime. X prime over t prime is just gamma times, well, let's put the t outside. We have a wx minus v divided by gamma times t times 1 minus v wx over c squared. And we can kill the gamma t. We can kill the gamma t. And therefore, we get wx minus v divided by 1 minus vwx over c squared. OK, good. So that is the answer for the x component of the speed. Let's go on to the y component of the speed. Well, that's just y prime over t prime. And y prime over t prime, what is that? Well, that's just wyt divided by this quantity over here. So let's work that out. wyt divided by gamma times t times 1 minus vwx over c squared. I just pulled the t out of this expression. And if I now cancel out the t's, I get wy divided by gamma times 1 minus vwx over c squared. So that's a curious result. The speed in the y direction does change, even though the train is only moving in the x direction, because of the way that clocks in the train differ from clocks in the platform. Finally, let's work out wz prime. And that is just z prime over t prime. So that's just wzt. Same really calculation as in y. Gamma t, 1 minus vwx over c squared. And that then is just wz divided by gamma times 1 minus vwx over c squared. So there are the three components of the velocity from the perspective of the train. The object itself has speed, again, wx, wy, wz from the point of view of the platform, but from the point of view of the train, moving relative to the platform at a speed v. Here are the three components of the velocity from that frame of reference, from that perspective. So you see, it's kind of curious. It's not that the y and z components of velocity just come along for the ride. You might have thought that. It's a natural thought for a moment, but then if you think it through, you realize that velocity has to do with distance and time. Even if distance in the transverse directions is not affected by going from the platform frame to the train frame, time is affected, and we see the way in which that effect on time comes into the formula. So the result then that we have now derived is that if the train frame is moving with velocity v relative to the platform, and the object has speed wx, wy, wz, here I called it a cheetah, here I don't know what I called it, I didn't even specify what the object was, doesn't matter. The velocity combination law is as we have now derived. This interesting combination of wx, wy, wz together with v and the various factors of 1 minus vwx divided by c squared. We now have a nice little formula for how to combine velocities in special relativity. We've derived it. We have the case in which the velocities are going along the same direction or opposite, but we've also done the more general case in which the object of interest may be moving anywhere in the three-dimensional space of possible velocities. Let's do a couple of examples just to make this a little bit more concrete. So example number 1, let's look at a case where Gracie is running by George at 80% of the speed of light and yells, "Tag, you're it." He then runs after her at 70% of the speed of light. From his perspective, how quickly is she getting away? Okay, so that's a direct calculation for us to do. So let's just use the notation that we have been using all along. So let's say W is equal to 0.8 c. That is Gracie's speed in the positive x direction. George, his speed is 0.7 c. Again, both are plus. They're both going in the same direction in this little problem. So, you've got Gracie running along at 0.8 c. You've got George chasing after now at 0.7 c. The question is, from George's view, how quickly is Gracie getting away? Well, we know how to do that. We use our velocity combination law. Newton would have said the answer is W minus V, that Gracie is getting away at 10% of the speed of light, 0.8 minus 0.7. But we know that we need to correct that in relativity using our factor of 1 minus V W over c squared. And now it's just a matter of plugging things in. So we have 0.8 c minus 0.7 c divided by 1 minus 0.8 times 0.7. That's 0.56. And the c squared cancels against the c squared. So we've got 0.1 c divided by 0.44 c. And if you plug this in, you will get the result 0.23 c. So instead of the answer being what Newton would have said, which would be 0.1 c, we see that the answer is 0.23 c. Quite a difference when the speeds involved are getting close to the speed of light. So far, we've only made use of our relativistic velocity combination laws when the motion involved was in the same or opposite direction. Now, let's, for good measure, just look at an example where we have to use the full three-dimensional formula. Let's imagine we're still having this game of tag. George is chasing after Gracie, who takes a sharp turn and starts running north at 80% of the speed of light. George is still running due east at 70% of the speed of light. Question: from George's perspective, what is Gracie's velocity as she is running away? Okay, so let's do that calculation over here. And it's just a matter of making use of the relativistic velocity combination law that we have already derived. So just in picture form, so we know what we're doing here, we've got George over here. We've got Gracie over here. And unlike in the previous problem, she's going to actually run in this direction, 0.8 c, in the north direction, while George is heading here in the east direction at 0.7 c. This is how things look from our perspective in the laboratory, the stationary frame, the platform frame, whatever you want to call it. What we're asking is, put yourself in George's perspective from his point of view. What is the speed with which Gracie is running away? And now we can just plug into the formula using W is equal to, we'll call our x, y, and z components to be, say, the east, north, and we could have a third component in principle, but it won't come into this particular story. So that is for Gracie. For George, what is his speed? Well, he's going at 0.7 c in the x direction or the east direction. He's got nothing in the y direction or the north direction, and we're not even going to talk about the other axis at all. So now we just take these two and we combine them in order to get Gracie's velocity from George's perspective. We just use our formula. So what does the formula say? Well, it says that you take the x component of Gracie, which is 0. You subtract from that the x component of George over here, and you divide through by 1 minus the product of those guys. But since you've got a 0 in there, that doesn't contribute much at all. OK, what about for the y direction, where we're told you take 0.8c minus George's y velocity, which is equal to 0, and you take this guy and you divide through by gamma times 1 minus VWX over c squared. But again, you have a 0 involved in WX, so you get a 0 in there. And then nothing at all happens in the third direction because there's no velocities there at all to deal with. So that is the combined velocity. And if we just work that out, what we get is a velocity of minus 0.7c. That makes sense. From George's view, he's running this way. If he claims to be stationary, as he always does, he would say that in this direction, Gracie has a speed going minus 0.7c. She's going the opposite direction at the same magnitude. But the feature that is unexpected is that when you look at the y component of her speed, you get 0.8c divided by gamma. Now, gamma is something that we calculate from George's speed. So gamma equals 1 over the square root of 1 minus 0.7c over c squared. And if you plug that in, the answer you get for gamma is 1.4, or very close to 1.4. So you get a factor of 1.4 here in the bottom. So then if you just want to see the numbers, it's minus 0.7c. And you've got 0.57c and 0. So that is the answer from George's view, making use of this more robust version of the relativistic velocity combination law. Now, as always with these formula, I like to give you some practice using them to get some intuition for them by playing with a demonstration. And we can look at a demonstration here. So let's take a look at one where we can play around with this. So in this demonstration, what you are able to do is you can choose the x, y, and z components of the velocity of an object. You choose them at will so long as the magnitude is less than the speed of light. And then you can choose the relative velocity between the stationary frame's perspective, which is the frame within which these velocities that you chose, that you selected, were defined, have another frame moving relative to that frame. And notice what the velocity of your frame does to the velocity of the object. So from your perspective, that is how the velocity looks when you are executing a velocity chosen by this fourth slider. So again, play around with it to get a little bit of a feel for this relativistic velocity combination law. Ultimately, it's kind of abstract, but it'll give you some sense of what's going on with that formula. Let's turn now to the subject, the important subject of spacetime diagrams. So what are spacetime diagrams and what are they about? Well, fundamentally, spacetime diagrams speak to a particular question, which is, how should we depict a series of events, right? That's something that we always do in our thinking about relativity. We're looking at various events from various perspectives. What is the most efficient way to depict that series of events? And we already have seen a variety of possibilities, right? You all know about movies, right? A movie shows event after event, and you just watch the film unfold on the screen, and that's the way the series of events is indicated. But earlier on, we encountered another way of thinking about a series of events. Let me show you this video again, because it really gets the point across really well. You can think about a movie like this, where you only see one moment at a time, and once it's gone, it's over. Or you can think about a series of events more as a kind of series of snapshots, a series of records which depict moment after moment after moment. Remember, we encountered this earlier when we were talking about the weirdness of changes in time over large distances. My point here is a little bit different. My point here is, if you want to be able to see a whole sequence of events at once, this is a good way to do it, to depict moment after moment after moment in one big collection of snapshots. Not literally snapshots, because we're talking about events at the same moment in time from one person's perspective, but this is a good way of doing it. Now, we saw another version of the same story when we focused in on a more, if you will, cosmic perspective like we have here, where again earlier we described how you can look at a series of events as a kind of series of now slices. We called them one moment after another moment after another moment. And the value of depicting events in this kind of way is that you're able to see a whole sequence of events at once. You don't lose a moment after it's on the screen and gone. And this is, in essence, really what a space-time diagram is about. It's a diagram, we will see, in which we are able to depict a whole sequence of events in one frame, in one geometrical picture, in one graph, if you will. So mathematically, we are thinking of time, if you will, as a new axis. Moment after moment after moment is being given a geometrical interpretation, right? You can think about this direction as the time direction. This direction is space. Each slice depicts what's happening at various locations in space. This axis is a time axis. So the way to think about that is we are including time as an additional axis, or if you will, an additional dimension is the language that we use, where we are looking at all of space at each moment of time, but including all of it in our pictures. Now, when we think about this from the perspective not of pretty animations, but when we put equations and mathematics to this, we depict events in much the same way, except by convention, for no really good reason, we typically choose the time axis to be the vertical axis, and we use these directions to be the spatial directions. Of course, we can't truly show three-dimensional space through time because we don't have enough dimensions to show that. We don't have four-dimensional screens, at least not yet, three space and one time. So what we do is we play the same game where we have two dimensions of space, or sometimes one. We'll simplify there as well. But we usually take the time axis to be vertical. So the picture then you should have in mind for our version of space-time diagrams will be something like this. So we'll have the x-axis, the y-axis. There is space at one moment in time. That's like one of the now slices. But now if we have the time axis going vertically, we have space at one moment in time after another moment, after another moment, after another moment. Exactly the same kind of picture that we had a moment ago when we were looking at moment after moment in the expanse of the cosmos. Geometrically, though, mathematically, this is how we will encapsulate it. So we'll have x and y, say two dimensions of space, sometimes one to simplify things, and we'll generally take the vertical axis to be the time axis. Now, let me give you just a couple of examples so we can get a feel for how these space-time diagrams work. So example number one, let's consider a flash of light that is spreading out from the origin. Let me say from the outset that we're going to choose our units so that the speed of light is equal to 1 in those units. And that becomes particularly useful because what it means is that when we look at a beam of light, the beam of light, let's say a flash goes on and it sends out light in all directions, the distance that the light will travel, of course, is velocity times time. If the velocity is 1, then the distance that the light travels numerically will be equal to the amount of time in those units that has elapsed. which gives us a particularly pretty picture for how we will depict in a space-time diagram a flash of light. Okay, so let's take a look at that. So here is a flash of light at the origin. It spreads out. Its radius is velocity of light times time, which in the units that we're using will just be r equals t. This is the movie version of a flash of light spreading out in all directions. What does the space-time diagram for that look like? Well, let's take a look at it over here. So here is the space-time diagram version, and notice what it has. It keeps each moment in time by having this additional axis, the time axis. So the movie, the light spreads out, and we only see the final moment in the frame of the movie. But here we have moment after moment after moment of the light spreading out more and more and more. And just to bring that point home, let me highlight the slices. One moment, the next moment, the next moment, the next moment. This is the unfolding of the spreading out of the flash of light over time. So you see the value of the space-time diagram is we see the whole history of the spreading of the light as opposed to just seeing where it got to at a given moment in time. So that's one example in which we have the space-time diagram version of a certain physical phenomenon. Let's look at another example. A flash of light in one space dimension where we'll see that the light goes along 45-degree lines instead of a 45-degree cone. We will simplify what we're doing, again, by only looking at one dimension of space, not two, as we were looking at in that picture. So what would the one-dimensional version of this be? So in one dimension, we have, say, a flash of light that will happen at the origin. That spreads out in one dimension, but the space-time diagram version, the light travels on these 45-degree lines. Again, the speed of light equals 1 means that we'll have equal amount of distance covered in equal amounts of time. So we have these 45-degree lines. This line over here is the history of the flash of light moving toward the right. This line over here is the whole history of the flash of light moving to the left. You see, the movie version, you're left with two dots in the final frame of the movie. The space-time diagram version, you've got more information there. You've got the full history at your disposal. Okay, so those are a couple of examples having to do with light, but you, of course, don't have to just look at light. We can look at a variety of other examples. Let's take a look at a few of them. Set up our graph paper here so I can make a nice, clean space-time diagram to work with. Of course, you don't have to have graph paper, but it's kind of nice in order to show what's going on. So here, say, are my coordinates. And let me label these guys now as one dimension of space, one dimension of time. So that will be the simplification that we'll use. And let's look at a variety of simple physical situations as depicted in a space-time diagram. So example number one is somebody who's sitting still at the origin. What will their trajectory in the space-time diagram look like? Well, since they're not moving through space, the only thing that happens is they move through time. Their trajectory in the space-time diagram would look like that. So that is someone sitting still at the origin. This is their history. They're always at one location in space, the origin, but they're there for various moments in time. Okay, let's look at another example. Let's say we look at firing bullets whose velocity is less than the speed of light. Well, what will that look like? Well, it's useful now for me to show you in this picture what a light beam looks like. So we've seen it already, but let's write it down. 45 degrees. I think that is 45 degrees. So that is the trajectory to the right of a beam of light. If something is moving slower than the speed of light, what will its trajectory look like? Well, let's choose another color. And if an object is going slower than the speed of light, then that means it won't cover as much distance in a given amount of time, which means the slope over here will be larger That is, it's going more in time than it is in space, and that could be, say, a bullet whose velocity is less than c. What about another example? So here we have a round-trip journey. So someone goes off into space and comes back. Let's even assume that they don't have uniform velocity in either part of their journey. So let's say that maybe they go out into space, and then they come back. Now, just so long as the magnitude of this slope is never smaller than 1, and it looks like I've drawn a little bit awkwardly over there, but you get the point. This would be someone who starts at the origin, turns around, and ultimately comes back. What about two laser beams that are firing at each other from different locations? Okay, what would that look like? So let's use yellow for a laser beam. And let's say we've got one laser firing from here. So a laser beam from there. Oh, that's kind of orangey. I don't really like orange for the color of a laser beam, so let's use yellow. So here is a laser beam, 45 degrees. I don't know, let's put it over here. And somebody else is firing from another location. Let's say they're firing, say, from over here, maybe. And their laser beam is going in that direction. So laser fire one direction, laser fire another direction. Again, we're getting the full space-time history in the space-time diagram. Final example, what if we look, say, at two people having a duel? They're firing bullets at each other. Well, let's use this for our first one. If someone is firing a bullet from some other location, let's say we use red for that. They, too, firing back in the other direction. And the slope here has to have magnitude that's bigger than 1. So it might look something like that. So maybe the two bullets hit each other at some location in space-time, right? Now, look, you can get confused with these diagrams. It looks very two-dimensional. But what is going on here is we've got one dimension of space, and two bullets are firing toward each other, right? So they will hit each other at some location. They're just moving in one dimension, but this is showing the full two-dimensional space-time history of the events in question. So that's the basic idea of space-time diagrams, and what we're going to look at next is how do we depict the space-time diagrams for two different observers moving relative to one another. Now let's take a look at how we would depict the space-time diagrams associated with two sets of observers that are moving relative to one another. And let me start actually by not working with space-time diagrams. Let me just remind you of something we've already discussed, but it is a model, if you will, for what we are about to talk about in space-time. Remember that in basic geometry, as we've reviewed, the change of coordinate system is a very useful tool to have at your disposal, and it's straightforward to work out the relationship between one set of coordinates and another, right? So the prototypical example that we have been looking at is a two-dimensional spatial system. Remember, you rotate one relative to the other, and you get different coordinate labels associated with a given location. And we have worked out, you know this even before this discussion that we're having, you know how to translate one set of coordinates to another using the basic trigonometric relations. Just to remind you, we derived this formula. No doubt you knew it before. I remind you of this because the Lorentz transformation that takes us from t and x to t prime and x prime is conceptually very similar to what we have over here when you think about things geometrically. Namely, you look at these transformations between the tx coordinates and the t prime x prime coordinates, and as we're going to see, if you embody that algebraic equation in geometry, in a geometrical depiction, which we will do in a space-time diagram, then you can interpret that as also just a change of coordinate axes. So much as we go from x and y to, say, x prime and y prime in this example, we will have a similar way of thinking about the transformation from tx to t prime and x prime as just changing the coordinate axes in a space-time diagram. Okay, so let's work that out. So let's imagine that we have two frames of reference moving relative to each other at some speed v, and I want to draw the x prime and t prime axes of that moving frame of reference. I want to draw them in the space-time diagram of the original frame of reference so that we can compare them. Okay, so let's take that calculation on here. And it's, again, good to have some graph paper so we can keep this as neat as possible. So let's take this to be our t-axis. Let's use double-headed one. So this will be our x-axis. And I want to figure out t prime and x prime look like in this coordinate system. Okay, so let me start by noting that I'll start with, say, the t equal to 0 axis, right? So x, of course, the equation is t equal to 0. So if I want to draw the x prime axis, right, the x prime axis is just given by solving the equation that t prime is equal to 0. Now, that's something we can do because we have the Lorentz transformation at our disposal. So t prime is equal to gamma times, well, it's t minus vx over c squared. That should be a t, not a t prime, so let me take that back. It's t minus vx over c squared. I'm not going to write the c squared any longer. Sometimes I'll put it back, but c is equal to 1, so it won't affect anything numerically that we are calculating. So setting this guy equal to 0 to get the x prime axis, we learn that t is equal to v times x. Now, t equals v times x, we can plot that in this diagram that we have here. V, of course, is less than 1 because in units where the speed of light is equal to 1, the velocity of a frame of reference is always less than c. And if the slope here is less than 1, then that axis looks something, say, like that. So that would be, say, the x prime axis plotted in this system. So that is the equation, of course, t prime is equal to 0. So this, if you will, is all of space at a single moment of time from the perspective of the moving frame, much as this is all of space at a single moment of time from the stationary perspective. Okay, let's move on. Having done the x prime axis, let's take a look at the t prime axis. And of course, the t prime axis is gotten by solving an equation, just as this t-axis is the locus of x equal to 0, right? So that's the equation here. X is equal to 0 all along the t-axis. The t prime axis is given by solving the equation x prime is equal to 0. And we can do that because we have the Lorentz transformation that tells us that x prime is equal to gamma times x minus vt. So setting that equal to 0, gamma can drop out of the equation, and we have x equals vt, which I am going to write as t equals 1 over v times x, because we're used to writing equations for a line, say y equals mx plus b. Remember that from high school. So y, now t is playing the role of y. This now is the slope of the line, and it's 1 over v. This is bigger than 1, so I can plot that guy too. And doing so would look something like this. Something like that. Okay, so that, therefore, is the t prime axis. So this is the t prime axis, which of course is gotten by the equation x prime equal to 0. So this now is a geometrical embodiment, if you will, of the Lorentz transformation. So we've drawn the x-axis, we've drawn the x prime axis, I should say, we've drawn the t prime axis, and now we can use this to, in a geometrical way, write down the coordinates of any event. How would we do that? Let's say a firecracker explodes at some location. Let's say that event happens, I don't know, right over here. Now, what would the space-time coordinates of that be? Well, in the original frame, say the stationary frame, you draw a line parallel to this axis. You draw a line parallel to the other axis, and this gives you, say, the x naught coordinate of that event, and this gives you the t naught coordinate. So in the blue stationary frame, you'd call this event t naught x naught. That's where it takes place. Now, if you want to do the same thing in the moving frame of reference, all you do is drop lines, I should say, that are parallel to the axes that we have here. So if I want to work out the x prime coordinate, I just draw a dotted line parallel to this guy. And let's see if I can get something reasonably parallel. No doubt that's not perfect, but that's the intersection there. And to get the other, we want to now draw a dotted line that's parallel to, say, this guy over here. So that would look something roughly like that. And we would look at this value, which I'll call x naught prime, look at this value, which I'll call t naught prime. And then we would say that this event, let's call this event E, can be written in the blue system with those coordinates, or in the moving system with the coordinates t0 prime, x0 prime. So that is the way in which we can depict the coordinates of an event either in the stationary frame, which is the blue one, or in the moving frame, which is the red one. Now, let me just stress a couple of things about this picture that are really worth emphasizing. The diagram directly shows the relativity of simultaneity, right? It's right there geometrically, because look at what this line means. This line is all of space at one moment of time from the perspective of the moving frame. These moments are all at the same moment of time, all simultaneous. But from the perspective of the stationary frame, in this case the blue frame, these points cut across many different moments in time because they cut across many different horizontal lines, which from the stationary frame are different moments in time. So the fact that this goes at an angle is nothing but the relativity of simultaneity turned into a geometrical form. So we have the basics of space-time diagrams now out on the table. There are a few useful remarks that I want to make about them because they are a somewhat unusual subject. And let me just emphasize or re-emphasize some of the things that characterize space-time diagrams. So let me get one up here, and let me label this guy as, say, x-coordinate and t-coordinate. And let me put up space-time axes for the moving frame of reference in here too. So we know that one of those axes might look like this, and then the other, let me try to get close to something that looks reasonable, something like that. So let me label those as well. So that would be the x prime axis, and that would be the t prime axis. Now, first remark is, notice that these axes, the t prime and x prime axis, they're not orthogonal axes, right? We're used to, whenever we change coordinates in basic geometry, we start with axes that are at right angles to each other, and then we say rotate them or we translate them. But in relativity, we see things are a little bit different. So the axes are not orthogonal, but that's okay. There's no mathematical rule that says axes have to be orthogonal. They provide a perfectly good coordinate system, and we've seen how you get the coordinates of any point by drawing lines that are parallel to one or the other axis to figure out the coordinate values of that point. So again, if I have some point over here, all I need to do is draw a dotted line this way, parallel to that axis, dotted line this, parallel to that axis. And these two points of intersection, call them x0 prime, as we've seen, t0 prime, give us the coordinates of this event E in the blue system as x. Let me put it in the correct order there that we're more used to. So let me call this t0 prime and x0 prime. Good. OK, so they're not orthogonal, but they're perfectly good coordinate axes. Second point is, let's just remind ourselves what the meaning of these axes are, right? So here we have all of space at one moment of time from the perspective of the moving frame. This axis over here, this is the origin of the moving frame as it evolves in time. So if someone's standing still at the origin in the moving frame, this is the trajectory that they follow. This is their path through space-time as plotted in the red system. The blue system, of course, the person would say that they are not moving at all. Now, it's also useful just to reemphasize that you can read off key features of the motion of the moving frame by just looking at the slopes of these lines, right? So the slope of this line, the slope of this is equal to the velocity. Again, we're using units where c is equal to 1. So this is the velocity of the moving frame. If you look at that slope, this guy over here, the slope is 1 over v. Again, v is always less than 1. So this is always bigger than 1. So the t prime axis is always sloped upwards in that way. And just by looking at the diagram, you can read off the speed, the velocity of the moving frame. Also note, and it's worth just putting this in for completeness, that if I plot over here, let's say the trajectory of a beam of light, so a beam of light would be at the 45, which would be, say, something like this, if the light beam is heading off into the rightward direction. And as the velocity of the moving frame gets faster and faster, approaches 1, approaches the speed of light, this axis will sweep up toward the yellow line. The time prime axis will sweep down toward it. They'll never cross it because v can't get bigger than 1, so 1 over v can't get smaller than 1, so they'll never cross, but they'll get ever tighter. They'll more tightly hug, if you will, this trajectory of a beam of light. That makes sense. The faster the frame is going, the closer the velocity of a person at the origin will be to the speed of light. Good. Okay, so two other points that I want to make before we move on. Point number one is this. When you look at this space-time diagram, it seems not to manifest the symmetry that I have emphasized repeatedly, that the person who is moving can claim to be at rest, and the other frame of reference from that person's perspective would then be moving in the opposite direction. There doesn't seem to be a symmetry manifest in here, and that's clear. It's clear why. We are showing what the space and time axes of the moving frame look like plotted in the coordinate system of the stationary perspective. You don't have to do that. You could take the perspective of the moving frame and plot within that frame of reference what the red system would look like. So just for giggles, why don't we take a look at that? So let me plot down here. Imagine we take the starting perspective to be the blue system. So here is its axis, and let me keep it reasonably close. So that then would be labeled as t prime and x prime. So there is space and time from the perspective of the moving frame. And then from this perspective, which is now going to be considered stationary in the way that we're looking at things, the red system is heading off to the left. And therefore, if you were to look at, say, the trajectory of somebody who is sitting still at the origin of the red system, that person, in this way of looking at things, would have a trajectory, well, that's a little off from the origin, so let me be a little bit better than that. So something like this, good, right? So this will now be the t-axis, and to draw the x-axis, we just, again, take things nice and symmetric about the light trajectory, which would be at the 45-degree angle. Again, as over here, the angle that we have here will always equal the angle that we have over here because of the way the slopes work out relative to the velocity. Same thing in this diagram, but now let me just label it for completeness. So we will have over here, this now will be t, and this will be x. And now you see the nice symmetry. So from the red system, the blue frame is moving, and its space and time axes look as we've drawn. From the perspective of what we initially called the moving frame, now make it the stationary frame, and the other frame is now moving to the left, and we can draw its space and time slices as well. And you see this perfect symmetry between the two pictures. OK, one final point, which is this. It is really important to always keep in mind what these diagrams mean, right? So we started off by saying that you can illustrate a sequence of events in two ways, as a movie, or you can illustrate a sequence of events by showing the whole history in a space-time diagram. Those are equivalent representations of the same information, and you should always try to keep both pictures in mind. So if we are thinking, say, of this in a movie perspective, the idea would be this is all of space at one moment in time. The next moment in time would be represented, of course, by drawing a parallel slice to this guy. Say, over here, that's a next moment in time, and a next moment in time, and so on. So a movie version of this would show this axis, which is all of space at one moment of time from the perspective of the moving frame, moving in the way that we've indicated here. So this then would be, say, the origin at one moment in time, the origin at the next moment, the origin at the next moment, and so on. So let me show you that just so that you can have that picture in mind when you think about space-time diagrams. So the movie version would look something like this. So here you have a frame moving relative, blue frame is moving relative to the red, and you see that axis, which is all of space at subsequent moments of time, is moving up, and you see the origin is moving along the trajectory we described. These are equivalent pictures. Try to have them in mind when you are thinking about space-time diagrams, and it'll keep you from getting confused and allow you to extract the full information that space-time diagrams are providing us. So now that you have the basics of what a space-time diagram is and how to express the space-time diagram for a moving reference frame relative to one that is stationary, you should get a little bit of practice with those ideas. And of course, the good way to do that is to use some of the demos that are available to you. So let's look at one of those demos over here. So this is a demonstration where you choose the velocity of the moving frame. And as you can see, this is showing you the spatial slices, right? So this is the t prime equal to 0 axis, right? This is all of space at a single moment of time from the moving frame of reference perspective. Now, this is just one of the axes. That is, it's giving us one slice of space at a given moment of time. If we want to show the other spatial slices, well, you click that button, and this is now showing you time minus 2, all the space at minus 2, all the space at minus 1, all the space at 1, all the space at 2. So you can get a feel for how these spatial slices vary as the velocity of the moving frame changes. Okay, so that's when we're looking at these spatial slices. Over here, we have the other axis, the temporal slices. So this is looking at one position in space throughout all of time, much as this axis is the origin of space throughout all of time. This is a similar idea, but now in the moving frame. And again, if you change the velocity of the moving frame, you see that the angle changes. Look, it varies from being very close to our own x equal to 0 axis, and then it sweeps over, gets close to 45 degrees, but never crosses it because the velocity is always less than 1, and the slope of this line is 1 over v. So the slope is always bigger than 1. It never comes down to the 45-degree axis. And if you want to see the other temporal slices, that is, other positions in space throughout moments of time, that's what they look like. And you can vary the velocity to get a sense of what those temporal slices look like. Now, of course, you want to put both of those together to get a feel for the full space-time diagram. And we can do that over here. So we vary the velocity of the frame. That is how the two axes vary relative to the velocity. And now we can fill in, if you will, the rest of the grid of spatial and temporal slices. And there we have the space-time grid associated with the moving frame of reference. Okay, so there are a few other demos that you should play with beyond these that are available to you. And the point is, use these to get some feel for the mathematical equations that we have derived. Bottom line is, though, we now have at our disposal a geometrical way of thinking about Lorentz transformations. We go from one space-time diagram to another, and we understand the algebra behind it. And from what we have shown through these diagrams, we understand the geometry of it, too. There's a tantalizing similarity between rotations in ordinary space, which take us from one coordinate grid to another, and the kind of strange-looking rotation that occurs in a space-time diagram when you go from one frame of reference to another, where the axes kind of come together. So the question is there a way in which the Lorentz transformation, taking us from one space-time reference frame to another space-time reference frame, can be described in a language that's similar to the language of rotations in ordinary space? And the answer to that question is yes. It makes use of hyperbolic cosines and sines instead of the ordinary cosines and sines. And I'd like to just take you through that, as it gives us another way of writing mathematically the Lorentz transformation. I'm going to break this little calculation up into 3 or 4 little pieces. So let's just go through them one by one. I'm going to begin with what might look like a kind of strange definition of a variable that will play the role of an angle. But the definition is going to be e to the phi. This now defines the variable phi is equal to the square root of 1 plus v over c divided by 1 minus v over c, where v is, again, the relative velocity of two different frames of reference. And therefore, e to the minus phi is that guy flipped upside down, 1 minus v over c divided by 1 plus v over c. And I want to play around with this definition to put it in a particularly suggestive form. So point number 1 that I'm going to make, with that definition of phi, you can show that gamma is equal to e to the phi plus e to the minus phi over 2. How do you do that? Well, just straightforward calculation. Let's spell it out. So e to the phi, square root of 1 plus v over c, 1 minus v over c, plus e to the minus phi, square root of 1 minus v over c, 1 plus v over c. And we're going to take 1/2 of this. All right? In order to evaluate that, let's put it all over a common denominator. Let's put it all over 1 minus v over c times 1 plus v over c downstairs. And what will we have upstairs? Well, we'll have 2 terms. So from this guy over here, we will have multiplied this guy by 1 plus v over c. So that will give us the square root of, if you will, 1 plus v over c squared from the first term over here. From the second term over here, I'll have something of exactly the same sort. So if I can squeeze that in over here, plus the square root of 1 minus v over c squared divided by the product here, which I'll simplify and write that in the form 1 minus v squared over c squared. That is the same. All right, so putting those two guys together, the square roots take away the squares on top, so we get 1 plus v over c plus 1 minus v over c from the second term, and both of these guys are over the square root of 1 minus v squared over c squared. And we see that the v over c goes against the v over c. We get 2 here, but bear in mind there's a factor of 1/2 that I should have carried over, but there it is. So with that half, that factor of 2 turns into 1, and we are left with 1 over the square root of 1 minus v squared over c squared, which of course is our friend gamma. So indeed, we've now established part 1 of this little calculation, that gamma can be written in this way, e to the phi plus e to the minus phi over 2. Now, why is that useful? Not that useful yet, but let's just keep on going. And let's look at point number 2 over here. And point number 2 is the claim that sinh of phi, the hyperbolic sign of this variable phi, can be written as v over c times gamma. Okay? So what is sinh phi? Well, of course, sinh phi, maybe it's worth saying over here, since I'm going to make use of it, that this guy over here is the same thing as cosh phi. So this can also be written as gamma equals cosh phi, where by definition, cosh phi is that particular combination of the exponentials. Good. So the claim is that sinh phi, which is the combination where you have a minus sign instead of a plus sign, can be written in terms of v as v over c times gamma. How do you show that? Well, remember that cosh squared phi minus sinh squared phi, this plays the same role for hyperbolic cosines and sines as the sum of the squares does for the ordinary ones. This is always equal to 1. And now we're in good shape because writing sinh squared phi is equal to cosh squared of phi minus 1. We now can make use of what we derived over here, that cosh phi is nothing but gamma. So we can plug that in this expression here and write this as gamma squared minus 1. Gamma squared, of course, is 1 over 1 minus v over c squared. If we want to subtract off 1, we can do that by subtracting off 1 minus v over c squared over 1 minus v over c squared. And as you see, the 1 will cancel against the 1. The minus sign will turn that into a plus sign. And we will be left with v over c squared times 1 over 1 minus v over c squared. So this is sinh squared of phi. If we take the square root of that to get sinh of phi, we'll have sinh of phi, therefore, is equal to v over c from the guy in front times 1 over the square root of 1 minus v over c squared, which is indeed v over c times gamma, as we advertised. Again, it should not at all be obvious to you why these manipulations matter, but they will in just a moment. Okay, so that's part 2 of the calculation. Now for part 3. So for part 3, I'm just going to put these two together, and we remember what they are, so we can clear this away and give ourselves a little bit of room. We have found that gamma is equal to cosh phi, and we have found that sinh phi, for this definition of phi, is equal to v over c times gamma. And the reason now why we care about this, putting it together, is that when we look at the Lorentz transformation, of course, involves gamma and v over c times gamma. So let's now rewrite the Lorentz transformation in these variables. So for instance, we know that t prime is equal to gamma times t minus vx over c squared, which we can now write as, well, for the gamma we have cosh phi. So we have cosh phi times t from this first term. Here we have a gamma times v over c with an additional factor of c that we will need to include. So that combination gives us sinh phi times x over c. And here we have a transformation that starts to look like a rotation, albeit an exotic rotation since we're using hyperbolic angles, but nevertheless, this looks very similar to the transformation from xy to x prime y prime. OK, that's half of the story. What about the other half? X prime is equal to gamma times x minus vt. Well, we can plug in for gamma cosh phi here as well. So we get a cosh phi times x over here. What's the next term? Well, we have a gamma v. We know that gamma v equals c sinh phi. So let's write this guy as the second term just for the heck of it, v over c gamma times ct. Just put a c up and down. And putting it that way, we see that we can just put in our sinh in the second term. So then we can write this as cosh phi times x minus sinh phi times ct. And there we have it, writing our Lorentz transformation in terms of coshes and sinh. Let me also note that if you look at tanh phi, that, of course, is sinh phi divided by cosh phi. And plugging in from what we have above, we have v over c times gamma divided by gamma. So that is simply equal to v over c. So the way that you can think about this is as follows. So if you give me the speed of one frame relative to another, I can use that to find an angle phi by solving this equation. And then I can take that angle and plug it into a transformation from t and x to t prime and x prime, where the transformation over here looks very much like a rotation with some different signs. And replace, when I say signs there, I mean S-I-G-N, different signs, because normally when you do the rotations in 2 dimensions, you have one minus sign and one plus sign. Here we've got 2 minus signs. That reflects the fact that we're doing space and time as opposed to space and space. But there you have a nice way of representing the Lorentz transformation that looks very much like a rotation in this exotic space. So if I write this down in terms of ct prime and x prime, I can make it look even a little bit nicer. And if I put this in matrix form, now it really does start to look like a rotation. If you closed your eyes and you didn't see the h in sinh and cosh, it would look like a rotation. It's not in the Euclidean sense. It is a rotation in this hyperbolic sense. So just to compare that, here is what we would have for space-to-space transformation. And now we have space-to-time in a form that looks very similar. So it's a nice way of thinking about how the Lorentz transformation can be given a kind of geometrical interpretation in terms of this exotic rotation. A while back, we described this curious idea that if two observers are very far apart from one another, then even at modest speeds, their conception of what's happening at a given moment of time can be radically different. And now we have enough machinery at our disposal to show the mathematics behind that. Spacetime diagrams are a particularly nice way of showing this. So let's set it up in the formalism of spacetime diagrams. So let's get some axes into the story here. Let's imagine, say, that this is my t-axis, and let's say this over here is my x-axis. Let me just label those so we don't get confused. Here's x, and here is t. And if you recall, this scenario involves, say, me. Let's just be concrete. Here I am sitting still at the origin initially, and very far away there is an alien. We can even give the alien a name. Let's call it Chewbacca or Chewie. Why not, right? So here I am. Here is the alien. And what happens, of course, is over time I move up my t-axis because I'm just sitting there and time is evolving. So I go, say, up the axis. And let's say we consider this moment in time over here. And Chewie is assumed to not be moving relative to me initially. So Chewie also just goes up this t-axis. And at any given moment in time, we all agree on the now slices. We all agree on what's happening at a given moment. So let's say at this moment in time, we all agree what's happening. At this moment in time, we all agree with what's happening, and so on. Good. Now, if you recall the scenario, what happens is, at a given moment in time, Chewie gets restless and decides to get on a bike, say, and ride directly away from Earth. Let's do that case. Let's make the moment when Chewie gets up and starts to move, say, right here. And we know that we, in a space-time diagram, can show the trajectory that Chewie follows. Let's say it's something like that. And that then should be labeled correctly as the t prime axis for Chewie. Now, what about the x prime axis? That is, what about space at a given moment in time from Chewie's perspective? Well, to draw that, let me just put a little bit of reference in here. So let me put, say, a little line. Let me use a different color so we don't get confused. So right over here, say, is the x-axis at that moment in time from our perspective. And we know that from our understanding of space-time diagrams that the x prime axis for Chewie will look like this. So it's symmetric relative to the x and t axes for me. And now I can label that. So labeling that with, say, this guy over here. Here is the x prime axis for Chewie. So this now represents points in space that Chewie says are happening at a given moment in time, right? Now what I want to do is simply extend this line. After all, it refers to all of space. So why don't I fill it in to see what it includes when we are focusing upon what's happening near planet Earth. So let's take this guy and now going to just extend it back. And notice that whereas from my perspective, I am over here, and this point and this point both lie on the same now slice before Chewie starts to move. This is the beauty of this whole thing. So here is the now slice at that moment before Chewie starts to move. Chewie, who's over here, and I'm over there. We both agree on what's happening at that given moment in time. So here I am, here Chewie is, perfect agreement. Chewie then gets up and starts to move, and now Chewie's notion of all of space at a given moment in time changes. It has swept into what I consider the past. Now, we can go further. How much has it swept into the past? Well, let me just put some symbols in. Let's say that Chewy and I are a distance d apart. We know from our understanding of space-time diagrams that the slope of this line, right, the slope is equal to v. And if you know the slope of a line, you easily can work out how much it rises or falls over a given distance. The very definition of slope is the amount that this drops over a distance d is equal to, so the drop is simply equal to the slope times the distance, which means that this change, this sweeping back in time, is an amount delta t, which is equal to this quantity, v times d. Now, we can take that a little bit further because I have been working, as we always do in space-time diagrams, with the units where c is equal to 1. Now, if we want to put c back into this so we can use more familiar units, in that case, of course, rather than thinking about the velocity as something between 0 and 1, we can think of it as any number between 0 and c if we look at v over c. So if I were to replace this by v over c, that would allow us to put c back into the equation. But one little subtlety with the units, of course, if I'm not using units where c equals 1, then I really need to choose my units such that this ct and this guy over here, x, have the same units, right? This will make them both equal to a length. So this would tell us that the drop in ct, the sweeping back in ct, is vd over c. And that implies that the drop in t itself is equal to vd over c squared. And by drop in t, I mean the amount of time that Chewy's now slice has swung into what we consider the past. And of course, I won't bother doing it, but you can easily see if Chewy was not going away from Earth, but was going toward Earth, this would then sweep that direction and would sweep that amount into what we call the future. So let's put some numbers in here because we have a formula and it's fun to see what it gives us. So there is the formula, minus v times d over c squared if Chewy's going away from Earth. If going toward Earth, it's vd over c squared. And let's assume that Chewy is very far away, 10 billion light years away. But let's assume that the velocity involved is pedestrian, everyday speeds. And I've used miles per hour there, 6.71 miles per hour, just chosen that it makes the math work out well. And if Chewy gets on the bike and goes at that speed, 6.7 miles per hour, the amount by which this slice will sweep into the past is equal to 100 years, right? And similarly, if Chewy gets on the bike and goes toward Earth, the now slice will sweep upward 100 years into the future. And of course, the reason why we care about this, I emphasized this earlier, but now we see the equations behind it. If we ask ourselves, what is real? What's happening at a given moment, right? That's what we consider to be real. Well, Chewy and I both agree on what's happening at this moment. Therefore, I am willing to accord Chewy the status of saying, I agree. If you tell me something's real, I am going to put that in my list of things that are real. When Chewy gets on a bike, we don't suddenly discount that idea. And now Chewy says that things that we consider to be in the past are real. And that leads us to conclude that the past should be on our list of things that are real too. Going to the future would just require Chewy to ride the bike toward Earth. And that gives us this idea that the past, the future, and the present are really all on the same footing. From this relativistic perspective, they are all equally real. So to get a feel for the mathematics that we've just derived behind this idea, let's take a look at one of our demonstrations. Let's bring it up over here. And in this demonstration, what you can do on your own is you can choose the distance to some observer, some alien being, if you'd like. So that is moving this red dot along the axis here. And you can choose the velocity of that observer. So if initially that observer is not moving relative to you, then you can't even see that observer's now slice because it coincides with your own. But then if the observer starts to move, say, away from you, their slice, if you can see it, may be coming close on this one, this red dot. It's a little bit faint. But these red dotted line here, this is the alien observer's now slice, that the observer is moving away from Earth. And if the observer turns around and comes toward Earth, it will sweep into the future. So there you can play with it, get a feel for the effect of distance, the effect of speed. But the main point I want you to take from this, beyond the startling idea that past, present, and future seem to be on equal footing, I want you to take the idea that relativistic effects don't only just kick in at speeds that are close to the speed of light. They only kick in at those speeds locally, but if you're looking over large distances, then that large distance can amplify a tiny effect, even when the speeds are small, into a large impact on what we consider to be happening at a given moment. Different frames of reference will have a different perspective on when and where events take place. They'll have a different set of space and time coordinate values for any given event that we are considering. And that is one of the beauties of the special theory of relativity, to go from the location and time that one person says something happens to the location and time that another person says that they happen. Now, that being the case, it is often useful to have quantities that everyone agrees on. They provide, if you will, a kind of anchor. They provide quantities that transcend the differences between different perspectives. So it's useful to find what we call invariants. So invariants are those combinations of coordinates that do not vary from one frame of reference to another. That's what I'd like to derive for you, some space-time coordinate invariants. To do that, I'm going to break the discussion up into a couple of pieces. I'm going to start where things are more familiar, invariants of just spatial coordinates. And after we cover that material, which is probably totally familiar to you, we will generalize to the case where time is part of the story too. Okay, let's begin with a familiar example. Let's imagine that we have two grids, and I'm going to use the grids that I've introduced earlier. They're going to have a common origin. Let's be concrete. Put that origin, say, at the Empire State Building. And we are going to look at the fact that the Chrysler Building has different coordinate values in the different coordinate systems. And then we're going to try to use those coordinate values to find what it is that the two coordinate systems agree on. OK, so here's coordinate system 1. There's coordinate system number 2. If we, again, pull these guys apart, Chrysler Building has coordinates 4, -3 in one system, coordinate 5, 0 in the other. But as no doubt you know, there is a combination of those coordinates that everybody will agree on. All we need to do is consider the sum of the squares of the coordinates in each system. So just by way of review, let's do that. So for the Empire State Building, it's at 0, 0. In both systems. Chrysler's at 4, -3 in the red system. It's at 5, 0 in the green system. And now if we look at the sum of the squares of those coordinate differences, we'll get 4 squared plus -3 squared is 25 in the red system. We'll get 5 squared plus 0 squared equals 25 in the green system. And they agree. Now, why do they agree? We all know why they agree. We're talking about, with that particular combination of coordinates, if I take the square root of that number, I'm talking about the distance between these two locations. And the distance between here and here doesn't care about the coordinate system that you might happen to use. The distance doesn't change when you start rotating coordinates. It's just the coordinate labels that change. And this particular combination of the coordinate labels is, by the Pythagorean theorem, the distance between these two locations in either system. And therefore, that number has to agree because distance is a coordinate invariant. Doesn't care about the coordinates that you use. OK, so that's a familiar idea. Let's just make certain that we're all on the same page by fiddling around with a little demonstration. And this demonstration, you get to choose the angle between the two coordinate systems, and you get to pick the location of the point of interest. So that's the yellow dot. And the thing that I want you to take away from this demonstration is that if you look at this number as I vary the angle, the coordinate values will change, but the sum of the squares will not. So here we go. Notice that the numbers are all changing, but 127 in this particular case is fixed because that is the distance of that point from the origin, and the distance doesn't care about the coordinates that you use. So this is a good model for thinking about invariance of a coordinate system. We're now going to jump off from this example to put time into the story and look for invariance of space-time coordinate systems. We've seen that different spatial coordinate systems will all agree on the sum of the squares of the coordinate values of a given location because that gives us the distance of that point from the origin. Distance, of course, is something that doesn't care about your coordinates. So all coordinate systems will, for instance, agree on the sum of the squares. I could take a square root, but it doesn't matter because if the sum of the squares agree, then the square root will as well. Now, we want to move on to include time in this story. And here is the claim. There is an analogous expression that uses the space and time coordinates of a given event that all observers, regardless of their relative motion, will agree on. And there is the expression right there. If we take minus c squared times t squared plus x squared, regardless of which coordinate system you are using, the answer, we claim, will be the same, much as in the spatial case, the sum of the squares of the coordinates will be the same. The difference, as you can see, is that there is a curious little minus sign that comes into this space-time coordinate invariant. That indicates really the difference between space and time. But let's see if we can prove this result. And of course, the way you prove it is much the same way that you prove this result in the spatial case. If you want to prove this result, you just make use of the relationship between x and x prime, y and y prime, using trigonometry. Plug it in, and you find that the result is independent of the angle between the systems. We're going to play exactly the same game here, where we're going to make use of course, the Lorentz transformation. That relates t and x to t prime and x prime. So we're just going to make use of that dictionary between the two coordinate systems. OK, so what is the Lorentz transformation? I remind you, t prime equals gamma times t minus vx over c squared. And x prime is equal to gamma times x minus vt. And now what we want to calculate is c squared t prime squared minus x prime squared. That's the same invariant that I have over here. I've just multiplied it by a minus sign, which won't change anything at all, because I'll do it on both sides. We want to know, is this in fact equal to c squared t squared minus x squared? So let's go ahead and just calculate this particular combination of the coordinates, see what we get. OK. Straightforward to do. So let's look at t prime squared. That is equal to gamma squared times t squared minus 2vxt over c squared from the cross term plus a v squared x squared over c to the fourth from the last term. OK, that's t prime squared. Let's look at x prime squared. So x prime squared is equal to gamma squared times x squared. The cross term here will be minus 2vxt. And then the final term will be the square of this guy, which is v squared times t squared. Now let me just put on the side, just so that we remember, as I'll be using it, that gamma squared, of course, is equal to 1 over 1 minus v over c squared. Again, it's because I'm looking at gamma squared. All right, now let's look at the difference then. C squared t prime squared minus x prime squared. What does that equal? Well, I'm going to organize the calculation by just looking at the quadratic, the linear, and then the 0th power of t, what those terms look like. So what do we have for the quadratic part? The c squared I'll just pull out in front. Where do I have t squareds in this expression? Well, I have 1 over here with the gamma squared in front, and that gives me a factor, therefore, of 1 over 1 minus v over c squared from that guy. What other t squareds do I have? Well, I've got an x prime squared. If I look in that expression, I've got a v squared t squared. But since I pulled out a c squared in front, bear in mind, I've got to compensate for that. And I have a minus v squared over c squared, therefore. And then the gamma squared, that happens in both of them, 1 minus v over c squared in the bottom. OK, that's the quadratic term. What about the linear term? Where do I have linear terms? Well, I have 1 over here, so I've got a 2vx coefficient. That c squared will cancel against the c squared that I have over here, and therefore I will just be left with minus 2vx divided by 1 minus v over c squared. Any other linear terms? Well, in x prime squared, of course, I have 1 over here. That minus sign combines with that minus sign to give me a plus sign, and that gives me a plus 2vx divided by 1 minus v over c squared. Good, that's the end of t squared and t. What about terms that have no t's at all? Well, let me pull out an x squared in front and look at all of the coefficients that arise in front of x squared. So I have an x squared over here, so I've got a v squared over c to the 4th, but the c squared will make that a v squared over c squared. And the gamma squared, again, will still be in front, 1 minus v over c squared. Where else do I have x squared? Of course, I have 1 over here as well, and that will come with a minus sign from the minus sign in front of x prime squared. So that's a minus 1 over 1 minus v over c squared. All right, now we are in good shape, because let me look at what cancels against what. So this term cancels against this. So I have 0 in front of t. What about over here? Well, I've got 1 minus v over c squared in the bottom, and I've got 1 minus v over c squared in the top. So those guys cancel and give me just a factor of 1. So I get a c squared t squared times 1 from that coefficient. What about the x squared coefficient? Well, it's just the reverse of what I had over here. So instead of getting 1, I will get minus 1. So this guy comes together to give a minus x squared. And indeed, we have now established what we were after. Our goal was to show that this is a coordinate invariant. And by direct calculation, we have now shown that this is true, because we've calculated this guy over here and shown, indeed, that he's equal to this combination over there. So that is the proof that this combination that we were looking at, minus c squared t squared plus x squared, is something that all observers, regardless of their state of motion, will agree on. Let me just give you one note that's worth stressing. When we were looking at the distance from a given point P to the origin, we were actually looking at coordinate differences, right? So when we look here at x squared plus y squared, that really is the difference in the x coordinate from the origin, the difference in the y coordinate of that point from the origin. It's coordinate differences, of course, because you look at distance between 2 points. Implicitly, if one of those points is the origin, you don't need to write down 0, but it is there. The same idea holds here when we're talking about space-time distance. This is often called the space-time distance or the space-time interval. And it, too, should be thought of as a distance that involves 2 points. The point of interest, who has coordinates t prime and x prime in one system, or t and x in the other system. But implicitly, those distances, those coordinates, are relative to the origin. So if you then want to be general, and in this case consider the distance between any 2 points, not just the point and the origin. If you had 2 points, you'd look at delta x and delta y between those 2 points and calculate delta x squared plus delta y squared. Same thing holds true in the space-time setting. If you've got 2 events whose coordinates are t1, x1 and t2, x2, you want to look at the space-time distance, the space-time interval between them. You look at delta t and delta x, and you calculate exactly the same combination of coordinates with t prime replaced by delta t prime, x prime by delta x prime, similarly delta t and delta x. How would you prove that that is invariant? It is exactly the same proof because the Lorentz transformation is linear. And because it's a linear transformation, I can simply replace all of these t's and x's by delta t's and delta x's, and the proof will go through exactly as we did it for the case of t and x. So that is our argument that we have now identified an invariant that all observers, regardless of their motion, will agree upon. It is the analog of distance for space. This is the space-time distance between 2 events. Let's look at a little example where we can see this space-time distance or this space-time interval in action. So let's imagine that we have a rocket that's being viewed from the Earth, and it's traveling at a constant velocity, we're told, for 13 years. From the perspective of those on Earth, it covers a distance of 5 light years. We want to know how many years pass on the ship's clock. You can solve this problem simply by calculating gamma using the time dilation formula. Straightforward to do. Let me just show you the alternate approach that you could follow that makes use of this space-time invariant. How does that go? Well, let's look from the perspective of the Earth frame. What is the data that we are given? So we are told that delta t is equal to 13 years from the perspective of those folks on Earth. We're told that delta x is equal to 5 light years. And again, this is all in the Earth frame. And we want to work out what's happening in the rocket ship frame. Now, in the rocket ship frame, that frame moves with the ship itself. So what that means is that delta x prime is equal to 0 in that frame. And we're asked to figure out what delta t prime is. And now we can do that by making use of the invariant space-time interval. So we just calculate away minus c squared delta t squared plus delta x squared. We'll put numbers in there for a moment. But the conceptual idea is that this thing is equal to minus c squared delta t prime squared plus delta x prime squared. And since delta x prime is equal to 0 in the rocket frame, since the frame moves with the rocket, this gives us c squared times delta prime squared. We know delta t, we know delta x from the data that were given in the problem. Therefore, now we can solve for delta t prime. So now it's just a matter of plugging in some of the numbers. And what you will therefore get here is c squared times delta t. We know, again, if you c equals 1 light year per year, to make life simple, then this 13 years turns into 13 light years. If you square that, that will be minus 169 light years plus 5 squared light years, so plus 25, equals 144 times light years squared, and that's supposed to be equal to, I should put a minus sign there. That's supposed to be equal to minus c squared times delta t prime squared. And of course, that means that delta t prime is equal to 12 years. So it's just a little example where you can see the space-time interval come into its own. And the nice thing is we were able to calculate that result without having to calculate gamma. We just made use of the invariance of the space-time interval to get at the answer. So that gives you some feel for the way in which you can make use of this invariance. To get a better feel for it, you should play around with this little demonstration where you can see how it doesn't change as you change reference frames. So we just did an example of that. But let's take a look at an example over here. So in this demonstration, you get to pick the space-time coordinates of some chosen event. Choose them at random if you'd like. And then let's vary the speeds between the two frames. And look, all of the coordinates, t prime, x prime, are varying as we mess things around here. But the value of the interval between them, this number over here, is not changing at all. So look way over there on the right-hand side. These numbers are rapidly changing, but the interval itself stays fixed. So that is a demonstration of the invariance of the space-time interval as you change from one frame to another. And we've given an example of how to put this invariance into practice to solve problems in a somewhat different way. We've seen that different observers that are moving relative to one another do not agree on the amount of space, distance between two events. They don't agree on the amount of time, the time interval between two events. Nevertheless, we've seen that there are some things that they do all agree on, the space-time invariant interval being a prime example. But what about the issue of cause and effect? Do all observers agree on whether or not one event can be the cause of another? Right? So let me give you a little example, silly little example to get us going on this question. So imagine that Gracie is over there at the origin. She throws a baseball and gives George a black eye, right? So her throwing the ball is the cause of the effect being George gets a black eye. And the question we want to ask is, if you look at that sequence of events from the perspective of another observer moving relative to that frame of reference, will they necessarily agree that Gracie's act could be the cause of that effect, or will they come to possibly a different conclusion? That's the question. Let's frame it in the language of space-time invariance and see if we can get a nice quantitative understanding of whether or not all observers agree on this issue of cause and effect. Okay, so let me set up space-time diagram over here. And let's look at that example of Gracie throwing a ball and hitting George. So assume that Gracie is over there at the origin of these coordinates, and she throws the ball from here. She throws it, of course, with a speed that is less than the speed of light, which in the context of space-time diagrams means that the slope of the trajectory of the ball must be larger than that of 45 degrees, which is the trajectory of a light beam. So that might be the trajectory of the ball, and over here is where the ball hits George in the eye. Now, mathematically, what is the requirement for the possibility of having cause and effect? Well, it's just that this trajectory must have a velocity less than the speed of light. So it must be, therefore, the case that the distance between the two events must be less than the distance that light could travel in the amount of time that is separating those two events. And that is just the statement that delta x over delta t, which is the velocity of this signal, if you will, is less than c. So is it the case that all observers will agree on whether or not there is the possibility for a signal to go between this event and that event? And the answer to that is yes, we can make use of the space-time interval. Let me frame this in that language. So this being the case, what does that imply? That implies that if I look at minus c delta t squared plus delta x squared, because of this relationship, this is negative. These are the same statements. But remember, all observers will agree on the invariant interval. So all observers will agree on the fact that that combination of coordinates is negative. So once we recognize that a causal link, so a causal link between two events is tantamount to requiring that this equation holds true for their coordinate differences in space and time. If one observer says that this holds, all observers will say that this holds because they all agree on the invariant interval. So they all will agree, regardless of their motion, that Gracie's action could in fact be the cause of George's black eye. So the statement then is, by looking at the notion of a causal link using the invariant interval, we come to the conclusion that all observers will agree on this quantity, so they will all agree that there can be a causal link between those events. Now that's a special case of the possible values of the invariant interval between events. Let's look at the more general situation where we can imagine that if we have two events whose coordinates, say, are t1x1 and t2x2, so we have delta t and delta x, there are three possibilities for the sign of the invariant interval. Of course, it can be negative. That's the case that we just looked at. It can be positive, or it can be equal to 0. So if I draw some examples which illustrate those possibilities, let's, in order that we see where the speed of light comes into the story, let me draw that 45-degree line right here. So there is the trajectory of a light beam. And the idea is, if we have locations in the space-time diagram, let's choose one of the events to be the origin to make life simple. And the second event, say, could be over here. So these guys have an invariant interval which is negative. If I want one that's positive, I can say choose a location over there. And then if I look at, choose another color for that one, if I look at this separation in space and time, there's very little time, a lot of space, which means this will overwhelm that. And so the invariant interval here will be positive. So this guy will be positive invariant interval. This guy will be negative invariant interval. And this guy over here will be 0. So for light, c delta t equals delta x. So that combination will give you 0. OK, so what do we make of those particular invariant intervals? Well, much as we just found, that in order to have a signal traveling from one event to another, you need the speed of that signal to be less than the speed of light, which translates into the ability of one event to affect the other. So that's the case over here. So this trajectory is a signal that has a velocity less than the speed of light. What about the case when it's positive? Well, if the invariant interval is positive, then if you looked at the purported speed of a signal going from here to here, that would have a velocity bigger than the speed of light. That's not possible. So all of the events in this region over here under the light signal, these guys are causally disconnected from the origin because there's no way for a light signal to travel from the origin to any of the locations in here, because the light signal is the fastest signal that there is. Nothing can go faster than the speed of light, so there's no way for this to affect anything in this region. But anything that is above the trajectory of a beam of light, and for completeness, let me also show the beam of light going in the other direction as well, so we can get a full picture going over here. So the beam of light can go this way. In the one-dimensional sense, it can also go that way to the left. And let me keep this nice and symmetric. So all of the stuff in this region has invariant interval positive. Similarly, for this region over here, in this region, the invariant interval is nice and negative. So all of the stuff in here is causally connected to the origin, which is simply the statement that you choose any event in here and you write down the trajectory of a purported signal to go between the origin and that location, and all of these signals travel at less than the speed of light. So that gives us our picture that if the invariant interval is negative, one event can be the cause of the other. If the invariant interval is positive, one event cannot affect the other. And again, all observers will agree on this regardless of their motion because they agree on the value of the invariant interval. Special case when the invariant interval between two events is 0, such as that location at the origin and, say, this event here or this event here. They can be causally connected, but the signal, of course, that gives the causal link must be a beam of light, because you need to travel at the speed of light in order to connect them. Okay, so that is the basic idea of causality in the language of invariant intervals. We now find that all observers do agree on whether or not events are causally connected or disconnected. The terminology that we typically use is we say that if two events are potentially causally connected, if the invariant interval between them is negative, we say that they are time-like separated. That's just the language. If the invariant interval is positive and they're causally disconnected, we say that they are space-like separated. The language makes sense because basically we're saying causally connected points, there is a lot of time between them but a little bit of space, say in this frame of reference, and that's why we say they're time-like separated. Here we have a lot of space and a little bit of time. They're space-like separated. And the boundary between the two, where they can only be connected by a beam of light, we say that they are light-like separated. So those are the three possibilities. And this holds true, of course, regardless of what point you choose as your initial point. Any 2 points can be put into this framework, and we can determine whether or not there is a potential causal link between them. So let's look at a little demonstration where you can play around with this on your own. So in this demonstration, you are able to pick whether you want to look at all locations that are causally connected or disconnected from a given point. If the given point is the origin, let's look at the causally connected region. So the causally connected region is all of the points in here. I also put the points down here because these are the points, of course, this guy can't affect anything in the past, but all of these points can affect whatever's taking place at this location. So all of these points can have a causal link in the manner that we just described. If instead you want to see the causally disconnected points, so these space-time locations are such that somebody at the origin could not affect them. They would have to send a signal faster than the speed of light in order to do that, and that is not possible. And of course, what separates the two is what we call the light cone, which are the trajectories of a beam of light that's emitted from the origin. And what you should do is you should play around. You can change the reference point that you are using. Let's say this is where you are standing, and you want to know what points you are causally connected to. Of course, this is cut off here. There's not much room on the right-hand side of the demonstration. But as you see, it's the same idea. This cone of points above, the cone of points below. Let me bring that back so it's a little bit clearer. But you should play around with moving this, and there you see the idea of causally connected and causally disconnected points. But the bottom line is, which is reassuring, all observers will agree on causality in the sense that if one observer says this event could be the cause of that, then all observers will agree on that. There's a fun little fact that comes into play when we're talking about whether or not two events are causally connected in space-time. Let me describe it to you. It's the following fact. So if you have 2 points that are causally connected, the invariant interval between them is negative, then the claim is there is a frame of reference such that those 2 events happen at the same place in that new frame of reference if its velocity is chosen correctly. And if 2 events in space-time are causally disconnected, if they're space-like separated, the claim is there is a frame of reference in which those 2 events happen at the same time. In the boundary case, we say that they will lie on a causal boundary, and we'll describe what that means in a moment as well. But let me try to establish this fact for you, and it's easy for us to do. So let's set up a new space-time coordinate system here. So here we'll say be our t-axis. This will be our x-axis of our initial system. And let's choose one of our events to be at the origin to keep life simple. And let's look at another event with which there is a causal link because the invariant interval will be negative. And let's figure out what frame of reference it would be in which these 2 events, as we see, happen at the same place. How can we do that? Well, it's pretty clear what we do. Here is that frame of reference. Let me draw it in red. So this will be my new t prime axis passing through those 2 points. And this will be my new x prime axis, chosen again so that its angle relative to x is the same angle of t prime to t. So let me now mark these guys. So if I take this to be x prime, this to be t prime, this is a single location in space over many moments in time. So from the perspective of the red frame, this white dot and this white dot, this event and this event are happening at the same place. They're happening at the origin in this coordinate system, but they are happening at different moments in time. Now, is this a sensible trajectory? Can that actually be achieved? Of course, because the very fact that these points were causally connected means that a signal can go from here to here at a speed slower than the speed of light. And all we're doing is we are riding along with that signal in this particular frame of reference. So in the example where Gracie was throwing the ball at George, imagine you go into a frame of reference where you are moving with the baseball. From your perspective, Gracie throwing the ball and the ball hitting George in the eye, those are happening at the same place in your frame of reference, and here is that frame of reference. For the other case, if we are looking at events that are space-like separated, let's do that over here. Let me choose another point for a space-like separated event. Let's choose one, say, at this location. The origin and that point are space-like separated. No way for a signal to go between them, but the claim is there is a reference frame where those 2 events happen at the same time. What is that reference frame? Well, I'll draw it for you. So let's choose another color so we can keep this straight. So I'm going to choose my new x double prime axis. Let me see if I can get this to go through. Hey, that's not too bad. So that will be my x double prime axis. What about my t double prime axis? I just choose the same angle over here. So that guy comes down. Yeah, it's not perfect, but pretty close. Let me mark those to keep them clear. So this guy will be x double prime. This guy will be t double prime. And in the Greene system, these two space-like separated points are happening, as you see right over here, they're happening at the same moment in time, right? Different locations in space, same moment in time. That, in fact, is t double prime equal to 0. It's the origin in time from the Greene frame's perspective. So there you have it. You can immediately write down frames of reference that establish the claim. If you like to do things algebraically, you, of course, can do that too. So if you want to write down the equation, for instance, in this particular case over here, where we wanted this point and this point to happen at the same location, the equation you would solve, therefore, is delta x prime equal to 0. Now that, of course, is gamma times delta x minus v delta t. Setting that equal to 0, you simply have delta x equals v delta t, and it's just obviously giving you that the velocity of this frame, you choose it to be the spatial separation between this point and this point in the original frame divided by the temporal separation. But that's just saying what I said before. You're moving along with the baseball, and in that frame, the two events are happening at the same location but at different moments in time. You can play the same game for the space-like separated ones, but I encourage you to do it, but you'll see that it works out just the same. So the nice thing here is we have a nice picture of what it means for events to be time-like or space-like separated. So they are time-like separated if there is a frame of reference in which the only thing that separates them is time. They are space-like separated if there exists a frame where the only thing that separates them is space. That's where the language comes from. This also gives us a nice physical interpretation of what the invariant interval is, because in the case where there is a causal connection, what is the meaning physically of the invariant interval minus c delta t squared plus delta x squared? Well, look, in this frame, delta x prime is equal to 0. So if we plug that in to this expression, delta x prime equal to 0, tells us that the invariant interval is nothing but minus c delta t prime squared. And that is something that obviously we can interpret. That's minus c squared times the time in this frame between the events. So you can think about the invariant interval in that case as minus c squared times the amount of time that elapses on a clock that is moving with the signal from one person to the other, from the cause to the effect. So going back to Gracie and the baseball, baseball is traveling along. If we travel with it, then from our perspective, the ball is at one fixed spot. We look at our watch between when Gracie throws it and when it hits George in the eye. That amount of time, delta t prime, multiply it by minus c squared, that is the meaning of the invariant interval. So you can think about the invariant interval between two causally connected points as minus c squared times what we call the proper time, the amount of time that elapses on a clock for which these two events are taking place at the same location in space. Good. What about the other case? Oh, and I should say, point of notation, we often introduce the symbol tau. I'll come back to this later, which is why I'm mentioning it now. We often call tau the proper time to distinguish it from the laboratory time, which we often use t. So the amount of time that elapses on a clock that is traveling along with the signal from one event to the other is the proper time between those two events. What about the other case? If they are causally disconnected, what then is the meaning of the invariant interval? Well, it's pretty clear, right? So what is the meaning of minus c squared delta t double prime squared plus delta x double prime squared? Well, look, the invariant interval between these guys, minus c squared delta t double prime squared plus delta x double prime squared. This now is equal to 0 in that frame of reference. So all we get, therefore, is delta x double prime squared. So the invariant interval between this point and this point is nothing but the distance between them measured in a frame of reference where those events happen at the same moment in time. So that we call the proper distance between the two events. And that is the way in which you should think about the invariant interval. When there's a causal link, it's the proper time between the events. When they are disconnected, no causal link, it is the proper distance in space between the events. You remember that earlier I gave you an intuitive way of thinking about time dilation, I described it as a mental mnemonic for thinking about why it is that when a clock is in motion from your perspective, it ticks off time at a slower rate. And just to remind you what I described how, by analogy, with a car, right? So if a car is going fully in the northward direction, all of its motion goes toward the north. But if it veers off to the east by varying angles, it won't travel as quickly in the northward direction as it did when it was pointed directly north, because some of its motion has been diverted from the northward direction to the eastward direction. And I encourage you to take that idea to heart and apply it not just to one space dimension and another space dimension, but rather to a space dimension and a time dimension. So remember how that went. I said, look, if I'm right here right now, I seem not to be moving. Remember, I described it, but I am moving because I'm moving through time. And then I said, if I start to walk, I divert some of my motion through time into motion through space, so my passage through time slows down. Now, I also mentioned to you that there was a mathematical way of thinking about that idea. Let me show you now, because we finally have the machinery to do that, how that mathematical justification goes. All right, so to do so, what I'm going to do is the following. Let me imagine two frames of reference. One of those frames of reference will be, say, your frame of reference watching me, and the other frame of reference will be my frame of reference where I'm moving with my own watch. And let's look at the invariant interval between those two frames of references, where, say, I'm looking at the events of interest being my watch going tick and then tock, right? Now, from my point of view, my watch going tick and tock happens at the same location in space because, after all, I am moving with my watch. So the invariant interval, if you recall, when events are happening at the same location in space, is nothing but what we call minus c squared times the proper time. It's the amount of time that I see elapse on my watch, minus c squared times the proper time squared, which we often write as minus c squared delta tau squared, proper time squared. I introduced this notation earlier, but this is, of course, what it means. I am going to choose my units so that c equals 1, just to make life simple. So the invariant interval from my perspective, therefore, is just minus delta tau squared. What about the invariant interval from your perspective, in your frame? Well, you will say that this is equal to minus delta t squared plus delta x squared. That's the invariant interval between tick and tock as you are watching my clock evolve forward in time. Now, let's write this then as delta t squared equals to, I should say delta tau squared is equal to delta t squared minus delta x squared. And let me just play around with this. And again, of course, the equality here is just the equality of the invariant interval, right? I'm hopeful that you remember that fact. Let me bring the delta x squared over to the other side and write the equation like this. And now let me divide through by delta t squared. So I will write the equation as delta tau squared over delta t squared plus delta x squared over delta t squared is equal to 1. And that's a very simple set of manipulations, but that little equation written in the form here is particularly striking when we think about what it means. So let me just indicate in English what this means. So if we look at this term over here, what is that? So I guess I'll write it on the other side. This is equal to the rate of elapsed time, the rate at which time elapses, I should say. So rate of elapsed time, rate at which time elapses on my clock. That's delta tau, so that's squared, divided by the same rate at which time elapses on your clock, right? Because your clock is governed by delta t squared, plus what is delta x over delta t squared? That is simply my speed. From your perspective, my speed squared is equal to 1. And let me box that guy up too, because in English, that makes clear the point that I was making. As my speed increases, right, this quantity must decrease because the sum is fixed. It must be equal to 1. So when my speed, say, is equal to 0, the rate at which time elapses on my clock is equal to the rate at which time elapses on your clock. That will then make this equal to 1. The equation is satisfied. But when I get up and I start to move, this term gets bigger and bigger. Never gets bigger than 1. My speed is always less than the speed of light. But as it gets bigger and bigger, this must get smaller and smaller. Or mathematically, this term gets smaller and smaller. What does that mean? It means the rate at which time elapses on my clock compared to yours gets smaller and smaller. My passage through time, the rate at which my clock is ticking, slower and slower compared to yours because my speed through time is being diverted into my speed through space. There it is. That's the mathematical justification for this idea, which is, again, a wonderfully intuitive way of thinking about why it is that time slows down for a clock in motion. The rate at which time elapses slows down because you are diverting the motion through time into motion through space. That's the mathematical justification for this very nice way of thinking about time dilation. The pole in the barn paradox. It's one of the famous paradoxes of special relativity, and maybe a paradox that already occurred to you as we've gone through our discussion. We're going to talk about it now, but let me first stress at the outset that there are no paradoxes in special relativity, right? If there were a real paradox, that would mean that the theory was inconsistent. There can, however, be, and this is what we are going to encounter right now, there can be what we might call seeming paradoxes, right? Which are situations where, from the perspective of two different observers, it seems like they're coming to conclusions that are so opposite to one another that there's no way that they can be reconciled. But the thing is, every time, if we carefully examine the situation, we find that we are able to resolve the issues, okay? So I want to show you how we resolve the issues in this particular so-called paradox. All right, to set it up, there are a couple of characters in this paradox, some animate, some inanimate. So we are going to have a pole 15 feet long when it's at rest, okay? We are also going to have a barn. We are going to stipulate that the barn is 10 feet long when you measure it at rest. Yes, it's a pretty small barn, but we're just using it for the example so that we can see what the seeming paradox is. So what is the seeming paradox? Well, when at rest, if you try to put a 15-foot pole into a 10-foot barn, it doesn't fit, right? Good, that's straightforward. But now let's imagine the following scenario. Let's imagine that the pole is moving toward the barn at very high speed. Let's say it's moving toward the barn at 12/13 the speed of light, really fast. Calculate gamma for that high speed. What do you get? Well, you get 13 over 5. Now, if you take 13 over 5 and you use it to look at the length of the pole from the perspective of the barn, or someone who's at rest relative to the barn, the length of the pole drops from 15 feet to 15 over gamma, and with gamma equal to 13 over 5, the pole's length becomes 5.8 feet. So it seems that from the perspective of the person in the barn, as the pole rushes by, it should fit. But from the perspective of the pole, or someone running with the pole, they come to a very different conclusion, because they say that the barn is Lorentz contracted. So it's not even 10 feet, it's less than 10 feet. Put in the numbers, you get 3.8 feet. So from the perspective of the barn, the pole fits. From the perspective of the pole, it doesn't fit. Seeming paradox. Okay, so let's see that visually so we have the issue clear. Here's how it goes. So we're going to take Gracie to be our observer who is at rest relative to the barn. George will be our carrier of the pole, so he will be running with the pole, making it go really near to the speed of light. So let's set this up and put it into motion. There he goes, and he's going to run toward the barn, and again, this high speed, which we're taking to be 12/13 c, and we want to see what Gracie says, and we will see that she says that the pole fits because it's length contracted. There we go, right? So you saw that from Gracie's view, the pole fit. That may have been a little bit fast. Of course, 12/13 the speed of light is fast, but let's use the wonders of animation to slow down 12/13 c so we can actually observe from Gracie's perspective what's happening. Okay, so here George is coming in, and he's now going, again, at very high speed. From Gracie's view, the pole is length contracted, and because it is length contracted, it fits inside the barn. So that is Gracie's perspective. Now let's take a look at George's perspective, the pole's perspective, okay? So as we described, from his perspective, the pole will not fit, but let's see that. So his view, it went really fast. Maybe I should show you that one again. So from his view, he's going by at such a high speed that the barn is shrunk. So there it is. The barn, from his view, is length contracted. So his pole, it didn't fit even when it was at rest. Now it doesn't fit even more dramatically, because from his perspective, it is the barn that's in motion. The barn is contracted, and therefore he comes to his conclusion that it doesn't fit. Okay, that is the paradox, or the seeming paradox. So the question, of course, is, what is the resolution? We want to know who is right, right? From the pole's perspective, it doesn't. The barn's perspective, it does. And the answer is, and you perhaps are not surprised by this answer, they're both right, right? They're both right. Now, how can they both be right? Well, let's just clarify that a bit. When we say they're both right, what I mean is each can make perfectly good sense of the other's seemingly contradictory claim, right? They have different perspectives, different claims, yet they can reconcile them. Why is that? Well, here is the key point. When we talk about the length of an object, that invokes a notion of simultaneity, right? We are referring to the measurement of the front and the back of the object at the same moment in time. Now, if two observers are in relative motion, we already know that they have different conceptions of simultaneity. They will have different conceptions of length. So one can conclude, and rightly so, that the pole fits inside the barn, and the other can conclude, rightly so, that it doesn't, because they have different conceptions of simultaneity. They therefore have different conceptions of the length of objects. Now, to make that idea a little bit more precise, let's look at their different conceptions of simultaneity a little bit more closely. And to do that, let's adorn the pole and the barn, say, with clocks. So we will now have a pole that has two clocks on each end, and the barn will have a clock at each opening of it. And we want to understand from each perspective how the other comes to the seemingly contradictory claim. If we can do that, if we can tell a coherent story about how the other came to their bizarre sounding claim, all of the seeming paradox will go away. So let's do that. So, question is, from Gracie's perspective, from the Barnes perspective, how does Team Pole arrive at their crazy answer? Well, let's take a look. Now again, let me just set this up. From Gracie's perspective, right, the pole is coming in this direction, right? Now we know that if a reference frame is in motion, its clocks from her perspective are not synchronized. We know, in fact, that the clocks in the front of the motion are late. They are behind clocks that are to the right of the motion. So what that means is, when the pole comes in, I want you to look at the readings on the clocks. And what we're going to see is, Gracie will say that from George's perspective, the position of the back of the pole will be noted first because those clocks are ahead. The position of the front will be noted later after the pole has had time to move outside the barn. And that will explain, from Gracie's perspective, how it is that George claims that the pole does not fit. Let's see that. So there are the clocks, right? Notice that this one is behind. It's the leading clock, so it's behind. 7 o'clock, 7 o'clock. So from George's view, the front and the back of the pole at 7 o'clock were not inside the barn. But Gracie says, that's merely that your clocks were out of sync. She says the front and the back were in at the same moment of time. It's just that her notion of the same moment of time is different. So that's how she explains how it is that George comes to this strange conclusion. So here it is, a couple of stills of the key moments of that animation. From Gracie's perspective, the clock on the trailing edge of the pole reads 7 o'clock when it's just entered the barn. But by the time the front clock reads 7 o'clock, since it's lagging behind, the front of the pole has had time to exit. That is how she makes sense of his claims. Now, let's do the other direction. From the pole's perspective, how does George understand that Gracie and Team Barn arrive at their crazy answer? It's exactly the same collection of words, right? Now, from George's view, right? So George is coming in this direction, right? Now, but from his view, that means that the barn is coming at him from the left in the animation that we have here. That means that clocks on the barn, the clock on this side will be late relative to this clock over here, which means that from George's perspective, Gracie will not be measuring where the front and the back of his pole is at the same moment in time, and that is going to be how he resolves her claim that the pole fit. So what George will say is, because Gracie's clock over here is ahead of the clock over here, he's going to say, and we'll see it in a moment, that she is actually locating the back of the pole early relative to the front. So she's saying the back is in, but then according to George, the barn continues to move, and then after the barn moves, she works out where the front of the pole is, and there has been time for the front of the pole to enter the barn because of that asynchrony. Let's take a look at that one over here. So we'll now look at the clocks from George's perspective on the barn. Again, he's going to find that this clock is lagging compared to that clock over there. So he doesn't think he fits, but he notices that at 7 o'clock and at 7 o'clock, according to Gracie, because the barn clocks are out of sync, he actually fit, right? So let me just quickly show you that one again. So he's heading in, and he's looking at the barn clocks, trying to understand how Gracie says he fits, which means he knows that Gracie says at one moment both ends are in. 7 o'clock, that end is in. 7 o'clock, that end is in. But from George's view, that's merely because the barn clocks were out of sync with one another he claims that in reality he doesn't fit, but understands how it is that Gracie comes to this conclusion. That is the resolution of the pole in the barn paradox. Let me show you a couple of still images just to solidify the idea that from George's perspective, what he is saying is that Gracie's clocks, the barn clocks, are not in sync. So indeed, when the barn clock reads 7 there on the left-hand side, one end of his pole is in, and even earlier than 7 o'clock, the other end is in, so it easily made it into the barn. So from his view, he understands why it is that Gracie would say that the pole fits, but he attributes it to the asynchronous nature of Gracie's clocks. All right, let's take a look at a little demonstration where you can play with this. So this is just the pole in the barn experiment done in the traditional way that we have been doing things. This over here is our schematic representation of the barn. Here we've got the pole, and here you've got the barn's perspective and the pole's perspective, both here at the same time. So if you choose the relative speed between these guys at will, you should do this on your own, but let's say we choose it to be high speed, and then we play it at high speed. The barn says that the pole fits. Good. The pole, however, says that it doesn't fit. And again, the resolution simply has to do with the fact that they do not agree on what happens at a given moment in time. It's the relativity of simultaneity that allows us to understand both of these perspectives. We understand now the resolution of the pole in the barn paradox, at least qualitatively. Let's now take a look at the numbers, the mathematical details, which will allow us to reconcile these two apparently contradictory perspectives. So what we want to do is to first take a look, say, at the perspective of Team Barn. We know that they say that the pole fits, and what we want to work out is how does Team Pole come to a different conclusion from the perspective of Team Barn? Team Barn is like, I can't understand how they came to this different conclusion. They said the pole doesn't fit. Let's understand mathematically how it is that they resolve that headache, that conundrum. And they do finally understand this claim of Team Pole that it doesn't fit. So to set this up, let's start by considering the perspective of Team Barn. Let's try to figure out how they make sense of the strange conclusion that they hear from Team Pole. And to do that, let's record a little data to begin with. So according to Team Barn, the pole is rushing by at 12/13 the speed of light, pretty fast. And remember that the pole, its rest length, we are told is equal to 15 feet. Okay, good. Now, let's draw a little picture of this so we know what we are talking about. We have the pole. It's rushing along, and it's rushing along in this direction to my left as I face the board, and the speed of this guy is at v equals 12/13 c. Okay, now what does this mean from the perspective of clocks that are being carried by the pole from the barn's perspective, right? So let's imagine that the pole has clocks at the front and the back. And let me draw those for good measure. So let's say we have a clock here, and we have a clock over here. And we know that the clocks from the barn's perspective will not be in sync with one another, right? So if the pole is rushing this way, we know that the leading clocks will lag behind in time. They will be late, right? And let's calculate how far behind this clock is relative to the clock at the rear. And that we know how to calculate the time difference. So the difference between those two clocks, this little formula, we take v times the distance between those two clocks divided by c squared. So plugging in the data that we have at hand, velocity is equal to 12/13c. we've got the distance between those clocks. And again, this formula is the distance as viewed in the frame whose clocks we're discussing. So this will be 15 feet. And since we're using feet, of course, we'll take c to be 1 foot per nanosecond squared. So here we have our answer. 12 times 15 is 180 divided by 13 nanoseconds. And this is about 13.8 nanoseconds. So what that means is when Team Barn looks at these clocks, if, for instance, this clock over here on the right is reading 13.8 nanoseconds, then this clock over here on the left will be 13.8 nanoseconds behind. So it will be reading 0 when this one's reading 13.8 nanoseconds. Now, qualitatively, what does that mean? Qualitatively, that means that according to Team Barn, Team Pole is assessing the location of the rear of the pole before it assesses the location of the front of the pole. That means that the pole moves between when the rear position is assessed and when the front position is assessed. And that's why the front has time to get out of the barn, according to Team Barn. That is why, according to Team Barn, Team Pole comes to this weird conclusion that the pole doesn't fit. Now let's make that quantitative. We know that there's this 13.8 nanosecond difference in the reading of the clocks. That is not the time difference according to Team Barn regarding when the front and the rear are assessed, because of course this clock needs to catch up to that one, 13.8 nanoseconds, but it's ticking off time slowly because it's a clock in motion according to Team Barn. So if we calculate gamma in this case, which will allow us to convert that time difference into the time difference according to Team Barn, what is gamma in this case? Well, again, 1 over the square root of 1 minus 12 over 13 squared. And if you work that out, that gives us a nice answer of 13 over 5. So what Team Barn says is you take this 13.8 nanosecond difference in the clock readings and you multiply it by 13 over 5 to figure out how long after the assessment of the rear of the pole will the front of the pole's position be assessed by those in Team Pole. So let's do that. So if we take 13 over 5 times the difference in the clock readings, and let me just write that as 12 over 13c times 15 feet divided by 1 foot per nanosecond, just to get our full answer. So the 13s go away, the 5 goes into 15.3, so this gives us 36 nanoseconds. So according to Team Barn, 36 nanoseconds after the rear of the pole's position is assessed, the front of the pole's position will be assessed by those in Team Pole. How far does the pole move between those two assessments? Well, that's just velocity times time, right? So we have 36 nanoseconds. How fast is this pole traveling? Well, it's going 12/13 c, so that's 12/13 foot per nanosecond using our usual formulation. And therefore, if you just plug in the numbers and calculate this out, you will get 33.23 feet, approximately, is how far the pole is going to move between the assessment of its rear location and the assessment of its front location. So what does this mean? Well, let's draw a couple of pictures to see what this implies for the measurement of the position of the pole. So let's draw a little schematic representation of the barn, and for good measure, let's make some doors so that the pole can get inside of the barn. And now let's look at the motion of the pole from the barn's perspective. So according to the barn folks, Gracie and her friends, they say that the pole fits inside, period, end of story. But they also recognize that the clocks that are attached to the pole are not in sync relative to each other. And they say that the pole people first measure the location of the rear of the pole and only later measure the location of the front. And we've calculated that there's a 36 nanosecond time difference between when the rear and the front are measured, which means the pole moves during that interval. In fact, we've calculated how far it moves. The distance between these two locations, we calculated that as 33.23 feet. So that's how far the pole moves between when the rear of it is measured and when the front of it is measured. So of course the pole doesn't fit inside the barn. During that interval, it travels this distance, so the front of the pole gets outside of the barn. So in this way, Team Barn is able to clear their headache, right? They didn't need any Excedrin, they didn't need any Advil, they just did a little calculation. And in that calculation, they recognize that Team Pole first assesses the rear location and only later assesses the front, and by the time they assess the location of the front, it has slipped outside of the barn. That's how Team Barn explains this weird sounding conclusion, according to Team Pole, that the pole does not fit inside. So that gives us our nice explanation, according to Team Barn, of the weird conclusion of Team Pole. Good. Now what we want to do is the same kind of analysis, but from the perspective of Team Pole. We want to understand mathematically how it is that Team Pole can explain the observations, the conclusions, the claims of Team Barn that the pole does fit. And we can do really just the same calculation, but it's worth doing a second time. Same essential ideas, but now let's look at this from the perspective of Team Pole and try to understand how Team Pole explains this headache-inducing claim that Team Barn is saying, where the Team Barn says the pole fits. Team Pole says, how could they say that? And we want to understand how they clear that conundrum by analyzing clocks in the barn frame from their own perspective. And of course, the key idea will be that according to Team Pole, the clocks in the barn frame of reference are not in sync, even though the barn folks say that those clocks are in sync, right? So just so we can get a picture of what's going on here, if we draw a little schematic here of the barn, so the barn has clocks all along its length. Let's just draw the clock, say, at one end and the other. And according to Team Pole, it is the barn that is rushing along at a speed v in this direction, and that speed v is equal to 12/13 of the speed of light. And since the barn is rushing in that direction according to Team Pole, this is then a leading clock. It's in the direction of the motion. Leading clocks lag behind. They are late. So this clock will lag behind this clock. And we can calculate how much it will lag behind in order to understand the reasoning of Team Barn from Team Pole's perspective. So what is the time difference between those clocks? Well, we know what to do. We take the velocity, which is 12/13 c. We multiply it by the distance between the clocks from the perspective of Team Barn. That's the way this formula works. That is 10 feet. And we divide through by c squared, which is just 1 foot per nanosecond in the approximation that we are using. So this gives us 120 divided by 13 nanoseconds. And if you just work that out, that's approximately 9.2 nanosecond difference between these two clocks. And what that means is, according to Team Pole, if, say, this clock is reading 12 noon, then this guy over here will be lagging behind and will be 12 noon minus 9.2 nanoseconds. So qualitatively, what this means is, according to Team Pole, Team Barn is first going to assess the location of the front of the pole. Say they will claim it's inside at 12 noon. And then they will allow some time to elapse before this clock catches up to 12 noon. And in that interval, the barn will move to the right, allowing the rear of the pole to slip inside. And that's why, according to Team Pole, Team Barn says that the front and the rear of the pole are inside at the same moment, whereas from Team Pole's perspective, those are not the same moment because the clocks in the barn are not in sync. Now, we can make that quantitative, of course, by figuring out, according to Team Pole, how long will it take for this clock to catch up to 12 noon? It's not 9.2 nanoseconds because clocks in the barn frame of reference are ticking off time slowly, according to Team Pole. So we have to multiply that 9.2 nanoseconds by gamma to get the amount of time that will elapse, according to Team Pole, between when those two clocks, when I should say this clock catches up to 12 noon. So let's do that. What is gamma? Gamma is 1 over the square root of 1 minus 12 over 13 squared. 1 minus v over c squared. Work that out. That is 13 over 5. So now, if you allow me, I'm just going to take that 13 over 5 and multiply it by the time difference that we calculated above. So if you don't mind, I'm just going to do it right over here. 13 over 5 times 120 over 13. 13s cancel. 5 into 120, 24. So that gives us 24 nanoseconds. So again, according to Team Pole, the assessment of the front and the rear of the pole happened 24 nanoseconds apart. That is, this clock and this clock differ from one another, and it takes 24 nanoseconds for this clock to catch up to 12 noon. Now, in that interval, the barn is moving over to the right. How far does it move? Well, that's just velocity times time. So we have 12 over 13c, so let's do that, 13 feet per nanosecond, multiplied by that 24 nanosecond time difference. And if you just calculate that out, it comes to about approximately 22.2 feet. So according to Team Pole, the barn is moving 22.2 feet between the measurements of whether the front and rear of the pole are inside. Namely, more precisely, it is moving 22.2 feet between when this clock and this clock have the same reading. So we can see what that implies by drawing a diagram similar to the one that we had over here. But now this is from the perspective of Team Pole. Let's draw a version of the barn. And let me, as before, give some doors for this pole to come inside. And from the perspective of Team Pole, what we therefore have learned is the following. From their view, the pole does not fit inside. And again, that's the end of the story, according to Team Pole. But Team Pole also recognizes what we have now calculated, which is that the clocks in Team Barn are not in sync with one another. So according to Team Pole, what happens is the barn folks first assess the location of this end of the pole. They say it's inside, but then they wait 24 nanoseconds before they assess the location of that side of the pole. So let me just draw that. So imagine that we now look at this situation 24 nanoseconds later. So let me draw another schematic of the barn. Now, according to Team Pole, the barn has moved in those 24 nanoseconds, which means that even though, according to Team Pole, this end of the pole did not fit inside the barn at the same moment as that end of the pole, they recognize that according to Team Barn, they do fit, because according to Team Barn, what happens is they wait 24 nanoseconds later. According to Team Pole, the barn moves over. We've calculated how far that is. How far was that? That's 22 feet, so let me just record that for good measure.
So if I draw a little dotted line here, a little dotted line over here, this now is 22.2 feet. So clearly, this diagram is not to scale, but the idea is correct. So according to Team Paul, what happens is the barn moves over 22.2 feet between when Team Barn assesses this location and that location. And then, of course, according to Team Barn, the pole will fit inside. It's not measuring, according to Team Paul, the front and the rear at the same moment. Whereas, of course, according to Team Barn, this moment and this moment are the same moment. According to Team Paul, they are not the same moment. The relativity of simultaneity coming back with a vengeance. So that is the explanation, according to Team Paul, of how it is that Team Barn comes to this weird conclusion that the pole fits inside, whereas they know that it doesn't fit inside. Both of these pictures are absolutely correct. They're just two different perspectives that allow us to understand how it is that not only do these two frames of reference come to a different conclusion as to whether or not the pole fits inside, but we now also understand how each team understands the other team's claim, even though they don't agree with it. Again, coming from the relativity of simultaneity. So that's the mathematics behind this way of resolving the apparent paradox of the pole in the barn. What we want to do now is to get some feeling for these ideas by working with some demonstrations, which are good to play around with these things on your own. And that's what these demonstrations are for. So let's take a look quickly at one, but you should study this in more detail. This is very similar to the demonstration that we had earlier, except now you will note that it's adorned with a little bit of extra detail. So we now have doors on the barn, one moment in time from the perspective of the barn, but not one moment in time from the perspective of the pole. And you know that because there's going to be a flash. I should have said that when it was going. Watch for the flash. And again, do this on your own. The flash is at one moment in time from the pole's perspective. The pole says that and that. Those are same moment in time from the pole's perspective, very different moments in time from the barn's perspective. And similarly, you should work on the pole perspective too, where you'll see again the relativity of simultaneity, but now in mathematical form, fully explains this pole in the barn paradox. Spacetime diagrams provide another way of understanding the pole in the barn paradox. It gives a kind of visual way of thinking about it that some people find useful. So there are a couple of demonstrations where you're going to have the opportunity to play with the space-time diagram version of the pole in the barn paradox. Let me just quickly show you what they are. And then, of course, you should play with these on your own. That's what they are for, to get a feel for these ideas. So in this demonstration over here, you can pick one perspective or the other, pole or the barn. Let's pick the barn's perspective first. Now, from the barn's perspective, it is sitting still. It is not moving, which means that the two ends of the barn, which are represented by these two lines, simply go straight up. That's an observer whose velocity is equal to 0 with respect to the barn frame of reference. Front and back just move up. Now, from the barn's perspective, of course, the pole is moving. And these two lines here indicate the front and the back of the pole from the barn's perspective. And what you can do is you can choose the speed of the pole. And you'll note that if you choose very, very high speed, and then you allow this thing to evolve over time, you will find that if you chose it fast enough, that the pole will fit inside. So, boom, it just fit inside, just barely actually in that case. You should crank it up to higher speed to see the effect even more dramatically, and then you can play with time on your own. So to speed things up, notice that at this moment, right inside there, the pole, because the yellow line is inside the barn from the barn's perspective. And of course, you can do the pole's point of view too. And from the pole's point of view too, it comes to a very different conclusion, right? Because the barn, look how skinny the barn is in this space-time diagram. It's that blue line from the pole's view, and no way does it fit inside, right? So let that guy run. No way does the pole fit inside the barn, but it understands how the barn folks will claim it does if you carefully think about these 4 buttons over here, which just illustrate what we have calculated early, the relativity of simultaneity. One other demo that I want you to play with to get a feel for this is this demo over here, which is really the same demonstration that I showed you a second ago, with the one difference being I find it useful in these demonstrations to have the ability to show the slices, the now slices, if you will, space at one moment in time from each perspective. So it's the same thing as before that I was showing you, but now you can turn on, say from the barn's perspective, here are the equal moments in time. Here are the pole perspective. These are the equal moments in time from its point of view. And if you play with this, I won't try to do this in front of you because this is one of the things you need to think about in the privacy of your own brain. As you play this, you'll be able to directly see how it is from, say, the barn's perspective, the pole fit, but from the pole's perspective, it doesn't because that event did not happen on one of these equal time slices from the pole's point of view. So again, play with the demonstrations because it's the only way that you build up an intuition as best you can for these pretty strange ideas. We've explained the pole in the barn paradox. We understand how the relativity of simultaneity allows each perspective to understand the other's view regarding whether or not the pole fits. But it still may leave you with a question. When I first learned about this pole in the barn paradox, it still left me with a question, which is this. I mean, what if you have a barn that has doors, let's say steel doors, right? And as that pole is coming in, when you say that it's inside, bam, you shut those steel doors. Wouldn't that prove that your perspective is the right perspective, that the pole really does fit inside the barn? Well, yeah, it would establish your perspective that the pole fits. But now you've pretty much changed the problem, right? Because if you have these steel doors, then the pole is going to slam into it, which means it's going to no longer be moving at constant velocity. It's going to experience an acceleration, or in this case, actually a deceleration as it slams in. And then all sorts of issues come into play because if you try to accelerate an object, well, there's no such thing as a fully rigid object in the world, right? So if you push on anything at all, the push that you exert, the force you exert, has to travel through the object so the back knows that the front has been pushed, and that can cause a compression of the object. Or if you're pulling on it, that can cause the object to stretch. So you really have changed the problem, but nevertheless, it's an interesting problem to raise. Can we work out exactly what would happen in this situation? So we're going to give a model for the idea of causing the pole to stop when it's inside the barn. And we're going to give a mathematical model for that in a moment. But let me first give you the essential idea, which is really just what I was mentioning. From the perspective of the barn, boom, they shut the doors at the same moment. Good. What will the perspective of the pole be? Well, from the pole's perspective, of course, the clocks in the barn frame of reference are not in sync with one another. So the pole is coming in, which means the barn is going this way, which means the clocks in the back are ahead of the clocks in the front from the pole's perspective, which means they claim, boom, the back door closes first, the pole comes in, it compresses, then the front door is closed. That's why, from the pole's perspective, it now fits, where previously the pole said that it didn't. Now, I'd like to take that idea and make it a little bit more mathematical, and to do that, I need to commit to some very specific way of stopping the motion of the pole.
because to understand this compression effect, we really need to understand the details of how the pole is brought to rest. And here is the method. And the reason I'm going to use it is because it's particularly simple for the calculations. The method I'm going to use is not literally steel doors. We could do that. It's a little bit more complicated. Instead, let's imagine that Gracie and all her friends in the barn frame of reference are standing there, waiting for the pole to come in. And they agree that when the pole is inside, at an appointed moment, they will simultaneously grab hold of it, instantaneously from their perspective, bringing the pole to rest. That gets rid of some of the issues of rigid bodies if we're going to grab it from the barn's perspective all at the same moment. That's how we are going to describe the pole being brought to rest. What will the pole perspective be, right? So I'm now going to be the pole. From my perspective, here I'm standing. The barn is coming toward me, which means that the clocks far away are further ahead in time, which means as the pole comes in, I'm going to claim, if I stand this way, that first someone in the barn grabs this point, then 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 this point, a wave of grabbing of the pole, not at the same moment in time, because I have a different conception of simultaneity if I'm moving with the pole. And what I'd like to do is do a little calculation right now of what would happen to the pole in that circumstance. If it's grabbed here, then grabbed here, then grabbed here, then grabbed here. Now, the issue of compression comes into play. If the pole is grabbed here, this part continues to move. Then it's grabbed, but this part continues to move, and then it's grabbed. And because of that, there will be a squeezing down of the pole. And that's why it will now fit. Let's do the calculation to see how that actually goes. All right, so let's look at our pole. So here is a picture of the pole. And from the pole's perspective, what happens is different parts on the pole get grabbed at different moments. So let's indicate that. So from the pole's view, the barn is moving that way, which means that this guy over here is grabbed first, according to the pole. This guy over here is grabbed second, third, and fourth, and say this guy over here is grabbed last. And I want to focus in on one little chunk of the pole. Let's just look at one piece right in there, and let's call that length, say, delta L naught. That's the length of that little chunk. And I'm now going to apply this idea that the left side is grabbed first relative to the right side to calculate how much it squeezes down. How do I do that? Well, let's calculate the time difference. Well, the time difference between the grabs. Well, we know what that time difference is. From the perspective of the pole, the barn is moving this way, which means the clocks on this side are earlier by an amount that is given by the velocity of the barn from the pole's perspective times the distance between the two clocks. And the distance between those two clocks, say, is equal to delta x. And you take that and divide through that amount by c squared, where this is the distance between the observers that are grabbing the pole in the barn frame. Okay. Now, given that, we can then work out that that amount, delta L naught, will get squeezed. It'll get squeezed by the amount that this part of the pole moves before it gets grabbed. This guy gets grabbed, then this guy gets grabbed. The time difference times the speed is how much it'll squeeze down. So you start with that length, you subtract off the velocity times the time, which is v times delta x divided by c squared. Okay, so what is the value of delta x? So delta x is just this guy delta L naught. So this then is equal to delta L naught times 1 minus v squared over c squared. And we recognize that as delta L naught
times 1 over gamma squared. Now that happens to each and every chunk of the pole. Each and every chunk of the pole gets squeezed down by the amount that the right-hand side moves after the left-hand side has been grabbed, right? So if you take account of that over the full pole, that means L naught itself, the length of the pole from the perspective of those who are moving with it, will go down to L naught divided by the same factor, gamma squared. So according to the folks in the pole frame of reference, this procedure of grabbing the pole, because from their view it does not happen simultaneously, results in the pole being squeezed down. And it's squeezed down by a sufficiently large factor that now the pole people completely understand why the pole fits. It's not a mystery any longer, not a matter of different perspectives. It has been squeezed down. Now, I want to ask you, though, does this answer make sense relative to everything else we know? And the answer is it does. Why do we get the answer L naught over gamma squared? Well, think about it. From the perspective of those in the barn, so the barn people, they say that the pole's length is L naught divided by gamma, because from their view it is length contracted. When they grab hold of it instantaneously, therefore, this is the length of the pole that they expect, and this is the length of the pole that they would get. So why do we have an extra factor of gamma over there? Well, let's think about it. This, of course, is the perspective from the pole frame of reference. And after the pole is brought to rest in the barn, right, the pole frame of reference, the guys who were initially moving with the pole, they aren't stopped. The reference frame isn't stopped. The reference frame continues to move. So now, after the pole has been brought to rest, the pole people say that the pole has velocity v. And if the pole has velocity v, then it gets length contracted from the perspective of the pole observers. So it has length L naught over gamma in the barn frame, but the pole frame is moving relative to this, so it gets length contracted by an additional factor of gamma, and therefore, indeed, the result L naught over gamma squared is exactly what we'd expect to find. So the way to think about this is the one factor of gamma you can think about coming just from ordinary Lorentz contraction. This additional factor of gamma comes from the compression of the pole, at least from this frame of reference. So there you have it. We can model how we bring the pole to rest. Indeed, it will fit inside the barn. From the perspective of the pole observers, though, there's a reason for that. The pole has been crushed. It has been shrunken down by a compression factor because it was not grabbed simultaneously. The parts on this side continued to move after this side was brought to rest. So that's how you can understand the pole in the barn paradox if you go this next step and consider stopping the pole inside of the barn. It all makes perfect sense, with L naught over gamma squared being the resultant length of the pole after it is brought to rest in the barn's frame of reference. So Lorentz contraction and compression explain what happens in this version of the scenario. The twin paradox is the most famous of all paradoxes in the special theory of relativity. But before we get into it, let me just stress the most important point. There are no paradoxes, as I said earlier, in special relativity. If there were, the theory would collapse. There are, however, situations where it seems like there's a paradox. It seems like we have two perspectives that we can't somehow meld together into a coherent story. But that generally means we have to think the situation through with detail. Think it through with our understanding of the essential physics. And when we do that, all paradoxes fall to the side. The same will happen here. Okay, let's set it up.
The paradox, or the seeming paradox, will involve a couple of characters. They are twins, George and Gracie. And the scenario is one that may have occurred to you in our earlier discussion of time dilation and space travel, because we are going to imagine, in this case, that Gracie goes into a spaceship. She travels out into space. We're going to have her go pretty fast. She's going to turn around and come back. Here is the issue. From George's perspective, stay at home, George, on Earth. Looking at Gracie, from his perspective, he knows how time works in special relativity. He says that her clock must be running slow, so that when she comes back, he will say that he will be older. Not as much time will have elapsed on her slow-moving clock compared to him. Gracie, however, she looks back at George, and she says to herself, look, I understand special relativity too, and it's George, from my perspective, that's moving. I'm stationary, and therefore it's his clock that's ticking off time slowly. So when I return, it should be the case that I, Gracie, am older, because less time will have elapsed on George's clock. That is the issue. Let's see that in visual form. So here is the question. There is George, first character, and let's bring in his twin. These are fraternal twins. Gracie, she gets into her spaceship, and we're going to send her off into space. So let's do that. And let's say she's going fast, so there really will be some kind of significant time dilation going on here. She goes off into space. She's going to reach some point that we will call P, the turnaround point, and she will then come back. Okay, so then the question that we are faced is, when these two guys compare the amount of time that has elapsed according to each, will it be the case that George is older than Gracie? Will his clock have ticked off more time? Will it be the case, on the other hand, that it is Gracie that is older? Will it be that more time has ticked off on her clock? Or you could even imagine a resolution that puts these two together. Maybe it's the case that each of them will have aged, each will be the same age as the other when they return. That is the question. We want to figure out which of those three scenarios is correct to resolve this seeming paradox that each says that the other's clock must be ticking slowly. Each therefore says that they should be older. Okay, so I'm going to offer you some resolution to this paradox. The deep question is, who is right? Which of these scenarios is correct? Now, you might guess that they are both right, because that has been oftentimes what we have encountered so far in special relativity. Each perspective is right, and you just have to reconcile them with your understanding of how special relativity works. So that's a natural guess, but that guess will not fly in this case. That will not work, because at the end of the journey, right, George and Gracie are together, right? So they can face one another. They can be standing right next to each other. In fact, they can even go into the same frame of reference. And there can no longer be any mismatch in their observations at that point. One cannot look at the other and say that you are older, and the other looks at the other person and says you are older. That's a contradiction. That's a paradox. That can't happen. So we cannot rely upon the kind of resolution that we have found earlier. Somebody here is right, somebody here is wrong. How do we figure out which? Well, I am going to give you the answer. It is Gracie who turns out to be younger. George turns out to be older. And I'm going to give you three explanations for that. Let me start with explanation number one, which is a simple explanation that really cuts to the heart of the matter. Where does the contradiction come from? Where does the apparent paradox come from? It comes from George saying that he can be viewed as at rest, Gracie moving, Therefore, her clock ticks off time slowly. And, of course, Gracie can say, I am stationary, and it's George who's moving, and therefore I can claim that it's his clock that is ticking off time more slowly. Is that valid in this situation? Well, remember, the only time that you can claim to be at rest and the rest of the world is moving by you is if you are going at constant velocity, constant speed in a fixed direction. That is manifestly not true in this case for Gracie. Gracie, going out into space and then coming back. She has to turn around. And when she turns around, she has to accelerate. She slows down, and then she speeds back up to get back to George on Earth. She feels that acceleration. She knows that she is moving. She is no longer moving at constant velocity. She is no longer justified in saying that she is at rest and the rest of the world is moving by her. So her perspective, her reasoning is negated by the fact that she is accelerating. She is not in an inertial frame of reference throughout the whole version of this journey, and therefore we cannot trust her conclusion. George, on the other hand, is in an inertial frame. He is at rest on Earth's surface. He does not move, subject to the issues of whether Earth's surface is an inertial frame, but those are the complexities that we are not worrying about for the discussion we are having. George's perspective, therefore, is valid. He is constant velocity throughout this entire journey. His conclusions are unassailable. They are absolutely correct. And he says that Gracie's clock is ticking off time more slowly, and therefore, when she returns, he will be older. Period. End of story. That is the resolution, or I should say, a resolution of the twin paradox. We will come to other explanations as we proceed further with this deep scenario that lets us really sink our fingers into a lot of the details that we have been developing. But as a first pass to this scenario, that is the explanation. Gracie is accelerating for part of the journey. Her perspective, therefore, cannot be taken into account. She cannot say she is at rest. George is the only one who can say that, and his conclusion that he will be older is correct. In the first and most straightforward explanation of the twin paradox, we make use of the idea that Gracie, the twin who goes out into space in the rocket ship, has to turn around and come back, has to accelerate, and therefore we cannot trust her perspective. And therefore, we only, in this scenario, can trust the perspective of George, who stayed at home, who claims that he will be older. Good. Okay, we understand that. But if you think about it, there is a simple way of modifying the scenario that doesn't need accelerations at all, right? You can imagine a situation now where we have 3 observers, right? So let's imagine that those observers are George, who stays home on Earth, as in the first version. Gracie, who, as in the first version, is always, say, moving to the right, except now we're not going to have her accelerate to come home. Instead, we're going to imagine that she has a friend called Germain, who is going to pass her, take the reading on her clock, set Germain's clock to be equal to Gracie's, and she's going to head back to Earth and compare her clock to George's. So in this way, there's no acceleration to come back because there's a kind of handoff between Gracie and Germain. So pictorially, this would look something like this. So as before, George and Gracie. Gracie is in the rocket ship. She heads out into space. But there's her friend that she's worked this arrangement out with Germain. As they pass, Germain sets her clock equal to Gracie's. And then she passes by George and can compare the amount of time that has elapsed on her clock to the amount of time that has elapsed on George's clock. So now we seem to be in a situation where there isn't any acceleration at all. Nobody accelerated in this version of the story. So now how do we explain that there is a time difference between George's clock and Germain's? After all, Germain's clock is the same, if you will, as Gracie's clock, because Germain took on Gracie's time when they passed by one another. So we seem to be in a situation that's a little bit more difficult than the initial version of the twin paradox, because now there's no acceleration that we can rely on to say that one perspective is wrong and the other perspective is correct. So how do we get out of the twin paradox in this case? Let's take a look at how we can resolve this version of the story. And to do that, I'm going to set up a little table over here with 3 key moments in this version of the story. So Gracie heads out into space. One key moment is when she passes Germain and they set their clocks equal to each other. Germain then starts on the journey back home. And a final key moment is when Germain passes George, because we want them to compare the amount of elapsed time on their watches, on their clocks. And what I want to do is fill in each of these boxes with the amount of time. These are basically clocks. I want to fill in with the amount of time that each will claim those clocks read. Okay, so these are pretty straightforward calculations based on everything that we have developed so far. Let's put some numbers into the story. So we are going to assume that the speeds involved are pretty high. So both Gracie and Germain will travel with v equals 12/13 of the speed of light. Let's call this location over here P. So the distance between Earth and the point P, we're going to take that to be 12 light years. Okay. So now George says, look, Gracie's traveling out at 12/13 the speed of light. For her to cover 12 light years, he knows that that means it's going to take her 13 years to get there. So from his perspective, when she reaches the point P, his clock will read 13. Good. Okay. Now, at that moment, Germain takes over the story. She also has to travel 12 light years back. And George says, well, it's going to take her the same 13 years to go back. So he says that when she returns, let's put this here, 13 is the same time when she starts her journey back. It takes her 13 more years to get back, so 13 plus 13. He says that his clock will read 26 years when Germain passes him. Good. Okay. So that part of the story we understand well. Now, let's look at George's view of Gracie's and Germain's clock. What does he say there? Well, he goes ahead and, knowing about time dilation, George calculates gamma, 1 over the square root of 1 minus 12 squared over 13 squared. And if you just plug in those numbers, you'll find gamma equals 13 divided by 5. Okay, with gamma equal 13 divided by 5, you'll notice that I have gamma equals 5/13 there. That's wrong. It should be the inverse of that. Everybody makes mistakes. That should be gamma inverse. So gamma inverse is 5/13. Gamma itself is 13 over 5. But what this means is, according to George, the clocks that Gracie is using and Germain is using, they are ticking off time slowly from his perspective. So if it took 13 years from his perspective for Gracie to reach the point P, he claims that it will only take on her clock 5 years. Her clock is ticking slow, so he puts in here the number 5. Now, according to the scenario, when Germain and Gracie pass one another, we know that she is going to set her clock equal to the time on Gracie's, so that will be 5, which means that as she begins her journey back home toward George, her clock starts at 5. And then George says, look, of course, it's going to take her the same amount of time to get back as it took Gracie to get there. Her clock is ticking slow, just as Gracie's. They're traveling at the same speed, just in opposite directions. So he claims that when she gets back here, it'll be 5 plus 5 more, 10. Okay, So that is George's view. He claims that he will be 26 years older when Germain goes by, while he'll claim that only 10 years will have gone by on the combined clock of Gracie and Germain. Okay, so that is the perspective, and I should just mark this so it's clear. This, of course, is George's view. This one we understand quite well. Now what we want to do is compare this to the view of Gracie and Germain. So to do that, let's set up another little table so we can record what they claim are the elapsed time on these various clocks. So the same table as before, but let me mark this so we know that this is the perspective of Gracie and Germain. What do they say? All right, well, let's just play the same game. First off, from Gracie's perspective, how far is this journey from Earth to this point P? Well, of course, she will claim that there is Lorentz contraction involved. So even though George said it was 12 light years, she will say that 12 light years actually is shorter. It should be 5/13 times 12 light years. So that is the distance that has to be traversed. So let's record that. So the distance is 5/13 times 12 light years. How long will it take? Well, again, the speeds involved are 12/13 the speed of light. So if we do distance divided by velocity, so it's 60/13 for distance, 12/13c for speed, and that yields a total of 5 years. So Gracie will claim, and this agrees with George, that 5 years will have gone by on her clock when she reaches the point P. Okay, again, the scenario tells us that Germain will pick up 5 years there too because she is setting her clock equal to Gracie's. All of that makes good sense. Now, what does Gracie say about George's clock? Okay, Gracie says, look, on my journey, I'm experiencing no acceleration whatsoever. I am perfectly justified in claiming to be at rest, and George is moving. No acceleration's now getting in the way, and therefore I can conclude that George's clock is running slow. And because it's running slow, if 5 years have gone by on my clock, only 5/13 of 5 years will have gone by on his clock. So she claims at this location, when she passes Germain, that 25/13 years will have gone by. That's about 1.92 years, less than 2 years. So she says 5 years for her, less than 2 years for him. Okay, now let's move on to Germain's perspective. Germain is looking at a journey that starts over here where her clock reads 5. Again, she says that the distance is length contracted. So rather than being 12 light years, as George says, she claims that it's 5/13 of that, which means that she's traveling 60/13 light years, just as Gracie did. And of course, it will take her the same length of time to get back. So she claims that her own clock will read 5 + 5 = 10. So far, so good. Now, let's look at Germain's perspective on George's clock. That's where the issue will arise. Again, Germain will say that she is executing constant velocity motion the whole way through, no accelerations in this particular case, and therefore she claims that George's clock is running slow. And because of that, again, she says that only 25/13 years will have gone by on the return journey, just as it took 25/13 for the outbound journey. So the total here, she says, is 25/13 times 2, 50/13. And now we see the paradox, or the seeming paradox, in full force. Everybody agrees that Germain's clock will be 10. We see it in this table. We see it also in this table. But in this table, which is George's view, 26, in this table over here, 50/13, a number that's less than 4 years. So that's the issue that we now need to think through to resolve? How do we make sense of these contradictory claims? Here is the answer. We've made a mistake, right? What is the mistake that we have made? Well, we have assumed that from Gracie and Germain's perspective that all of the clocks in George's frame are in sync with one another. But they're not. Relativity of simultaneity, asynchronous clocks in a frame that is moving relative to you, we haven't taken that into account. Let's do that now. Okay, so the point is, Gracie and Germain see Team George's clocks as out of sync. And in particular, let's now look at the clock in George's frame at location P. What will Gracie say that that clock reads at this moment? Will that read 25/13? Absolutely not, because this clock, from Gracie's perspective, George's frame is rushing by. She claims to be at rest, so George's frame is rushing by, which means clocks over here are ahead of clocks over here. How much are they ahead? We've now used this formula many times. You simply take the speed of the frame times the distance divided by c squared, and if you plug in those numbers, it means that the clock at P is ahead of George's by 12 squared over 13, 144/13. So the time here, according to Gracie, if she's now careful, would be 25/13 plus 144/13. Good. Now, Germain comes into the story. Germain is in a different frame of reference from Gracie, right? From Germain's perspective, George's frame is moving that way, right? And if the frame is moving that way, it means George's clock is ahead of the clock at P. So you have to take that into account in order to properly get Germain's perspective. How much is the clock here ahead of the clock over there? Well, again, by an amount, 12/13 times 12, again, VD over c squared. And putting all that together, then the clock over here would have a reading of 25/13 plus 144/13 plus 144/13. I've simply taken the time over here and I've added to it 144/13, the time by which it is ahead of the clock at P. Good. Okay, so what do we do with that? Well, now Germain says, I still am going to allow that clock to evolve in time as I am executing my return journey, and that adds to it the amount 25/13. That's how much George's clock will evolve forward in time from this amount. So now let's put that together. So here we have the 25/13, the 25/13, which gives us the 50 that we had before. But now we have to add this offset, and that offset is 144/13 plus 144/13. So if you add all that up, what do you have? Well, the simplest way to do this, this is 5 squared over 13, 12 squared over 13. 5 squared plus 12 squared is 13 squared. 13 squared over 13 is 13. You do that twice. I encourage you to check. The answer that you get is 26. So it all works out. If you correctly take into account the asynchronous nature of the clocks in George's frame from the perspective of Gracie and Germain, you come to this wonderful fact that whereas initially, when we didn't take that into account, we had what looked like a paradox on our hands, right? We had that George's clock was supposedly reading 26 from his perspective, but only 50/13 from Gracie and Germain's perspective. But when we correct it using the asynchronous nature of clocks in motion, we get 26 years on George's clock. So the two sides of the story, right? Gracie and Germain's perspective, this table. George's perspective, over here, this table. They are now in complete agreement. That resolves the paradox. No need to talk about accelerations in this case, but you do need to take into account that at this moment, we change from one frame to another, and that results in a time difference for what this observer claims George's clock reads when that handoff takes place. Take that into account, and it all works. No paradox at all. We now understand how we can resolve the twin paradox without relying on accelerations to save the day. In this version over here, we don't have any accelerations at all. It's simply that when you change from Gracie's frame of reference to Germain's, that results in a jump in the time on George's clock from the perspective of Germain, who's undertaking this return journey. It's nice to see a graphical version of that story, and that's what space-time diagrams give us. So let's see the space-time diagram version of this resolution of the twin paradox. So let's take a look at a space-time diagram that will embody all of the interesting physical features that we have been talking about. So as always, this will be our x-axis, this will be our t-axis. And we are going to imagine that we look, say, at the trajectory of Gracie as she is beginning on her journey. So let's give her a nice red color, and she's traveling near the speed of light, but certainly not equal to it. So let's say, I don't know, she goes out to here. That is Gracie's outward trajectory. And now why don't we put Germain's trajectory coming back into the story too. So let's put in here Germain's return voyage as well. Okay, so what are we going to put in this diagram? Well, let's put in the equal time slices from Gracie's perspective and from Germain's perspective. So we'll use orange here, and let's plot all those positions in space that are at the same moment of time from Gracie's perspective. So let me just mark that. So this is an equal time slice, a now slice, if you will, for Gracie. And you'll note that over here, we have, from her perspective, that the amount of time that has gone by on George's clock is quite small. In fact, might as well just fill in the numbers. So 25 over 13 years have gone by to this location on George's clock. But now Germain takes over, and let's put an equal time surface for Germain. And let's choose, say, yellow for that. So that equal time surface for Germain will make a similar angle, but it's just going in the other direction. It looks something like that. Good. Okay. And again, from the perspective of Germain, 25 over 13 more years will go by on George's clock between those two locations. And the resolution to the paradox, why it doesn't come out to a total of 50 over 13, is because of this time jump in here. And that time jump is equal to this amount of time in between these two locations is the jump that we have calculated. And that jump, of course, is equal to 2 times 144 divided by 13. So in a space-time diagram perspective, this is what happens. This is the time jump that occurs when you switch from Gracie's perspective, where these are the equal time surfaces, to Germain's perspective, where she has different equal time surfaces. So again, it is just the fact that clocks in motion are not in sync from your perspective if you are moving relative to them. And it's this jump in here as we go from the Gracie perspective to the Germain perspective that ensures that when Germain returns, George will be 25 over 13 plus 2 times 144 over 13 plus 25 over 13. If you add all that up, you will get 26 years. So that's the space-time diagram version of this resolution. And it gives us a kind of nice geometrical picture of what's going on in this situation, allowing us to not have to rely solely on the arithmetic and the numbers, but we can actually see that there is a jump in time when we change off from one frame to another. And this explanation is one that I want you to get a little bit of experience with. So we have a little demonstration that you should play with on your own. And it is just a version of the calculation that I just did. So here you have it. You can choose the velocity of the person who's going out into space. And of course, it's the same velocity of the person who's returning. You can dictate how much time total will elapse on Earth. So here I'm choosing 15 years. And you can take the Earth perspective, George's, which is simple. One ship goes out, the other comes back, not much to it. But if you take the spaceship perspective, then you can show the outbound journey, where only a little bit of time, according to the person going out, has elapsed on George's clock. Then there's a change of reference frame, which makes a jump from their perspective in George's clock. And then finally, the inbound journey has, again, just a little bit of time elapsing. This is the 25/13th. Put it all together, and you get exactly the numbers that we have calculated, but you should play with that to, again, get a feel for this space-time diagram version of the resolution of the twin paradox, but also more generally, this resolution which does not involve any accelerations at all. Even in that case, we have a perfectly good understanding of why it is that George is the one who ages more in this situation. In most of the scenarios that we consider in special relativity, we're really not that concerned with what someone would actually observe, right? We're more interested in what they would measure, what they post-process figure out was responsible for what it is that they are now seeing, because we're really interested in how reality is constructed, not reality that then has to be filtered through all the issues with perception, light, travel time, and things of that sort. In this version of the twin paradox, we're going to change that perspective a little bit. We're going to ask ourselves, what would each of the twins in the twin paradox actually see if they were able to communicate with one another during the journey? So in this version, we're going to have Gracie go out into space. She's going to turn around. She's going to accelerate and come back. But we want to understand what would happen if each of them has a powerful telescope, is looking back at the other throughout the entire journey, and when they return, we know the answer. We know that George is going to be older, but how will they see that asymmetry? Where will they see that asymmetry and aging take place if they're looking at each other the entire time? So what will they see in this situation? And to make this nice and systematic, we're going to imagine the following. George is going to send out a bright flash once each year toward Gracie. Gracie is going to send out a bright flash once each year toward George. So all we really need to do is count the bright flashes that each of them see to determine how much time they will say has gone by for the other. Okay, so let's see what that would look like. So here we have George and Gracie. Gracie is going off out into space. And each year, George is going to send out a flash. 1 year goes by for him. 2 years go by for him, and so on. And Grace is going to do exactly the same thing. So each year that goes by on her ship clock, she's sure to send out a beacon toward George, which alerts him that 1 more year has gone by on her clock. And what we want to do is we want to keep track of those flashes between George and Gracie. So we're going to set up some counters that allow us to do that. So here we see this will count how many times George has sent out a flash. And then over here, each time Gracie receives a flash in her telescope, it will go up by 1 notch. And we're going to do, of course, exactly the same thing for George. every time he receives one of the signals that Gracie sends out, that'll tick up by 1. Every time Gracie sends one out, this guy will notch up by 1. So that's the way we are going to keep track of the flashes that each sends and receives. We are going to look ultimately at a comparison in which we are going to count the number of flashes that each has sent and that each has received. And that number, again, will be the number of years that George has aged, and the number that Gracie sends out would be the number of years that she has aged. The number that George receives is his understanding of how much she has aged. And again, Gracie, the number that she receives, gives her an understanding of how much George has aged. So now what we want to do, having set up this way that the twins will communicate, let's look at the experience that each of them has. All right, we'll begin with George. What's his experience? Well, during the outbound part of the journey, while Gracie is rushing away, notice that he will say Gracie's clock runs slow, and he'll also say that because Gracie is moving away, each flash has to travel much further to reach him, so he's going to receive those flashes slower than if she was standing still. So he's going to receive those flashes at a slower rate compared to what happens when he is looking at the inbound flashes, right? The inbound flashes, when she's coming back, each of those flashes has to travel less far compared to the previous because she's getting closer year by year. Those flashes, according to him, will be coming in, therefore, more quickly. So let's take a quick look at that. So from his perspective, let's look at his counter. As Gracie is going away, he's getting the flashes at a certain rate, but relatively slowly, because each flash, looks how much farther it has to travel compared to the one previously. But then when she turns around, let's now focus on the inbound flashes. The inbound flashes, well, when he finally receives the first one, and the second one will come in very quickly. And watch, so boom, 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 they come in very fast at the end because each one is traveling much shorter distance than the previous one. But what I want to stress in this picture is that the flashes that are coming in more quickly don't immediately arrive after Gracie turns back because it takes some time for that inbound flash to reach him. But when the inbound flashes start to come in, they come in rapid fire. So the point that we should stress here is that the effect of Gracie's turnaround does not kick in immediately on his experience. It takes a while for the effect of her turnaround to have an impact on him because she turns around, she fires, but it takes a certain amount of time for that flash to travel the intervening space and reach him. Good. That is George's experience. Let's take a look at Gracie's experience. She similarly will find that during the outbound part of her journey, the flashes from George are coming in relatively slowly. Why is that? George's clock is running slow, and also, since from her view he's moving away, each flash has to travel much farther than the previous to reach her. Good, we understand that. What about the inbound part of her journey after she turns around? Then she's going to say that the flashes from George are coming in more quickly because, again, she's getting closer, so the flashes don't have to travel as far to reach her. So they will be coming in faster on her return journey than on her outbound journey. So let's take a look at that from her point of view. And let's see. So she will go out into space. George is sending these flashes. Since she is rushing away, each flash has to travel farther to reach her, so they're coming in relatively slowly. In fact, she hasn't even gotten one yet. But then when she turns around and begins the inbound part of her journey, look what happens. Flash, flash, flash. They are coming in rapid fire here. She is going towards them. They don't have to travel as far to reach her. And therefore, they are coming in bang, 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 bang throughout the entire half of her return voyage. Now, the thing that you need to recognize is, unlike George, the turnaround has an immediate impact on Gracie. From George's view, she turned around and it took a long time before the inbound flashes reached him. Her act of turning around only affects George when enough time has elapsed for the signal that she sends here to reach him. And then all subsequent ones come in rapid fire. But Gracie's experience is very different. Immediately when she turns around, she receives the flashes that George sent rapid fire for the entire return voyage. See, the bottom line is, because it's Gracie's act that is the operative act in this situation, her action affects her immediately. Her action only affects George after a delay. And that is the key asymmetry. That is why in this situation, it is Gracie, we'll work out these numbers in a little while, it is Gracie that will receive many, many flashes, indicating that George has aged a lot, whereas George will not receive many, many flashes because the rapid fire part of his experience only happens for a small window of time at the end. So Gracie's actions affect her immediately. They only affect George after a delay. So if I put both of those together in this animation here, let's see both of those experiences at once. Okay, so there she goes off into space. George and she are both sending out their flashes when 1 year has gone by on their respective clocks. But now focus in on what happens as Gracie makes the turnaround. You will see that her receive counter starts to go up very quickly. She receives many flashes rapidly because they don't have to travel as far to reach her. But George has not received many flashes. His rapid fire experience is about to happen only when the inbound flash first reaches him, boom, 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 boom. Then all of them kick in, giving him a total number in this particular example that we will calculate of 10. But you see where the asymmetry comes in. Gracie turns around, and at that point, all the way for the rest of her journey, she is receiving many, many flashes. George only receives many flashes rapid fire for a tiny window toward the end of the journey after the first inbound flash that Gracie has fired has had a chance to reach him. That is the explanation from the perspective of what they would observe regarding how it is that one recognizes that more time will have elapsed for the other. Now look, talking in terms of light flashes may not be particularly evocative, particularly gripping way of describing what each of these observers will see. So let me show you what they would literally see if they had a powerful telescope that was not just sensitive to light flashes, but could literally see the other person. Okay, because, and let me set it up for you, when I say that light flashes are coming in rapid fire, I literally mean that if you're looking at the person, you are seeing year after year after year after year go by very, very quickly. That is Gracie's experience here. George's experience of rapid fire is just at the very end. So the bottom line that we'll see in a moment is each sees the other in slow motion when the flashes are coming in slow for part of the journey. Each sees the other in fast motion for part of the journey. The asymmetry is Gracie sees fast motion in George for more of the journey than George does. So let's make that clear over here. So in this picture, we're now looking at what George and Gracie would see. So they both see the other in slow motion for part of the journey because the flashes are coming in slow because they are each receding from the other. But look what happens at the turnaround. At the turnaround, when Gracie's looking at George, now it's fast motion. And look, he's aging, right? She's watching him. The beard is growing. He's getting older and older. But from George's point of view, Gracie's still in slow motion until here. And then, boom, fast motion, but only for a little part of the journey. That's where the asymmetry comes from. Each of them sees the other move slow for part. Each sees the other age quickly for part. But it is George who only sees fast motion for a little bit of the journey. Gracie, because she is the one who turns around, sees fast motion for half of the journey, And that is why George is older at the end. Now, to make this quantitative, to understand the numbers 10 and 26 in this example, we have to introduce another idea which is important in its own right, called the relativistic Doppler effect, and that is what we will take up in the next section. The relativistic Doppler effect is important in its own right, but we are ultimately going to apply it to understand the twin paradox. But let's start general and note that the Doppler effect refers to a situation in which you have a source sending out a signal toward an observer and there is relative motion between them, right? This is something that you have experienced, no doubt, with sound waves, right? The ambulance is coming rushing by, and the siren, right, you hear it, it goes, right? You've heard that? That's because the sound waves are piling up as the vehicle is coming toward you, making the frequency higher. As it rushes away, the sound waves are stretched further and further apart, so the sound goes down. That basic idea that you have experienced is something that applies to light as well. And since light is something that travels fast at the speed of light, you need to take relativistic effects into account to mathematically understand what is happening. So let's take a look at that and do a calculation. So what we're going to try to figure out is if you have light that, say, has a frequency nu, and if you have an observer that is moving relative to that light with a velocity v, our goal is to understand the frequency that the observer will see relative to the frequency at which the light was emitted. And let me give you the answer before we derive it. That is the formula that we are going to find. The frequency observed can be gotten from the frequency at which the light was emitted by multiplying by this factor. Square root of 1 minus v over c divided by square root of 1 plus v over c. Just a little calculation to establish that, so let's take a look. Alrighty, so let's imagine that we have a source over here, and that source is sending out some light waves. So let's draw a few of those. So the light waves are all emanating from the source, something like that. And imagine that you are receiving that light. So let's say imagine you are right over here. But let's also imagine, let's do the case where, say, you are running away. So you are moving away at a velocity equal to v. And we want to figure out the frequency with which you receive those light waves. Now, a couple little details worth emphasizing on the side. Remember quite generally from your understanding of waves that the wavelength of light times its frequency, that is the speed of light. So this is equal to c. And therefore, it'll be useful for us to write this in the form nu is equal to c divided by lambda. And lambda, of course, if we want to draw it in the picture, is the distance between these wave crests. So let's imagine that one of these wave crests has just hit you. You're moving away. You want to know how long it will take for the next crest to hit you. How long will it take this one to reach you? That's not hard to do, because if you call that time delta t, it had better be the case that the speed of light times delta t is equal to the distance it needs to travel. Now, at first sight, you might think that distance is lambda, but now that we've done this kind of calculation many times, you recognize that you were moving, so actually you've moved over here. So the distance between your initial and your next location there is going to be v delta t. So the light has to cover that distance as well for this next crest to hit you. And therefore, we can solve for delta t. Delta t, bring that over to the other side, is just lambda over c minus v. Now, we're not quite done, because this delta t over here is the time that we, watching this unfold, would say took place. The time, according to the observer, him or herself, is delta t prime. That watch, of course, is ticking off time slowly. So we need to take delta t for us and multiply by a number less than 1. Of course, it's either going to be gamma or 1 over gamma. Don't get confused about them. Don't even try to figure it out from a formal mathematical sense. You need a number less than 1, since this time is less than this time, and that therefore means it must be 1 minus v squared over c squared. So now we can plug in for delta t, and we will have what we are looking for. So writing this, say, as lambda over c times 1 minus v over c, that's the same as that expression, that's delta t, times the square root of 1 minus v squared over c squared. I'm going to play a game here. This can be written as 1 plus v over c times 1 minus v over c. So let's write that. 1 minus v over c times 1 plus v over c. And then I can bring this guy inside by squaring it. One factor will cancel against that, leaving us with 1 plus v over c over 1 minus v over c and the square root. So we have lambda over c square root of 1 plus v over c divided by 1 minus v over c. Now that's the amount of time it will take for that next crest to hit. If we're interested in the frequency, so the frequency observed, of course, that goes like 1 over the time between when the crest hit. Bigger frequency means less time between each of these hits, and therefore we need to flip that guy upside down, c over lambda square root of 1 minus v over c, 1 plus v over c. And then we recognize from the formula that we have over here that that is just the frequency at which the light was emitted, this term in front. So this is nu emitted times square root of 1 minus v over c divided by 1 plus v over c. And indeed, that is the formula that we advertised, giving us the frequency observed in terms of the frequency emitted, a factor of square root of 1 minus v over c divided by square root of 1 plus v over c. And you can play with a nice little demonstration that I will leave it to you to manipulate, where you can choose the velocity of the source, you can choose the wavelength of the light that it's emitting, and you'll be able to see how the frequency of the light changes depending upon whether the source is coming toward you. That would be if you were in this location, or if the source is moving away. As you will note, if the source is coming toward you, the frequency will go up, which means that the color of the light will shift toward the blue. That's blue shift. If the source is moving away from you, the frequency will go down, because that means that v would be positive in that case, and that means the light gets shifted toward the red. So that's the essential idea of the relativistic Doppler shift. Let's then go on to understand how we would apply this idea not to light in general, as we've described here, but to the case of interest that we will apply this to in a moment, when we have our two characters, George and Gracie, sending flashes to one another, because it's just a moment's more work to recognize that the formula that we have derived here will be just as relevant in that case. What do I mean by that? Well, each flash that George and Gracie sends to the other, you can really think of each flash as just like a crest of a wave. So rather than thinking crest after crest after crest, you can think about it as flash after flash after flash. So exactly the same formula that we have derived for how the frequency of the wave changes can now be interpreted as how the rate of flashes changes based upon your relative motion. So there is the relativistic Doppler shift formula that we have derived for frequency. We now just reinterpret it as giving us the rate at which flashes are observed compared to the rate at which they are emitted. And I can show you a couple of visuals that will make that link between this picture and the flash picture a little bit more direct. or more precisely, between this formula and the formula that we are going to use in the case of flashes. So let's take a look at an example where we can see that interpretation in terms of flashes in action. So here, George is throwing one flash after another, and get a feel for the rhythm as Gracie receives them. So 5, 6, 7, 8, 9, right? You can feel that. But now let's change things and have some relative motion between them. In this case, Gracie's going to run toward the flashes, and look what happens as she does so. Get a feel for the rate at which she receives them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? You feel it. It's going faster because she's running toward them, and we would make use of our formula in which, as we've seen, the rate increase is augmented even more by time dilation, so that with v replaced by a minus v, which means that the rate at which she receives them goes up relative to the rate at which they were emitted. And you can look at the various other combinations too. So now we are going to do a case where Gracie, the source, is going to run. So George gets them 3, 4, 5, and so on. Now, if Gracie runs toward him, that also is a case where v would be negative as they are approaching each other, and get a feel for the rate at which George receives the flashes now. So she's still throwing them at the same rate, but he's going to get them 1, 2, 3, 4, 5 faster because of the relativistic Doppler effect. So that gives you a good sense of how the relativistic Doppler effect can be reinterpreted as giving us an understanding of the rate at which flashes are emitted versus how they are received. You should play around with a little demonstration over here where you can basically do a version of the animation that I just showed you. So here we have the velocity of a source, and I'm going to have the source throw out flashes in both directions. And you will note that the flashes on this side are piling up, so a person here would get them quickly. 1, 2, 3, 4, 5. Someone over here, very slowly. 1, 2, 3, 4, 5. So play around with that, because that's just an illustration of the relativistic Doppler shift formula. Our goal ultimately will be to apply this formula to the twin paradox, where the twins are sending signals back and forth. But the relativistic Doppler shift formula is vital and important in its own right. So look at the equation and try to get a feel for the math by manipulating the demonstration. We can now make use of the relativistic Doppler shift formula to give a quantitative explanation for what each of the twins, George and Gracie, will see if they have their telescope trained on the other during the scenario of the twin paradox. Okay, so let's see how that goes. The data that we're going to use, same data from before, we're going to assume that the velocity of Gracie's ship is 12/13 the speed of light. And now what we just want to record over here is the rate at which each of them will receive flashes when they are looking at flashes emitted during the outbound part of the journey, and when they are looking at flashes emitted during the inbound part while they are coming together. And we know how to do this. We have our formula, 1 minus v over c divided by 1 plus v over c. Put v equal 12/13. So we're looking at 1 minus 12 over 13, 1 plus 12 over 13, and that is the square root of 1 divided by 25 equals 1/5. 1/5 means one flash each 5 years. So when they're moving apart, that's the rate at which each of them will receive flashes if they're looking at light that was emitted while they were separating. Good. What about when they're looking at light that was emitted when they're coming back together? Well, we know you just flip that formula over. So instead of getting 1/5, we'll get 5. So it's 5 flashes per year when they're looking at the light emitted when they're coming back together. This 1/5, as I mentioned, means 1 flash per 5 years. Okay, so far we have complete symmetry between the two situations. I didn't even have to mention who was George, who was Gracie. It doesn't matter which is which. All that matters for that calculation is the relative velocity. Now let's make use of that calculation in order to work out the experiences of both Gracie and George in this twin paradox context where they are looking at each other. So let's work this out here, make it nice and clean. So here, George and Gracie, let's divide this up, and let's put over here the outbound part, and then we will do, let's put the inbound over here. Okay, so what is Gracie's experience? Well, from her view, she's traveling out to the turnaround point P. We've calculated before that that takes her 5 years. During that part of the journey, the relevant number over here is 1 flash per 5 years. So 5 years times 1 flash per 5 years, 1 per 5 years. She gets 1 flash during that part of the journey. Good. Then she turns around and she comes back. And from her perspective, that's another 5-year journey. Now, the relevant part of the calculation that we did over here is this one, 5 flashes per year. So 5 years times 5 flashes per year equals a total of 25 that she receives during that part of the journey. So if we add it all up together, she receives a total of 26 flashes. And that 26 flashes means to her that George has aged 26 years because he sends out 1 flash every time he ages 1 year. Good. Okay. Now, let's turn to George's experience. So George is looking at Gracie, and he knows that she is traveling 12 light years away before she turns around. She's going at 12/13 the speed of light, which means it will take 13 years for her to get to the turnaround point. Then she emits a flash that is an inbound flash. That's when the inbound part of her journey begins. But George knows that she's 12 light years away when she emits that flash, so it will take 12 additional years until he starts to receive the inbound flashes. So he says that the total journey for her is 26. He knows that it will take her 13 years to get to the turnaround point P. It'll take 12 years for the light from that point to reach him. So it will take 25 years before he starts to receive the inbound flashes, which means for the first 25 years, it is this calculation that matters, 1 flash per 5 years. So it's 1 flash per 5 years times 25 years when we take this into account, which gives us a total of 5 flashes. Then there's 1 year left on the journey from his perspective, and that 1 year is one for which the inbound part of the calculation matters. So from year 25 to 26, that is when he's getting all the inbound flashes that Gracie emitted after she turned around. So for 1 year, he is receiving 5 flashes per year for a total of 5 more flashes. And there we have it, a total of 10 flashes, which means that from George's perspective, Gracie has aged 10 years. She's sending out a total of 10 flashes. That's what he is receiving. She sends out 1 flash every time she ages 1 year, so 10 is the right number. And from Gracie's perspective, we see that she will see George age 26 years. He sends out 1 flash per year of aging. From his perspective, 26 is what she receives.
26 years is how much he has aged. Let's take a look at a visual depiction of that idea. So here we will now show each of our twins firing a flash at the other. And you will notice that there's a nice symmetry here in that 5 and 1 is what we see over here. And of course, you'll note that you will have 5 and 1 here, right? That is the outbound part of the journey, 1 flash per 5 years. But now on the return, look what's happening. Gracie is getting flash after flash after flash, but George, it's only at year 25 that he gets boom, 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 boom at the end, taking him to the total of 10 flashes. So we see that the asymmetry kicks in precisely because it's Gracie's act of turning around that is what distinguishes outbound from inbound. That turn affects her immediately because, after all, she's doing it. George has to wait 12 years before he even sees that she has turned around. So the inbound part of the journey from George's perspective only lasts 1 year, and that's why in total he gets a smaller number of flashes than Gracie does. Okay, so let's take a look at a little demonstration where you can play around with this very idea on your own. So here you can choose the speed of Gracie's spaceship at will. And if you play this, you will see exactly what we have been describing. Gracie gets very few flashes until the inbound, and then she gets many. And that's from her perspective. But if you now want to see, say, George's perspective, you can choose that too. And from his view, he is getting flashes at the small rate for most of the time until the very end, when he gets a bunch of them rapid fire. And once you have all of that well understood, look at both of them at the same time. And if you look at both of them at the same time, you will see the same kind of scenario that we just discussed, where it's symmetry until the turnaround. Gracie's now getting many, and only for that little window at the end does George get many. So that is a nice quantitative way of thinking about the twin paradox when they can't communicate. The final point I want to make is, again, one I mentioned before. These flashes are really indicative of how much George or Gracie has aged. They really are sending out the flash, if you will, on their birthday. Each year they're sending out one, which means if George sends out 26, he really has aged 26 years. And again, we saw this before, but now it will make more quantitative sense. If they're actually looking at each other, not just at the flashes per se, they will each see the other in slow motion because they're getting one flash for each of their 5 years that goes by for them, for that part of the journey. But then when Gracie turns around, she starts to get George's flashes rapidly, which means that she literally is seeing him move more quickly, age more quickly, and that's why we see him getting old. And it's only at the very end of the journey, when George receives the flashes in rapid fire, that he will see Gracie moving very quickly. He only sees her move quickly for a small window. There is a very straightforward, flat-footed version of the asymmetry between them. That is the resolution of the twin paradox when the twins can see each other, when they can communicate with each other. Perhaps the most famous equation in all of physics is E equals mc squared. It comes right out of the ideas that we have been developing. And I'd like to first give you a sense of where it comes from, just motivating E equals mc squared. For those of you who are taking the mathematical version of this course, I will do a full derivation in short order. But let's just begin with the ideas that lead us to the possibility that energy and mass, E and m, might be deeply related. They might have some deep connection that is ultimately embodied in Einstein's famous equation, E equals mc squared. Now, to do that,
I'm going to start by telling you a little story. A story that I like to call the parable of the two jousters. So it's going to be a kind of joust, but different from the one that you might have in mind. We're going to have two individuals perfectly matched. So they're going to be on identical horses. They'll have identical masses. And they're going to hold a lance, but not one that has a sharp end. We're going to imagine that there is a large metal ball at the end of the lance. And the way this joust will work, when the two combatants cross by each other, just as they are passing, each is going to lunge outward toward the other, smashing their spherical balls together, trying to knock the opponent over. So let's take a quick look at what that joust would look like. This initially was meant to be another George and Gracie animation, but I contacted Gracie. She said, talk to my agent, getting kind of diva-like. So we have a new character whose name is Evil George. So it's George versus Evil George. There they have their lances with the metallic spheres. They slam those into each other. And because they are perfectly matched, we are assured that it will be a draw, a tie. Okay, now George takes a course in special relativity, and he starts to think. He says to himself, from my perspective, I'm stationary, right? And therefore, Evil George is coming at me. And let's assume that this joust is happening at very high speeds. The horses are moving near the speed of light, let's just say, to be dramatic. And George says to himself, that means Evil George is in motion, from my view. That means Evil George's watch, his clock, is ticking off time more slowly. That means, from my perspective, Evil George, as he goes by, he may be moving quickly on his horse, but his movements will be slowed down, slow motion. So George says, this is going to be a piece of cake. Because as Evil George goes by, he's going to lunge at me so slowly that I will easily be able to knock him over and win. So that is his view in his mind. So just to peer into George's perspective as he thinks about this relativistically, he says, Evil George's lance is approaching me slowly, so I should win. And yet he doesn't win. It's still a draw. So the question is, what was George leaving out? Evil George thrusts the lance at him slowly. He should be able to knock him over because he is going to thrust it quickly. What has he left out? Well, if you think about it, the amount of impact that you receive from a joust of this sort depends on two things, not one. It depends on the speed of the lunge. That's absolutely the case. But it also depends on the mass of the sphere at the end. So what this tells us, because it has to be a draw again, right? Because it can't be that you change your frame of reference and you turn a draw into a win. All observers in space-time agree on the events. They may not agree on when and where they happen, but it can't be that from one perspective it's a draw, from another perspective it's a win. So we know it still has to be a draw. So how can it be that Evil George hits George with the same force even though the lance is going slowly? It must be that the mass of the sphere at the end of the lance must increase to compensate for the slow push that Evil George uses. So that suggests to us that energy of motion must be able to increase the mass of an object. And in fact, we can go a little bit further. We know the degree to which Evil George's lance has slowed down. It's just the time dilation factor, gamma, that we have encountered over and over again. So it must be the case that the mass at the end of Evil George's lance increases by the same gamma factor to precisely compensate for the slowdown with which Evil George is thrusting his lance. So that suggests to us that the mass of an object must depend upon its speed. The mass depends upon its speed, and the way it depends on the speed is the mass that it has when it's at rest multiplied by the gamma factor. Now, that is a remarkable formula because if we look at a little demo over here, look at what this formula is telling us. As the velocity of an object gets larger and larger, this is telling us that its mass becomes bigger and bigger. So you can play with this on your own, of course, but there you see it. As the velocity of an object gets larger, its mass grows larger and larger until, as it approaches the speed of light, the mass grows without bound. Now, this has a number of vital consequences. Number one, we have spoken a lot in our discussions about the speed of light, and implicitly, we've always been using the fact that nothing can go faster than the speed of light. But you may have recognized I have never really established that for you. Now I have, because if you think about it, when you try to speed up an object, you've got to push on it, right? Now, if its mass gets larger because its speed increases from your initial push, to get it go faster, still you have to push it harder and harder. And in fact, as the speed of the object approaches the speed of light, its mass gets bigger and bigger and bigger, which means you need to push harder and harder and harder to get it to go faster still, until at this point you need an infinite push to get it to go beyond the speed of light. No such thing as an infinite push, and that establishes that the speed of light is a speed limit for any object that has mass. The second consequence here is that this result strongly suggests that energy and mass are interchangeable, that you can take the energy of motion, the energy of Evil George's motion, it turns into, if you will, the mass of an object that he is carrying. So this interchangeability between energy and mass is itself pretty vital, but let's take it one step further still.
When an object is at rest, it still has mass, of course, m at v equal to 0, what we call the object's rest mass. So using the interchangeability of mass and energy, we're led to anticipate that the object at rest still also has energy. So let me motivate the formula for how much energy the object at rest has.
We know what the units of energy are in traditional units. You may recall it's kilograms times meter squared per second squared. If you're not familiar with that formula, don't worry about it, but this is the unit within which energy can be specified. Now, mass, of course, has units of kilograms. So for energy and mass to have the same units, we'd have to multiply mass by something with the units of meter squared per second squared. Meter squared per second squared. Well, meters per second, that's a speed. What speed would we multiply by in order to have some universal way of translating between energy and mass? Well, of course, the speed involved would be the speed of light. So this is one way of thinking about Einstein's amazing realization that energy and mass are interchangeable, sort of like dollars and euros, with the conversion factor between energy and mass being nothing but the speed of light squared. E equals mc squared. En route to E equals mc squared, which is where we are heading, there are a couple of ideas that we need to develop. We'll need to understand the notion of momentum in relativity. We'll need to understand the notion of kinetic energy in relativity, and then ultimately we'll be able to put it all together and arrive at our goal, a mathematical derivation of E equals mc squared. So I'm going to start with momentum in relativity. Think about how the ideas that we have so far developed impact the usual notion of momentum that you have encountered in earlier studies. Okay, so to do that, that naturally takes us to Newton's second law, right? So Newton's second law is usually written in the form F equals ma, But of course, that can also be written as dp dt, with p equal m times v, assuming that m is constant. So this is one way of expressing the traditional second law of motion. Good. Now, what I'm going to argue is that you can still, in relativity, have an equation of just that sort, F equals dp dt, but I'm going to argue that p has to be changed. If you are doing relativity, rather than an m times v, we'll see it's m naught, the rest mass of an object, v, its velocity, multiplied by the gamma factor again. And the way I'm going to do this is with the following approach. One of the critical features of Newton's second law is that if there is no external force acting on a system, if F external is equal to 0, then the total momentum of the system won't change. And what we're going to do is we're going to examine that idea relativistically. And what I mean by that is we're going to consider a collision between two particles, two identical particles, and we're going to consider that collision from two different frames of reference. And what we're going to see is if the traditional notion of momentum, m times v, is used, then that might be conserved in one frame of reference, but then it will not be conserved in another frame of reference. So we'll see that the usual conservation of momentum doesn't really hold true from that perspective if you use p equals mv. It might hold true in one frame, but it will not hold true in all frames. That will then motivate us to try to update our definition of momentum, and that definition is the one that we will come to. Okay, so let's take a look at the particle collisions. So here is collision number 1, and I'm going to look at the same collision again from a different frame of reference in a moment. Two equal mass particles, number 1 and 2, red and blue, they hit each other. Blue, as you saw, went up and down. Red came in at an angle and bounced off. The other collision that I'm going to look at, or I really should say the same collision that I'm going to look at from a different frame of reference, will be, well, let me do it over here. So I'm going to imagine that I go into a frame of reference that is moving to the right so that it is keeping pace with the red particle. In that frame of reference, what will happen? The red particle will come down and go straight up, and it's the blue particle that will be coming in from the right because my frame will now be in motion. Okay, so here it is. This is the same collision from frame number 2. Red goes straight down and up, and blue comes in and bounces off. And what I want to do is now analyze mathematically that collision from these two frames of reference. So let's draw a little schematic picture of those two collisions. So in frame number 1, the red particle came in and bounced off, whereas in that frame, the blue particle just went straight up and down. So I'll draw those arrows in a moment. And in the other frame of reference, say over here, it's the blue particle that comes in, bounces off, and carries on its merry way, whereas the red particle in frame number 2 is the one that goes straight up and down. Same collision, just with two different perspectives. And let me just put the arrows in so we don't get confused on what particle is doing what. I won't bother color coding those. But the red one comes in to this location, bounces off. The blue one goes straight up and straight down in that frame. In frame number 2, what happens is it is the red one that goes straight down and straight up, and the blue one comes in and bounces off. So those are the two pictures of the same collision. Now let's look at the issue of momentum, and in particular the issue of momentum conservation. So in this frame, and let me actually give these guys names so I don't have to worry about color coding. This is particle 1, particle number 2. And what we have in this frame is that the change in the y component of the momentum of particle 1, in order to have momentum conservation, must be equal to minus the change in the y component of the momentum of particle 2, right? So this guy goes up and down. This guy also goes up and down as well as moving to the side. But in the y direction, that's the relationship that must hold. There's no external force here. So that is conservation of momentum. And we can go even a little bit further. The change in the momentum, it was first going down in the y direction and then up, the red particle. If we just look at that component, this then is equal to twice the y component of the momentum. First down, then up. So the number minus minus itself gives it twice the number. Similarly, over here, this is 2py of 2. And therefore, we have py1 equals minus py2 from that little analysis over here. Now, let's do the same analysis for this collision over here. And I'm going to call the momenta primes in this frame number 2. In fact, let me label those as well. So this will be in frame number 1, and this will be in frame number 2. So the y component of the momentum of the first particle, just as before, the change in that must be equal to minus the change in the y component of the momentum of particle 2 for the exact same reason as before. And again, just as we had on the other side, this will be 2py prime 1. And this guy will be equal to minus then 2py prime 2. Now, the one other thing that we're going to make use of, and of course you can kill the factors of 2 and get the same formula in the prime system. Now, the one additional observation that we're going to make here is that this collision and this collision are so symmetric. The masses of the particles are the same. The only difference in some sense is that this one is a flipped upside down version of that one. So that symmetry allows us to easily conclude that the change in the momentum of particle 1 in this system over here, that's a 1, not a prime, that must be equal to, whatever this guy changes, must be exactly the opposite of what the blue guy does from this frame of reference, since they're just flipped upside down. So we can say delta py1, therefore, is equal to minus delta py prime 2. This now is a relationship between quantities in the two frames of reference. And because we know what is going on with these fellows over here in terms of how they relate to the momenta, we now conclude from this that py1 must be equal to, and from this guy over here I can now plug that in, and this guy will give me delta py prime 2, which is equal to minus of py primed 1, so the minus signs cancel, and I'm left with py prime 1. And that is the little equation that I was after, because, as I mentioned, we're after an understanding of momentum conservation in relativity. And here we have directly that form without doing much analysis at all, just using symmetry properties. The y component of the particle number 1 on this frame of reference must be equal to the y component of the momentum of particle 1 from the other frame. In other words, by changing your frame of reference, we've now established that you don't change the y component of the momentum because you're only moving in the x direction. Good. Now comes the crux of the matter. If we set using the Newtonian approach, so if we take Newton to heart and we set py, and I'm going to drop the 1s now because only particle 1 is going to be relevant for this calculation. So all of these quantities refer to particle 1, but I won't write it. If we set py, say, equal to what Newton would have told us to, namely that we set that equal to m times vy, and similarly, if we set py prime equal to m times vy prime, the question is it the case that py will be equal to py prime as is required by the analysis that we just did? And we can answer that question because we know how to get the relationship between the two velocities, right? The velocity that we've called velocity of particle 1, which is now just vy, that can be gotten in a straightforward way by using the velocity combination law, right? So here we have the velocity in the y direction of this guy being Vy prime. Frame number 1 is moving, if you will, to the left relative to frame number 2. It's moving to the left with the speed equal to minus Vx. So frame 1 moves with speed minus Vx relative to frame number 2. That's the way we set things up in order that in this frame the particle number 1 is bouncing in that manner, but in this frame it's going straight up and down. Frame number 2 had to move to the right with Vx, which means frame number 1 is moving to the left with speed Vx, and that's what that minus sign over here means. Now we know how to transform velocities, our velocity combination law from one frame to another, if we know the relative speed between them. And that tells us, therefore, that Vy can be written as Vy prime, remember this formula that we had, gamma of minus Vx multiplied by 1 minus Vx times Vx prime, which in this case is just 0 in that frame of reference. Gamma of minus Vx is just gamma of Vx. It only depends on the square of the quantity. So this gives us Vy prime divided by gamma of Vx. Now, if we take that relationship between Vy and Vy prime and plug it in, that tells us that we can write Py equal to m times Vy, but now I'll write it as Vy prime divided by gamma of Vx. And the question is, does that equal Py prime, which is m times Vy prime? And as you see, it doesn't. We have an additional factor of gamma of Vx in the bottom. So the answer to that question is absolutely no, which means that this formula that we derived that must hold for momentum conservation to work if you change frame from one perspective to another, that will not work if we use the Newtonian formula for the momentum of a particle. All right, so what then do? We have to change that formula in some way. How are we going to do that? Well, we have a good guess at our disposal for what to do, right? Because already in the parable of the jousters, we found that we really should think about m as not a fixed number. We found that we should think about m, the mass of a particle, as a function of its speed. And we said that the formula should be m0 times gamma of v. So maybe we should stick in that form for the mass into the Newtonian expression and then see if momentum conservation holds. It's a guess, but it seems like a reasonable guess. Let's do a calculation and see if that will fix up this problem with the failure of momentum conservation using the Newtonian formula. Okay, so here's our try. Here's our guess. So we're going to try the new formula where we're going to take momentum to be equal to, and I can do it in vector form, it doesn't matter, m of v now instead of just m times the velocity, where, of course, as I just said, this is m0 of v, gamma of v, multiplied by the velocity. So now what I want to do is take that expression, plug it in to this equation, and see whether or not it holds. And that's just a matter of doing a little bit of calculation. Couple lines, here we go. So we'll look at m0 multiplied by Vy. So this is for particle 1 in frame number 1. Now we're told to divide through by 1 minus Vx squared plus Vy squared over c squared, because again, in frame number 1, this particle has an x and a y component to its velocity. They both come in to the calculation of gamma. Does that equal the same expression when we plug that in for Vy prime? So m0 Vy prime, and we want to divide that now, the new factor, 1 minus Vy prime squared over c squared. Is that an equality or not? Well, how do we check that? Well, we know the relationship between Vy and Vy prime. So we calculated on the other board a second ago. Vy prime is equal to gamma of Vx times Vy, right? This is what we have in our little calculation over here. Vy prime over gamma Vx. I'm just going to multiply through by the gamma of Vx to put that in a somewhat more convenient form. And now all I need to do is take this fella and plug into this equation and see what I get. So this is a question mark. We're trying to see if this holds true. So we'll put this as m naught multiplied by gamma of Vx times Vy divided by the square root of 1 minus Vy prime squared is now gamma squared of Vx times Vy squared over c squared. All right, let's just carry on, follow our nose and see where this leads. So we get m naught times Vy. Gamma is 1 over the square root of 1 minus Vx squared over c squared. And then we have an additional term in the denominator here, square root of 1 minus the gamma squared there gives us a 1 over 1 minus Vx squared over c squared. That fella is now multiplied by Vy squared over c squared. And we can bring this guy inside. When we bring it inside, it'll turn this factor over here into a 1 minus Vx squared over c squared. What will it do to that factor? Well, to bring it inside, I, of course, will be multiplying those two guys together. And where should I put that answer then? So that then is equal to m naught times Vy divided by the square root of that first factor. Let me write that one out. 1 minus Vx squared divided by c squared. And then the other factor over there, that guy just cancels him out in the bottom, giving me minus Vy squared divided by c squared. And lo and behold, if I now look at what I had over here, it is an exact equality. So that's worthy of boxing this fella up, because we've now seen that our guess for what the momentum definition should be in relativity has borne fruit, because by using this new form, not just mv, but m naught gamma of v times v, by using that new form, we have indeed found that this momentum conservation equation holds, right? So this then is the justification for the formula that we have here, that in special relativity, when objects are moving quickly in particular, you need to use this different form for the momentum, which has the factor of gamma in it. So let's take a look at a demo where you can see this new momentum formula in action. So this demo assumes that the object has a certain mass at rest, just chosen to be 5 kilograms. And now as you vary the speed, the velocity of the object, you're not just getting m times v, you're getting m times v times gamma. So as you see, the momentum starts to really pick up, of course. That's again just our friend the gamma factor coming in, kicking the momentum up very, very large when the velocity approaches the speed of light. So this concludes part 1 of our approach toward E equals mc squared. We now understand the relativistic form of Newton's law, the relativistic form of the formula for the momentum of a particle that has velocity v. With the relativistic formula for momentum under our belt, we can now use that to work out the relativistic form of the kinetic energy, right? So that's a straightforward thing for us to do. Let me just quickly show you what we're going to find before we get there. We're going to find that rather than just having, say, 1/2 mv squared, the Newtonian expression, we'll have a somewhat more complicated form for the kinetic energy. But it is straightforward for us to work out where that comes from. Okay, so what do? Well, when you talk about kinetic energy, you can talk about building it up from a force that's acting on an object. So if you want the change in the kinetic energy that a particle experiences, we know how to do that. You just look at the amount of work that is done on it. And for the work done, that of course is equal to a force acting on it that's exerted through some distance. Let's say that's delta x. And using the fact that F is dp dt, we can write this as dp dt times delta x. And we can play a little game where we take the delta x and the dt, or the delta t, put those guys together into a velocity, and write this as dp dotted with or times the speed v. Now, that's a nice way of writing things, because we can write down p also in terms of v. It's just m naught times v times gamma, which is 1 over the square root of 1 minus v squared over c squared. And then putting those together, we can write down, if you don't mind me writing this in a more calculus type form, d of the kinetic energy is equal to d of m naught v over square root of 1 minus v squared over c squared multiplied by v. And now we just integrate this expression up to get our answer. And let me just write it down formally, and then I will give you the answer. So integral of the d of the kinetic energy is the kinetic energy. And you can calculate that by just doing this integral that we have over here, v d of the stuff inside, m naught v over square root of 1 minus v squared over c squared. Now, I've not really been using much calculus at all in the discussion that we've been having, so I'm not going to assume that you are expert on doing these kinds of integrals. I'm going to give you the answer in a moment, but let me note, if you want to go through all the steps, there's an office hour question in the timeline to the course where you can look at the calculation, and it will guide you through it step by step. But now it really is just reduced to a problem in calculus, and so this is something I'm just going to give you the answer, because we're not really interested in teaching calculus in this particular set of discussions. So if you do that integral, here is what you find. Kinetic energy will be equal to m naught c squared multiplied by 1 over the square root of 1 minus v squared over c squared minus 1. And that is our relativistic form for the kinetic energy of a particle whose rest mass is m naught and is traveling along with a velocity v, just as advertised. Now, one quick thing that's useful to point out here, which is probably clear from the discussion before, that the mass of an object soars to infinity as its speed approaches the speed of light. Here you see, too, as v approaches c, this expression over here gets larger and larger, so the kinetic energy gets larger and larger, which is another way of concluding, again, that there's no way to reach the speed of light. You can get close, but it would take infinite energy to get there. So let's take a look at a little demo over here where we can just see that spelled out for us. So in this demo, what we are choosing is the rest mass of some object, a particle. Then you get to choose its velocity. And in this column over here, there's a comparison between the result in special relativity and the result that Newton would have given us. And you see that there is a difference between them. And as the velocity of the object gets larger and larger, that difference becomes ever more pronounced. But you do see that when the velocity is small, Newton and special relativity actually do coincide with one another. And that is something that we can derive just by looking at this equation over here, just for one more second. So if I imagine that v is very small compared to c, then I can expand that 1 over the square root in a Taylor expansion.
So this then becomes close to, only for v much less than c, I will get my m naught c squared in front, 1 over the square root of 1 minus v squared over c squared. Taylor expand that, and you get 1/2 with a plus sign. So you get 1 plus 1/2 of the quantity inside the bracket, which is v squared over c squared. So again, if you're not familiar with Taylor expansion, that's something that you should learn about. But this is a close approximation to that formula. And then I still have the minus 1 from over here. And that then, of course, is now equal to m naught c squared times 1/2 v squared over c squared, as I start to write ever more downhill. But let me then cancel out those c squareds and write this as 1/2 m naught v squared. That's great, right? So there you see the usual expression that Newton taught us about, 1/2 m naught v squared, 1/2 mv squared. And that's why we have this nice confluence of the Newtonian curve and the relativistic curve at low velocity. But we see that at high velocities, there's a sharp distinction between the two of them. Kinetic energy in special relativity is fundamentally different from what Newton would have thought, and that difference becomes ever more pronounced at larger and larger velocities. We're now ready to take on E equals mc squared. Let me just quickly remind you of the meaning of E equals mc squared. The idea is we want to establish that energy and mass are convertible. They can be transformed one into the other, and that c squared is nothing but the conversion factor that takes you from mass to energy. Now, we actually have already seen a hint of E equals mc squared in our formula for the kinetic energy of a particle. And let me just show you this little hint. It's just suggestive, but then we will do the real thing in a moment. The hint that I have in mind is when we talk about the energy of an object, we know that we usually break that up into kinetic energy plus potential energy, which means that kinetic energy can be written as the total energy minus the potential energy. So let's take the form for the kinetic energy that we have and write it in this way. So kinetic energy we have as m naught c squared times 1 over the square root of 1 minus v squared over c squared minus 1. Let's write that in a form that's similar to what I have on the top line. I say m naught c squared times gamma, so that's just my gamma over there, minus m naught c squared. And this way of writing it is suggestive. In fact, it's true. But this might lead you to think that the energy, total energy, is given by m naught c squared times gamma, and that there's some kind of potential energy, stored energy, if you will, in the mass of a particle itself, and the amount of stored energy looks like m naught c squared. So again, that's just suggestive. Let's now undertake a real physical mathematical argument to derive E equals mc squared. And to do that, I am going to play a game that is very similar to the game that we played in trying to come up with the relativistic equation for momentum, right? Remember how we did that? We looked at one and the same collision, but we looked at it from two different frames of reference. We are going to do the same thing now with another specially chosen collision between two particles. And the kind of collision that I have in mind that I'll show you here involves two particles coming together, slamming together, and sticking, creating one particle whose mass is going to be bigger than the mass of the particles that come in. Now, the thing that I want you to think about, as this will be critical to the approach that we're taking, ordinarily, if particles slam together, we assume that we hear something, we assume that the air molecules get jostled, and therefore some of the kinetic energy that comes in gets converted to waste, heat in the environment.
But we are going to imagine that in this kind of a collision, there is no environment to take away any energy. We are going to assume that all of the energy is totally in the system at the end if it was there in the beginning. And the question is, therefore, where does the kinetic energy of the incoming particles go? And we are going to argue that the kinetic energy that they slam together with goes into increasing the mass of the particle that they create. Their kinetic energy is going to be transmuted into an additional mass of this particle that they create. And we're going to calculate how much additional mass this particle gets from the kinetic energy, and that will lead us to the promised land of E equals mc squared. Now, to do that, I'm going to consider that collision, but from another frame of reference. So this frame of reference, as you will see, is one in which the second particle, remember there's one particle that came in from here, the other particle came in from the other side. Let's look at a frame of reference where that second particle is at rest. In other words, we have a frame of reference that is moving to the left with the speed of the original incoming particle from the right. So here it is. One particle is at rest, the other particle slams into it, and of course, finally, it pushes the combined particle off to the right. Now, we're going to do a mathematical analysis of this collision in particular and show that the kinetic energy must be transmuted into mass. So I'll call this particle over here particle A, and it may be a different color from what you just saw a moment ago, but don't worry about that. This guy, particle B, is the one that it slams into. Let me get that in a closer line over here. I don't know if that's much better, but imagine these guys are in the same line. So this guy over here on the left is coming in. He slams into that particle. So this is what happens, say, before the collision. And then after the collision, they join together into the third particle, which itself is kicked off to the right because of the incoming collision from the left. So, if you will, this is what we had before. This is what we have after. And let's now fill in some of the mathematical details and do some calculation. All right, so let's call this guy A. Let's call this guy B. You might think I'd call this guy C, but I won't because I don't want to get confused with the speed of light. So let me call it particle D. And I am going to assume that in the laboratory frame, that both of the particles that we looked at over here, assume that these guys were coming in. So I might as well just have the lab data as well over here. So in the laboratory frame, what was happening is the particles were both coming in. So one particle was coming in this way. The other particle was coming in this way. And from the laboratory perspective, this guy, say, had velocity v. This guy has the same speed v in the opposite direction. So this is particle A in the lab, and this is particle B. And this is particle D. So if that is the picture from the lab point of view, then from the moving frame, which makes particle B stationary, there is a standard calculation that we are now quite familiar with to determine the velocity v prime of A in the moving frame. All right? How do we do that? Well, we know that the frame that we are looking at, the frame in which B is at rest, is a frame that's moving this way with a velocity equal to B, which means that v prime gets increased by the amount of the velocity of that frame. It's got velocity minus v, because that frame is moving to the left, but we know there's a correction factor, and the correction factor is 1 plus v times v, v squared over c squared, just our favorite velocity combination formula. Good. So that's the velocity of particle A in this frame of reference. What about the velocity of particle D? Well, in this frame, particle D was at rest, So if the new frame is moving this way, then particle d is moving that way with velocity v, as I've indicated over here. Now we're in good shape because we can calculate the consequence of momentum conservation in this frame of reference. So let's write down that the momentum of particle A in this new frame of reference is equal to then the mass of particle A times its velocity times gamma. So we have to divide through by square root of 1 minus v prime squared over c squared. And therefore, we can substitute in this expression for v prime in terms of v. So we've got 2v over 1 plus v squared over c squared. We can plug that expression for v prime into here. And I'm going to leave it to you to do the algebraic simplifications. Couple lines of algebra, not hard. You'll find that the momentum of particle A in terms of v is 2m naught v divided by 1 minus v squared over c squared. OK, that's the momentum of particle A. What about the momentum of particle D? Well, first off, this, of course, is equal to the momentum of particle A by momentum conservation. But let's write down the formula for the momentum of particle D in its own right, which is equal to its rest mass, m naught of d, times its speed v times gamma, which is square root 1 minus v squared over c squared. And the nice thing now about equating that expression to the momentum of particle A is that we have the ability to solve now for the rest mass of particle D in terms of the rest mass m naught of particle A. And equating those two expressions, we'll find that m naught of d is 2m naught. Now that's not quite the end of the story, because if you look over here, I've got a 1 minus v squared over c squared in the denominator for the momentum of particle A. But for d, I've got a square root of 1 minus v squared over c squared, which means for these guys to be equal to each other, I need to throw in one more factor of the square root of 1 minus v squared over c squared. And that is a remarkable formula if you think about it for a moment, because it's basically telling us that the rest mass of particle D, that's this guy that we have over here, the mass of particle D when at rest is not equal to 2m naught. It's not equal to the sum of the masses of the two particles that are coming in. It's a little bit bigger than the sum of the masses of the two particles coming in. This expression right here is showing us that the kinetic energy of A and B as they collide with one another is being transmuted into an additional amount of rest mass of particle D. You would have thought that the rest mass of particle D, you just add up the mass of A and the mass of B to get 2m naught. But we don't have 2m naught. We have something bigger by the factor gamma. So let's actually calculate how much bigger it is than we would have anticipated. So let's look at that expression that I have over there, which is 2m naught multiplied by gamma minus 2m naught. This is what we would have expected. So the difference then is equal to, let me call this delta m of d, is equal to 2m naught times gamma minus 1. This is the additional mass that this particle gets from a conversion of the kinetic energy between those two incoming particles. Now, how much kinetic energy did we have at the start? So from the laboratory expression, at the start of this experiment, when A and B are coming in, each of them has the same kinetic energy. So kinetic energy total is equal to 2 times the kinetic energy of each of them individually, and that is equal to m naught c squared
times gamma minus 1. That is the formula that we have already derived. So now you see what's going on here. The kinetic energy equal to 2 m naught c squared gamma minus 1 is being converted, this is being converted into that amount of rest mass. So if I think about that in equations, I'm saying that the change in the mass of this particle d can be thought of as equal to the change in the kinetic energy. This is the kinetic energy at the start. At the end, there's no kinetic energy, so that's the change from before to after. You take the change in the kinetic energy, divide through by c squared in order to get the amount of mass that that turns into. And that is a nice expression because if you think about it, the additional mass from the colliding particles is just mass. It's like any other mass, and we're basically saying that the particle d at rest has some frozen energy inside of it. It's holding on to the energy that was initially kinetic energy. Now it's turned into mass, and you could in fact envision building up the particle d by many of these collisions over and over and over again, making its mass bigger and bigger until we have the form that we have here. So what this is really telling us is that there is a rest energy, which is what we usually call it, a rest energy of the particle d, an energy that it embodies even when it's sitting still, because that kinetic energy has been turned into that, which is given by the mass of d at rest multiplied by c squared. So that kinetic energy turns into mass times c squared. The particle is at rest, and yet it embodies that amount of energy. Now, if the particle is moving, then it has its own kinetic energy. So let's get the total energy of this particle, which we would get by looking at the rest mass times c squared times gamma minus 1, the formula that we derived earlier for the kinetic energy of a particle. But now we add in this additional energy that we have just established that it contains even when it is sitting still. And putting those together, we get at our formula m naught, so the mass of this particle when it's at rest, times c squared times gamma. And that is Einstein's famous formula. That is E equals mc squared, because typical notation that we use, if we define the, in fact, let me just do it over here because it's our final and important equation. So if we define the mass as we have been doing, now we have established it mathematically, m of v defined to be the rest mass of an object divided by 1 over the square root of 1 minus v squared over c squared, then the equation I have on the other board is nothing but E equals mc squared with this definition of the relativistic mass. So there you have it. E equals mc squared. It simply comes from this beautiful little argument. The kinetic energy of the incoming particles slam together, and we can show that it increases the mass of the particle they create to be larger than just the sum of the masses of the incoming particles. Their kinetic energy is transmuted into mass. The particle at rest therefore has that energy inside it, and the amount of that energy is given by this formula. Delta m is the change in the kinetic energy over c squared, which gives us E equals mc squared, with the mass being the mass that depends on v. Mass goes like m naught 1 over square root of 1 minus v squared over c squared. One quick little example so we can see the power of this result. We've shown here that energy is being turned into mass. Of course, you can go the other direction too. Mass can be turned into energy. And doing a little calculation just to see the power of this result, if you had 10 kilograms of potatoes just sitting at rest, plug that into E equals mc squared to get the total amount of energy that the potatoes at rest
would give you. Gamma in that case is 1, so it's just m naught c squared. Plugging that in, you find that the result is 9 times 10 to the 17 joules, which in kilowatt hours is about 10 to the 11 kilowatt hours. Just to give you a feel, New York City uses about 10 to the 11 kilowatt hours each year. So were you able to extract all the energy in 10 kilos of potatoes, you'd be able to power New York for a year. That really gives you a sense of the wonder and power of this unexpected interchangeability of mass and energy in Einstein's famous E equals mc squared. Thanks for coming along on this ride into the wondrous world of special relativity, these wild ideas that come out of Einstein's thinking about space and time, and matter and energy. Let me leave you with just one thought as you reflect back on all of the material that we've covered. All of the results that we have found, all of them fundamentally come from one idea: the constancy of the speed of light. Right? That is where the relativity of simultaneity came from. Remember, forwardland and backwardland, it's the constant speed of light which makes it so that those on the train and those on the platform do not agree on what happens at the same moment. The constant speed of light is what makes clocks tick off slowly as they are moving by us, right? We use the light clock. Again, constant speed of light as it travels along the double diagonal. That is why time ticks off slow when a clock is in motion. We then parlay that into length contraction, where lengths of objects in motion appear shortened along the direction of motion. And finally, we've gone further, and we've come to this stunning realization that energy and mass are interchangeable. Again, it comes from the constant speed of light, the fact that observers in different frames of reference should agree on, say, momentum conservation, and the transformation between one frame and another is dictated by the nature of light, the constant speed of light. It all comes from that single idea, which is just to show that if you focus on an idea, if you focus on some new feature of the world and are really able to think it through to its logical conclusion, sometimes that results in a revolution in the way that we think about things. So go back to the rest of the course, review it, try to get a feel for these wondrous ideas, because special relativity is truly one of the crowning achievements of our species.